Right before we get going, I want to again recognize really the sponsors for our workshop as we head into our third and final day. The Natural Science Foundation and NCAR, without them, we wouldn't be able to put this on and have a great venue that helps us keep the registration costs down for folks. So one, thanks to NSF, who also provided funding for our students to be able to attend. So that's a wonderful thing. Also, Building Envelope Consultants, that's David Ballesteri. David supported our first workshop and has continued to do so now. Sentinel Tile Systems, and IBHS and Verisk. So thank you to all those folks who've helped make this a success again, I would think. I also want to recognize Shelly Rayburn out front. Shelly handled a lot of the logistics and has done just a fantastic job again, making sure this goes. Without folks like Shelly, we wouldn't be able to do this. So let's actually give Shelly a round of applause if she can hear us out front on the speakers. Thank you so much. Wanted to make sure we get those in. Also, Kelvin and our AV team back there, you guys raise your hands. We'll give them some applause. As somebody who has participated in many insurance industry hybrid meetings, they're doing way better than those guys. So great job, Kelvin. We really thank you. And this has been wonderful from a hybrid perspective to be able to offer this. And we wanted to make sure we could do that. One, not only from the issues we deal with our wonderful global pandemic, but also this has made this workshop so much more globally centric. We've gotten all the perceptions from across the globe, getting to see all the great and kind of renaissance and hail research that's going on. So it's been a wonderful experience. So again, Kelvin and his team made that happen with the hybrid side. So thank you to them back there. Again, I will also remind you in that note to upload your slides if you haven't done that already. I'm looking at John Allen, Andy Heimsfeld. Actually, it's Matt Phelps back there. Yeah, I just wanted to give Andy a hard time, but I think we're good there. Those are the only two. And so John is on the steering committee, so please, you can just kindly nudge John to get his slides in. All right, everybody, good morning. I apologize again. I'm losing my voice, not conditioned for this. We have a wonderful panel this morning to kick off a session focused on damage. So now we're down at the impact part of hail and hailstorms. So I'll introduce our panelists, and we'll get going kind of how Julian did it yesterday with a couple of start-off questions, but get your minds going, think of those questions, and hopefully we'll get some good engagement again and have a great panel discussion. So I'll start off just looking down the road here. Robert Wright from Robert Wright and Associates. Robert is a forensic engineer, so he's with us to talk a bit about how we assess damage, look at it in the field. Up next is John Sedgwick. John's the founder and president of VDE Americas, dealing with commercial scale utilities. John's here to talk about hail risk and impacts on photovoltaic systems. Next is Chris Sanders. Chris is from IBHS. He's a research scientist and actually has done quite a bit of our impact testing. Chris also, though, in a past life was an insurance adjuster. So he has a little bit of that there. Next up, Emily Sambuco. Emily is a senior catastrophe risk specialist. Did I get that? No. Yeah. Okay. At Liberty Mutual. So Emily's going to talk a little about the big picture of risk and what we're seeing in terms of losses. And last is Greg Keeler. Greg's the technical services lead at Owens Corning. Yeah, everybody should know Owens Corning, but Greg also was actually a building code official prior to coming to Owens Corning. So he has a wonderful perception on both from the manufacturer side, but how we deal with more resilient construction in the codes realm. So it's a wonderful kind of industry panel we have. And so we'll go ahead and get going. Our first question, we're going to start off with Emily. From a big picture of severe convective storms, what does the trends and losses kind of look like? What concerns you the most? What are some of the mechanisms we can do to help bend down that curve? So let's start with just the big picture of severe convective storm loss, and how do you guys view that from the insurance space?
Sure. I had a feeling I'd be first. I got two mics.
There we go.
Well, we all know that losses are increasing, right? And there's a lot of uncertainty with climate change impacts to hail. But one thing that is certain is population growth and exposure growth. So what I think a lot about is the human impacts to hail losses that we've seen and what we'll continue to see. And from the insurance side and from the catastrophe modeling perspective, we're trying to figure out what those other influences are. Things like what we call the expanding bullseye effect. So as we grow our urban centers, more things are there that we care about that are getting hit by hail. So that's a big factor. But, hail size and hail severity often doesn't correlate one-to-one with the claims losses that we're experiencing. A lot of things are going into that, like societal norms, societal shifts, social inflation, that kind of thing. You're more likely to file a claim if your neighbor got a new roof because they filed a claim for the same storm that rolled through. There's this also like this compounding small hail event problem where over time, many little events will impact a roof, and then someone knocks on your door and checks out your roof, and all of a sudden you're good to go. You can file a claim and get a new roof. So it's almost like this binary pattern that's happening with claims loss with hail that often, doesn't correspond to what the scientist in me says, oh, it's hail severity, hail size. So I think there's a lot of complicating factors there that we're trying to figure out, especially when we're modeling from a catastrophe perspective.
Yeah, I'll kind of stay on that theme a little bit. So we're coming at this a couple days into our workshop. You've seen a lot of the science that's presented from the catastrophe risk assessment perspective. What are some of the things that we as a community could do to help with that assessment? What do you need to have better tools to assess that financial risk and to start to make some lever changes to see if we can't get that loss trend under control?
Right. And from the catastrophe modeling perspective, I think better data is an obvious one, right? We use catastrophe models, and what we get out of the models is directly related to what information we put in. And so if we put in crap data, we're going to get really unreliable results out of it. And that's part of the reason why hail has been so difficult to consider as far as like our holistic catastrophe risk. And there's a lot of work happening in this space. A lot of people in this room working with AI algorithms, that kind of thing, to develop ways to figure out hail or roof age, roof condition, those types of exposure characteristics that are really valuable when we're modeling hail in our catastrophe models. So that kind of thing. And then also, partnerships with groups like IBHS and the like, just to further understand what types of mitigation features policyholders could put in place, and finding a way from the insurer's perspective to incentivize our policyholders to make those mitigation changes, because it's a win-win, right? It's in the best interest of the insurer as well as the policyholder. And so work that you all are doing has been very helpful to understand what types of features policyholders could actually do to help reduce their risk.
So on the risk note, I'm gonna change up our order a little bit, and I'm gonna go to John, because John, talk a little bit about your experience in evaluating hail risk from a commercial power production perspective, whether we want to dive into the photovoltaic element. How do you guys approach that and manage that risk?
Yeah, thanks a lot. Appreciate being invited to this. It's very interesting having a mix of industry and academic. It's fabulous to be there. And yeah, much what Emily, you were talking about is very pertinent. And what we're looking at it is more specific to photovoltaics. And the specific photovoltaics that we operate with, that I operate with, is large scale, utility scale projects. They're hundreds of megawatts to almost a gigawatt in scale right now. So there's thousands of acres of glass out in the middle of Texas. Nobody would expect any problem with that, would they? Believe it or not, a lot of smart people did not expect it when they started deploying that in that area. And then we had a couple of events that triggered some very severe responses by insurance companies. So for the past couple of years, we've been working very closely, very closely with John Allen in developing some tools for doing risk assessment and return-interval calculations of hail specific to a photovoltaic site. So the location is critically important. A lot of other cat risk modelers will look at large areas of geography. We need to look down at the actual equivalent size of the project site.
I think that's a great point. I think the work that we've had here too is anytime we can assess probability of an event happening, but also look at the damage element too. What's the probability distribution of damage as well, and how do those line up. So all that work we've talked about over the last 2 days certainly has so many industry applications. So it's kind of a point there. So thank you, John. We're going to keep working our way down in scale. We'll come back to you in a little bit once we get down to the photovoltaic test side of things. But I'm going to go to Robert now. So Robert, you're there at the roof level, but many of us in the weather enterprise may not have a clue what a forensic engineer does, what do you do, and how you do it. So I'm going to give you a little bit of time to explain that, and then we're going to talk a little bit more about damage and work our way down to Chris and Greg down at the scale of materials.
Yeah, I started my career as a structural engineer. I started in 1980. And structural engineers basically, and I'm talking about buildings, design buildings for gravity loads and lateral loads, and they make sure the elements in the building can stand those loads. A forensic engineer, I started that in 94. It's a completely different way of looking at it. It's damage models of a building, particularly for hail. We look at hail, wind events, but for this venue, it's hail. So we look at the envelope of a building. And we want to assess the damage to the envelope. And the reason that's important is because when water gets into a building, it really starts degrading the building, and you start having all other kinds of problems like rot, corrosion, mold problems, other types of pathogens inside the building. So we really want to make sure that the envelope of the building is performing like it's supposed to be. Typically, and I'm going to limit this just to roof envelopes. There's wall envelopes and roof envelopes. But when we go out and we do this, well, let me start with this. The word forensic means in a forum of a forum. It's a legal forum. So what I do, a forensic engineer writes reports to be presented in the courtroom. And we go through a process of depositions, and sometimes we have to testify in the courtroom as experts. So, and typically what I do is I have a three-prong approach. I do a detailed analysis, time history of the weather event. I actually get up on the roof. I do test squares and things like that. I'll use thermography, drones. And then I'll find papers that are out there that are written that talk about damage thresholds, and I compare the damage thresholds to what I see. I look at the directionality of the storm. I'll actually pull in the radar imagery. I'll cut a section through it. I'll look at some of the thermodynamic relationship to make sure that it was high enough, it was cold enough, there was enough energy to see if the probability of hail was realistic. And I look at directionality, and I'll put that directionality on the roofing envelope. There are two sides of this. The policies, the insurance policies actually drive the boat. What's excluded in the policy and what's covered. And we have two sides. We have the side that represents the engineers that represent the insurance carriers that are the defendants. And we have the other side that represent the owners or the plaintiff. I've worked on both sides, but I tended that I work on the plaintiff side most of the time. Not that I won't work for the other side, but they don't call me up very often. So it's an adversarial process. It needs to be an adversarial process because people are approaching it from two different perspectives. I find a lot of times the guys on the defendant side or the insurance carrier side will look at the exclusions, and they tend to migrate towards what's excluded from the policy. Guys on my side tend to look at what's covered and migrate towards that. And so it ends up being a clash of two sides saying, the damage. Another really key thing is date of loss, and that is a pretty tough thing. What I have found is the research that you guys are doing is going to trickle down, and it's going to start affecting building codes. It's going to start affecting things like the Lorry chart for terminal velocity and kinetic energy, the more research that's done. And let me just go to the final thing, and that's the damage, the definition of damage. Policies have typical definition of damage, and it gets played around with, but I typically use the Oxford definition. It's physical harm caused to something in such a way as to impair its value, usefulness, and normal function. So there's 3 criteria when we look at, say, a roofing envelope. Cosmetic damage. Did it get cosmetically damaged like a metal roof? The second criteria, did it shorten the life of the roof? Typical roofs have a certain lifespan. The third criteria is, did it change its function? The function of a roof is to shed water. Did it compromise that, and is water actually getting into the roofing system? So that's what you find in policies, and then they find that there's certain things that are happening out there to change, certain kinds of exclusion, like cosmetic exclusions, granular loss exclusions. I'm finding marring exclusions now in some of the things I'm looking at. So with that, Ian.
Yeah, so Robert brings up a good one. And at IBHS, one of our goals in a research perspective is to actually challenge a lot of those assumptions. So to encourage everyone to actually see Brenna Meisenzahl's talk coming up in this session about, we talked a little bit about the small hail problem, what that can do to the lifetime of a roof. So Brenna's got some great work that we've been doing, but Chris has also done that. So we're going to get to that in a second. So thanks, Robert. We're going to turn now to Greg on the end. So Greg, you're at Owens Corning. We're going to look at asphalt shingles. It's on 3/4 of the roofs in America. I should say that my wife, Tanya, and I, we have an OC product on our roof. And Greg has I need to preface, they have 2 products that are in our good performer category and our IBHS ratings. Greg, from the shingle industry perspective, what are we needing to help raise the overall performance bar of products that are out there in the marketplace?
So the asphalt shingle industry takes the problem of hail very seriously. We do a lot of research. We work with IBHS very closely. We work with other test labs closely. We work with Dwayne at UL very closely. I'm responsible at Owens Corning to help draft some of those standards and help maintain those standards in a form that makes sense for the industry. So I would say that the industry is taking it very seriously and always working on developing new innovative techniques to make the shingles more resilient to hail damage. The problem that we have is that the testing standards haven't quite caught up with the hail problem. We're working very closely with IBHS on their ice ball test standard. And I'm also co-chair at ASTM of a task group that's working on developing an ice ball test standard. And really, from the testing standpoint, it's not the impacts that cause the problem. IBHS has done a wonderful job of collecting data and coming up with a procedure for impacting the shingle products. The problem is assessing that damage. You've got to come up with an assessment tool that is not too subjective. You can't have human interface driving the results of that testing. And so that's what we're working on now, is coming up with a test standard that replicates real ice ball damage, but also assesses the way the damage impacts the product. As was said earlier, damage is making the product less useful than it was intended, or reducing the life of that product. And we're working on trying to characterize what is damage really on an asphalt shingle roof.
So I love it because it's the world I live in, and Greg knows that. But Greg, I'm going to keep going there, and we're going to get a little myth dispelling. Since we started this work at IBHS, we did realize that there are good performing asphalt shingle products out there, absolutely. But I want you to talk a little bit about the cost, because there's a misnomer that the cost is so much more ginormous. And that's the argument that we often hear just across the industry, that the cost is so prohibitive, we can't do this. But talk a little bit about that.
Well, that actually goes more into the building code realm, because those of you that aren't familiar with the way the building codes are adopted and modified, stakeholders from all areas of roofing come in, roof consultants, structural engineers, building officials, insurance companies, and most importantly in this conversation, the National Association of Home Builders. And so anytime anyone proposes anything that in the code that would increase the cost of construction, you can almost guarantee that the National Association of Home Builders is going to fight against it. So that's the fine line that we have to balance right there, is the innovation and the cost of the innovation, the cost of the final products, and the cost of the homeowner and the affordability, because as we know, affordability of homes is already very, very difficult, especially right now. And so increasing affordability is at the top of most people's lists. And most people will say, when it comes to hail especially, well, I don't live in an area where hail is prevalent. But it may not be prevalent on a routine basis like it is here in Denver, in the Denver area. But all it takes is one hailstorm that can produce size enough, large enough hail to create damage, and that kind of pretty much shoots the roof right off the deck. The insurance companies then have to deal with the replacement costs of that roof. So it's really a fine line, but I can tell you with the advent of SBS products, that does add cost. Obviously, it's another step in the manufacturing process that we haven't been doing historically, but it is a step up. So we started with a scrim-based product. I don't know how many people here are familiar with asphalt shingles, but the first impact-resistant products were basically scrim-based. They had a fabric on the back side of the shingle that prevented it from cracking when it was impacted. Then the SBS came along, and we've been using SBS in our underlayments for years. Any of the polymer modified self-adhering underlayments are all SBS-based products. And we realized, based on the performance of those and the properties of those, that might actually work pretty well in an impact-resistant shingle. And so we've incorporated SBS into our asphalt compounds and found that those shingles are much more resilient and do fare much better in hail events.
Yeah, thanks. Great. Yeah, most of on our rating system, the modified asphalt products are all the good performers that you would see. Very quickly, I'm going to turn to John on testing standards, since Greg touched on it. What's needed in the photovoltaic space from a test standard development? A lot of times we see emerging technologies, the business side grows so much faster than the engineering and testing processes can keep up.
Yeah, I'd say that statement is absolutely true. It's very interesting, the similarities between what's going on in the roofing industry, which I'm not familiar with, and what we're dealing with at utility scale power plants that are assets that are valued in the 500 million or more kind of a range. So testing has been completely inadequate in our industry, totally inadequate. The existing tests that were out there are one that provides hardly any information at all that we need in order to do a proper risk assessment. And technology changes so quickly that there are so many moving variables that the industry is changing rapidly. And it's kind of interesting in relative to hail that the deployment of photovoltaics largely happened in places like California and Hawaii and New Jersey previously. But then because of incentives in Texas, there's huge deployment in Texas recently. So we didn't think we had a problem when all we were doing was deploying in Southern California. And the other element, I've been in solar for 25 years now, and every second of that 25 years, all we've been trying to do is reduce cost. And reduce cost means you're using thinner glass, thinner materials, faster manufacturing. In other words, you're making everything less hail resistant, and you're deploying in a more hail prone area. So testing is currently completely inadequate. There's a lot of effort in the industry to develop superior testing methods. Going through the IEC standard, which is what we normally utilize, is really a painful process. It's like United Nations negotiation committee. It takes a long time. However, there's manufacturers that think they have a competitive advantage where they can be more readily deployed in places like Texas are doing quite extensive testing. The IEC standard, they take a 25 millimeter freezer ice ball that's highly defined and identified by the IEC, and then they throw it in a panel in a normal, and then they look for glass break. Every single panel has been tested under the IEC 61215 that I'm aware of passes. But other manufacturers now are doing much more statistically appropriate testing where they're taking the large variety of sizes of hail, and they're impacting many more modules, and they're doing it at many more locations on the module. So you get a much better characterization of how that module is going to behave in the field.
That's actually a really good one. Think about all the things we've talked about size distributions of hail. It plays an industry role for somebody like John and these large scale photovoltaic farms that have to evaluate that. So I'm going to turn now to Chris, and then we're going to get to some audience questions after Chris. Chris, you are at IBHS and you work with me, but you serve as our staff liaison on our emerging technologies subcommittee that's made up of our membership. What are you seeing out there that we've done and looked at in terms of emerging roofing products that could be a future path for hail resilience, or maybe we have some serious concerns about making sure that maybe they aren't as resilient to this hazard that we've been talking about for 2 days?
Yeah, so some of the products that we've started shifting to testing are just some of the newer products that are coming out there on the market. One of those products is called F-Wave. It's a synthetic composite shingle that installs just like a traditional asphalt shingle. So your roofer doesn't really have to learn anything with that new technology. But they're very thick shingles, and they offer a very specific hail warranty instead of just an impact resistant warranty. And from the testing that we've done in our lab, they performed very well. And in fact, they even came back and said, well, have you looked at the potential for it to actually heal over time? And so we then put it outside and reevaluated the damage that did occur and found that it was actually reduced. The dent that occurred just kind of healed itself a little bit. So.
Yeah, I would encourage folks also to check out Chris's poster or later this morning that some impact work on some of the new metal systems that have granule coatings on them. All right, so we're going to open things up to audience questions. So if you have a question, let's start there. And anyone in the virtual space, please use the hand raise function and unmute yourself. I'll try to keep an eye on that. So let's see if we have any audience questions out there for our panelists. Amanda, I'll see you back there.
It's for the Owen, I'm sorry, I forgot your name, but Owens Corning. So I have a claims background. I'm now in corporate underwriting, but I've done a lot with shingles, and we always looked at shingles and say it's 20-year shingles, 25-year shingles, a 30, a 40, a 50. Has the industry ever looked at changing those lifespans based on geography? Because certain areas of the country that are more sun exposed, that shingle's still going to wear faster than somewhere that's not?
Yeah, so I try to stay away from talking about warranty in a public forum, but I can say that warranty is all about the level of risk that we're willing to accept. Right. And it's largely a competitive portion of our product line. It would be much like offering a regional shingle that has high wind resistance that we would sell in the Southeast and low wind resistance that we'd sell in the Northwest. From a logistical standpoint, it would be very, very difficult to have different levels of warranty coverage for different geographical areas of the country. It just would be very prohibitive. It would get very difficult. It's already hard enough to deal with those issues, but then when you exponentially expand that to geographical restraints, it would just be very difficult to do. Thank you.
More questions? Anyone out there on our virtual attendee side? I know it's early, y'all. Come on. Oh, got one over there. There we go. And I do have some more in my head. So.
Hey, so cool. I mean, it's a neat panel. So I'm thinking the number of talks between the first day and today that have involved mesh and hail size and things like that. Is the scientific community solving the right problem? Because I haven't heard you guys talk too much about mesh and hail size. It's been about damage and impact. What problem should we solve?
So I'm kind of looking there toward, Robert, you use these products. I know Emily, you do. Chris, you know me talking about them, but I'll start with Emily and then we'll go to Robert about using some of the radar information.
I think that's a really good question, and something that I think is important to bring up in this audience with a lot of different representation from academia, industry, all over the place. And what I've been kind of struck by during this workshop is, I don't mean this in a negative way, but I think that there may still be a gap between the two communities and what we care about from, I'm speaking from the insurance perspective and, the hardcore academic research that's happening. And that very much needs to continue to happen, right? It's very important. We need to know these scientific things that underpin so much of what is happening in the atmosphere. But sometimes when you kind of boil it all down, what we care about is actual impacts. And like I mentioned, it might be a little controversial, but the hail size, all these specifics of hail often doesn't come through in our claims loss history. I was actually just speaking with some claims folks at Liberty Mutual, and it's almost like this exasperation, like it is so impacted by human elements. And I was actually speaking to some colleagues last night about this. I think someone posed the question from the academic side, what should we care about? Tell us what we should do. And I would also kind of add, at the same time, we do look to the scientists to help us understand what's most correlated with claims loss. That's something that you could definitely help us with. And once we know those parameters, whatever it is, then we can kind of have this partnership. But there is maybe a little bit of disconnect, and that's why we're all here at this workshop, to maybe close that gap a bit. But I think that's a really excellent thing to call out.
Robert, using weather data and things like that.
Yeah, when I first got involved in this, I realized that I asked a question about terminal velocity, but then after going down that pathway, date of loss is a big thing, trying to determine the date of loss. And it's a big problem for hail. It's not such a big problem for hurricanes or tornadoes, but there's typically a lot of events in different parts of the country. I typically look at the severe events database. I'll look at the ASOS, the closest airports, to get an idea of the winds, and then I'll look at the SWDI. I actually wrote a little program called Weather Strike to put it all together, but the golden standard of all of this in my mind is the damages I actually see when I get up on the roof and look at it, and I look at directionality. Some of the stuff that I'd like to see a little bit more on the melting layer. I know Andy wrote a 1987 paper. I'd like to see, hail of certain size. If I see it with radar, what will it be when it hits the ground? The other thing I'd like to see is the size of hail and it's how far it can fall. 1 inch hail at 15 or 20,000 feet versus 3 inch hail. And I think the bigger it is, intuitively, it doesn't fall as far, So I'd like to see something like that put out there because I'm trying to link the event to the damages that I see on a roof. And I try to pinpoint it, and I try to use all the best tools I can. And sometimes at the end of the day, I throw my hands up. I do go and I look at maintenance records. I look at Google Earth. I do interviews with people and talk to them, maintenance guys and stuff like that. If they have reports and they refinanced it and somebody got up on the roof and did a report, trying to find a benchmark in time to lower the window of when an event actually happened. But that's what I like to see.
Yeah. So in the last, John, hang on just a second. Let me see if there's any questions out there in the virtual space, and then we'll turn to some final thoughts from you guys. Make sure we get our virtual attendees included. Any questions out there from our folks on the Zoom box? Oh, they got a hand raised there. I think that's Sarah Corfidi. Sarah, if you can unmute yourself, ask your question, please.
Yes, thanks. I just have a question about what can homeowners or property owners do to kind of help themselves to get their claims covered when they are. Because just from my perspective, we've been in Oklahoma living here for almost 25 years. And so we have hail pretty much every year, every season. And we've had a couple of roofs replaced. And it always is a pain, you know, with the insurance companies, because you have to prove that there was a hailstorm, you have to prove the date. But my question really is, since we get so many hailstorms, we can't get up on the roof and evaluate the damage. Is it worth hiring a forensic engineer or somebody, a roofer even? I mean, but a roofer has a biased opinion, but is it worth hiring somebody to come up after every year, for example, to kind of evaluate how your roof is bearing?
That is one of the great questions that I get to sit right in the middle of at IBHS. And so does Chris, and so does Brennan, Lucas up there. Anyone want to take it? I mean, I kind of guess, I know Robert will say, yeah, you know, that's his job. And
you got guys on both sides, so it's not just one side that's going to do it.
Yeah, I'm going to look kind of down the, you know, Emily, from the insurance side. I know there's a lot of work trying to help streamline that process, but I will say from an industry perspective, I think we're behind.
It is really hard to streamline that process. And I did want to maybe mention that some people are turning to the opportunities of parametric insurance. And if you're not familiar with parametric products, they're slightly different than a normal insurance policy, right? You think of a normal policy as being triggered by whatever is being covered when damage occurs. The insurer then pays out according to that damage. But parametrics maybe alleviate some of that in between kind of fuzziness. And the way parametrics work is that they're triggered, the payout is triggered by a certain threshold being met or a certain event happening. So in the case of hail, it would be if a hail event occurred in that region, a policy would then automatically pay out. These are used in other types of perils. You know, you'll hear them about like hurricane parametrics, et cetera. But it could maybe be an opportunity for the industry to alleviate some of the complications in the in-between.
Yeah. So in our last minute or so, Sarah, that was a wonderful question. Thank you.
Thank you.
I'll turn to, all right, thank you. And I'll turn to John and Greg for your final thoughts here in the last 2 minutes. I know John was going to jump in there. So John, you go first, and then we'll hit our, Greg, I'll let you wrap it up.
Yeah, I think I'll try to be quick. In summary, when people are considering making, billion-dollar investments in these areas that are at risk, then it's like any business decision. First thing you need to do is assess the risk, and that's a tool that John and we have developed, is assessing the actual probability of risk. So the science community can definitely help out in trying to forecast what's projected going forward. Then once you make that risk assessment, then you need to determine optimal ways of mitigating. And fortunately, we have ways of mitigating, significant mitigation. And then, just for example, you can tilt solar arrays. So unlike a building, we can reconfigure our physical characteristics to optimally mitigate against an event. And then finally, you need to understand what the financial impact is. And so one of the things that we spend a lot of time in doing is analyzing the probable maximum loss and the average annual loss associated with hail. And it's unique for our industry in that we're doing it with a science and technology bottoms up analysis, which is different than approach typically taken by insurance companies. And parametric insurance is something that our industry is definitely looking at.
Well, thank you, John. Greg.
Yeah, so the last thing that I would like to close with is solving the hail damage issue with asphalt roofing is about manufacturers and researchers collaborating and cooperating. It's all about the pipeline of information coming into the manufacturers so that we know what we need to do to our products to make them better so that they're more resilient against hail impacts.
All right. Thank you, everyone. Let's thank our panelists for another good panel discussion. Thank you all. And thank all of you for some good questions, including both from here on site and on our virtual space. So we will now move into our more technical session discussions. Again, thank you guys. You can step down. Robert will stay with us as the session chair. I guess I get to stay up here and talk some more with Dwayne Sloan from Underwriters Laboratory. So some of the things Greg just finished us up with, we're going to touch on and continue on that theme in our damage session. All right. Well, Dwayne, I can let you kick us off. And start us off. And we've had a couple clicker issues, so we'll just bear with us. If Kelvin back in the back needs to advance our slides, no, they can do that.
Okay, wonderful. Well, good morning, everybody. My name is Dwayne Sloan. I'm with UL Solutions, and I think this is a great follow-up to the wonderful panel session that we just had this morning. So we're going to be here to talk to you today about mitigating hail damage and insurance losses, but really focusing on the role of understanding laboratory testing and certification and evaluation programs that can be used sort of as a tool to help in mitigating that process. So I'm glad to join Ian here, and we're going to go through quickly. Again, I'm Dwayne Sloan. I'm the technical director of built environment at UL, and you can see some of the things I've gotten into, but I've enjoyed working with the roofing industry. I've been working with the roofing industry for about the last 15 to 20 years. We're working with IBHS as well. UL is a testing, inspection, and certification organization, and we also write standards. Ian?
Yeah, so there's me. A lot of you know me, but if you don't, I am a research meteorologist at IBHS, but I'm also our senior director for standards and analytics. So I directly work with this. I need to give a big shout out to my wife, Tanya, who actually started and really drove this program that Dwayne and I are going to talk about today forward. And that includes our ability to assess damage, rate products, things like that. So I wanted to give Tanya a big shout out. I don't know if she's on the Zoom call there, but she started this effort and led it all the way to its finish, and I get to talk about the fun stuff. So.
Great. Okay, so today we'll go through the impact history of 2218, which is our test standard, science that led to new hailstone testing, the overview of the IBHS protocol that you're starting to hear about, differences between that protocol and the current standards that we have, and then this performance rating program that Ian has mentioned a few times, and UL's role in that. Okay. So UL Solutions and IBHS kind of found that we had some really great synergies. We do a lot of large-scale fire testing. We have a really close knit with the building community and the fire inspection community and the code officials and what have you. And then you've got the big IBHS facility there in South Carolina. I actually reside in North Carolina, and it was just a really nice union. So we actually formed this memorandum of understanding back in 2015 so that we could work more closely together. And when it comes to roofing products, we kind of felt like UL has been a pioneer in the whole idea of laboratory testing. Our lab testing goes back to the 1900s, literally, in fire testing of roofing products. There, I've got a Sears and Roebuck catalog around 1918, where they're actually talking about we're approved by Underwriters Laboratories. That was a huge thing back then, and it still is now today. We still have our UL 790 that was first published in 1958, and so UL and roofing, we go all the way back to the olden days of 1900s, and so it was sort of a natural evolution for UL to kind of move beyond fire testing to get into wind testing damage and what have you, as well as hail damage. Certainly, as you heard many times, annual losses routinely exceed $10 billion a year, and damage from a single hailstorm hitting a big city can reach $1 billion just alone, right? And you've heard a lot of statistics here at this forum. So around the mid-1990s, insurance companies approached UL and with concern over hail damage. It started with asphalt shingles, very specifically in the severe hail belts such as Texas, Oklahoma, and Kansas and Colorado. And working with them, we started testing, believe it or not, we actually started with ice balls, but we really couldn't hone in on the ice balls and could not get the results back then that aligned with the hail damage that we were seeing in the field. And so we reverted from ice balls and went to a steel ball test method. And so that steel ball test method is UL 2218. It has been the industry standard in testing roofing products for impact for many, many years. We work with State Farm, who sponsored the program for steel balls. We used the impact energies from Laurie that you've heard about here. And then in May of 1996, that's when we published 2218. It was limited to asphalt shingles, and then later we opened it up to other shingle types. So here's how it works. It's, you'll hear about class 1, 2, 3, and 4. And basically the class 1, 2, 3, and 4 kind of relates to the ball diameter, starting with 1 1/4 up to 2 inches. And then it also relates to the drop size. You just heard on the panel that the drop actually really relates to the impact energies that you're going to get with a hailstone or what have you. So these impact energies related to what we saw from Laurie, and we designed this so that you would have the size, the weight, and the drop in order to achieve these impact energies. And this is how you achieve the class 1, 2, 3, and 4 in 2218. So the class 1 is about a Kennedy 50 cent. Class 2 is your ping pong ball. 3 is a golf ball, and 4 is like a hen egg size or something like that. All right. So when we do this test, it's 2 coincident drops. You choose 6 of the most vulnerable locations, and those locations are your edges, your corners, your unsupported areas, your overlaps, and your joints on a panel, on a test panel. Okay. And the acceptance criteria that has been in place for many, many years is basically looking for any evidence of your damage, like tearing, fracturing, cracking, splitting, rupture, crazing. We look at it under 5 times magnification. But as you heard in the first panel, sometimes there's a disconnect between what we see as standardized testing and the testing that would actually lead to an insurance claim. And so many years, I get the phone call to say, well, what about aesthetic damage? What about granule loss? And that has never been a part of this standardized test that's been in place since the 1990s. So if you have aesthetic damage, that is not considered a failure in this UL 2218 test. We were really looking at the type of damage like cracking and tearing that would actually let the water damage come through. All right. So we had some changes that happened in 2020. We changed from a 6-inch mandrel to a 6-inch mandrel versus a 4-inch mandrel, just so that you're not breaking and cracking the shingle just by bending it over a mandrel to look at that damage. And then we actually also made some changes relative to not necessarily focusing in on a visible crack on the back side of the shingle. It used to be that you would turn it over a mandrel and look for a crack on the back side, but our current standard was kind of tweaking that and trying to make it more consistent with the damage that you would look at for other shingles or other roofing products, just not asphalt shingles. So there's been a lot of discussion about that change. There's a discussion on whether we should change it back to the way we've been doing it since the 1990s, but we have some ballot activity that's going on right now today over exactly what you're looking at for the acceptance criteria in 2218. All right. But once we get through a testing, a successful test, then I wanted to make sure that everyone knows that it doesn't stop there with UL. What we do is we put it under what we call a third-party certification program. We literally go in and knock on the door, over at the shingle manufacturer's location, and we say, hey, the UL pan is here, and we're going to go through and make sure that that product is made the same way as it was originally submitted to UL and tested, to make sure that it complies with all of our testing. So it's not just tested one time. There's this ongoing relationship with the manufacturer to make sure that they're continuing to make the product the same way. Okay, so those periodic inspections, we know all of the secret sources of what's in this SBS, modified formulations to scrim. We know all of that, and we're looking for that to maintain their listing with UL. All right. And all of that information, like if you wanted to see which manufacturer set of cleat had achieved class 1, 2, 3, and 4, is on a website. It's called ul.com Product IQ. And there's no charge to get on it. You do have to register, but you can get on there and, give me a call, give me a shout, and I can walk you through exactly how you get to this category of the whole list of those that are qualified for 2218. Insurance companies use this readily. Some of them even use it in order to give certain rebates and what have you, if you actually have impact rated shingles. All right. So with that, I'm going to turn it over to Ian so he can share with you how we took some of this where we were and drove it into some new science.
Yeah, thanks, Dwayne. So what our role was to try to build upon what had already been done in the industry. And as science really increases our ability to do some of these new applications, was bring that to bear on the performance problem. How can we assess damage How can we actually look at the spectrum of performance? As Dwayne mentioned, they look at it from a classification perspective, a pass-fail. So we knew we wanted to kind of push the envelope. How can new science be brought to bear with this problem? So we've done Dwayne's test. We actually helped you guys with some data, and I know it changed how you guys worked your surveillance of factories. And then we started into what would it look like to come up with a new testing standard. And for IBHS, this was the first time we ever delved into the public release of a ratings program where we actually showed shingles by name and what their performance were. So we took the ones rated essentially class 3 and 4 from Dwayne's program and put them into our protocol that I'm going to talk a little bit about. So part of that was, well, what do we got to go learn about hailstones, hailstorms in the field to engineer a laboratory test? We're not necessarily worried about making a hailstone the same way a supercell may do that, but we want to engineer the outcome of our ice to match what's out there in the real world. Well, at some point, you hear in the literature, everybody talks about hard hail, slushy hail, but there was zero quantitative data, none. So how do you do that? Well, the engineering world's had material test programs for everything. Why can't we take that for hail? So I actually went out there and actually crushed hailstones, looked at the amount of force it takes to fracture them, scale that by their cross-sectional area, and do the engineering work to figure out what we have to replicate in the lab. Same was with density. We kind of give Andy a little nod. Back when you guys did density, you were dunking stones in liquid mercury to get density. Well, we're not doing that in the field anymore. So we had to figure out how to do that. And 3D scanning was a way. I had somebody tell me I wanted a toy when I wanted a 3D scanner, but think about all the things you guys have seen, the use of that data. And then just making simple measurements of hail. Like when Andy came and ran up to me after giving a talk and just showing all these different measurements, revisiting the hail problem. And so we took all that information back to the lab and figured out how do we engineer this. So a little bit about our field program. Many of you have used the data. Again, if you want to use our data, please come talk to me and I'm happy to share it in the research space. But just to look at what we've done in the field. We were able to update the kinetic energy curves. That's the paper that Andy, Robert, and I worked on back in 2014. We've updated that again in 2018. That will go into the next iteration of our standard at some point. Looking at the size mass curves and then the compressive strength. How strong are hailstones? And it turns out that actually matters when it comes down to damage on asphalt shingles. So there's a little video there. I don't know if it'll actually play. And I might have Kelvin actually just some photos of us in the field. That's me with no facial hair. And that's Brian right there from his time in the field, looking over my shoulder, me looking very, very perplexed there. But one of it was to how do we, let's start with kinetic energy. Let's use the new data. Let's use better curves from some of the Laurie work. And if you ever talk to Andy and Robert about the story behind some of those curves, and it's rude, we presented it last time. It's a crazy one. So talk to those guys about how some of those original kinetic energy curves actually came about. But how do we take all this information we've gained in the field and apply it to developing a new test protocol? So some of the things we learned, natural hail as a distribution is slightly stronger in its mean sense than pure ice that you'd pull out of your freezer. There's a wide range of that. The strongest stone, I'll use just English measurements in our database, it took 6,000 PSI to fracture. What's in your car tire, like 32? That's big. That's very strong. That's a very strong piece of ice. Trying to understand the mass element. So, people had moved to ice ball testing, as Dwayne mentioned, and it was really hard to get a consistent pure ice sphere. Each one was different. So how do we make sure our impact number 48 is the same as number 212? Dwayne knew that was a problem back when they developed their program, and that's why it was one of the big challenges in developing an ice-based test. And then also to understand those kinetic energy curves. So we had a little bit of changes there. I actually backed off some of the impact energies when you looked at the distributions there. So taking all these field measurements and actually applying them to engineering. Now, as we tried to figure out how to make the most sophisticated ice machine on the planet, there was one of those, hey, that's weird moments when we did some ice cross sections, and we actually generated some of the similar layering structure. And it is a completely different process than what's going on in a supercell. But we engineered the thing. And I remember I started calling, I think I called Matt, I called my old cloud physics professor. I'm like, what in the Sam is going on, because this is not the same process. But what you ended up with is a consistent ice sphere that matched strength and density, and we could turn the knobs on it. So we were able to actually run through that. And what that kind of distribution in terms of strength looks like, we knew we had to match and put some lines and percentiles to make that standard. And that's kind of where we did. We took all this field data that we collected and figured out how to match it in the lab. So what strength does in terms of impacts, that video is not going to play. I was hoping it would. I showed it in my poster talk. You saw a little bit of that. There's different impact modes. You have a hard bounce impact. That's a very strong hailstone that will bounce off something. Think about those hailstones you see on YouTube bouncing off of asphalt. That. The next one was a shatter, where you get kind of that middle of the ground kind of mean strength, where it shatters into a whole lot of pieces. There's no piece of ice left that could support a load. And then lastly is a very slushy impact, which you hear in the literature a lot. Charlie Knight was one of the ones who talked about slushy hail, what's real, and it's very soft stones that kind of leave a snow cone looking residue. There's kind of the graphic that goes with it, just to see what happens when we use a high-speed camera to capture some of those impacts. So the soft modes are on the top, getting down to the hard bounce, which simply just bounces off the shingle. It's very good at cracking them. So we took all this information, went through impact configuration, the hailstone characteristics, and tried to assess damage. So I'm kind of hum through this a little bit. So we used two sizes of stone, 1.5 inch and 2 inch. So that's the same diameter as Dwayne's 2218 test. We actually take our products from the distribution chain, but we also use the same test setup and panel configuration as what Dwayne does in the 2218. So we're building upon what they had done before and use some of the same test conditions that were required. We're not reinventing the wheel. They've done a lot of work. Why would we change that? And then actually have a hail cannon I mentioned yesterday. It's a lot of fun if you're having a bad day to go shoot some ice at things. So there's kind of the impact configuration. We do multiple impacts across the panel. And then we actually rate 3 different types of damage. And this is what we're getting out of the pass fail. We look at cracks, we look at the granule loss problem, we also look at the dents. And we use a machine vision system to actually stitch together a 3-dimensional model to quantitatively give us those values. Now we had to look at what was damaged, and we did some water penetration testing to be able to draw the lines. This is the one human element that comes in, is where do you draw the lines in your quantitative data as to what is bad, what is good, what is sufficient. So we put it on a weighted scale, which enabled us to take all this information that we get from machine vision and turn it into a rating system. So we can assign big dents, small dents, look at cracks and tears and how much granule loss is there, all by taking a series of 9 images around that impact, and it stitches together, and we have an automated system. So there's some comparisons between the 2218 program versus the IBHS one. And like I mentioned, we built upon what the UL program was, taking the class 3 and 4 products, which are going to be the top of that heap, and putting them through to look at relative performance. Chris Sanders, his posters on using the same protocol for other materials. So that's where kind of we're going from that perspective. There's just some more test comparisons with some of the other tests to look at energy versus the classification system, and some of those as we kind of work through the other test that's out there, which is an FM test, which is a pure ice sphere test. But I know we're short on time, so I'm kind of humming along through. There's our performance rating system. I see Robert in the front giving me the "you need to stop talking" kind of sign, and I'm the one who got us off the rails in 2018, so I'll try not to do it again. But that's what you get, is a sheet that looks like that. And if you go on our website or just Google IBHS shingle ratings, you will see a graphic that has the manufacturer and its scores. And we have the overall rating, the ridge, dent score, the tear score, and the granule loss score. And Brenna's going to cover a little bit about granule loss in her talk next. But it's an objective way to get quantitative damage information in a lab setting. It's not for use in the field, nor will this system work in the field to do this. We haven't got that far. But there's the website. You can see it. It's been a wonderful partnership with Dwayne. I've known you now for, going on 8+ years as we've started this. And I was happy to be able to do the talk with Dwayne today. And with that, we will go ahead and wrap it up. And Dwayne, I'll open it up to you if you have any final thoughts as we kind of close out our our piece.
Right. Yeah. So as we wrap it up, basically the needs of the industry is the shingle manufacturers needed a way to conduct these experiments under developmental. They're wanting to make a better product. As Greg mentioned, they want to just make a better product. And so UL is actually going to come in and be able to perform that developmental testing even before they ever get to IBHS and actually qualify for the actual rating program. And so we're glad to be a part of that. And if anybody has any other questions about how we work together, please let me know. And okay, sure.
Okay, yes.
So, and then you've got the wind driving through. That increases the water, which is again increases the wind.
So, Mike, please.
What do we do for that?
So on ours, we actually put a bound on it in acceptable test. So we used the standard surface pressure, 1019 millibars. That's what ours is based off of. So we run that curve. But the one nice thing about the work we did is you can actually make that adjustment. And we've done some work looking at kinetic energies for a place like here, which is at higher elevation, and what that looks like in a relative sense compared to, say, an 1.5 inch test there may actually be more representative of, say, an 1.25 inch hailstone here because of the sea level density change and those faster energies. But we put some bounds on that. The test itself is not, you don't have to get to the hundredth of a kind of significant digit there, but we do account for that. And same for strength, we had to put a bound on it very quickly. Yeah.
Can I go? Oh, sorry. Can you hear me? I don't know.
Yes.
So my quick question is, you have the UL standard, and I know I'm an insurance company, and I know a lot of people, they'll give like impact resistant discounts for things like that. And I know IBHS, you've done all these studies. And I know you have like IBHS Gold and all those things. Are you doing anything for impact resistant so that like insurance companies, you say IBHS certification, right, for hail roofs?
So for us, the stamp that's labeled on the product is the UL approvals.
Right.
IBHS does not do that. However, you mentioned our fortified home program. To qualify for a fortified wind and hail roof, you have to be a good or excellent performer on our ratings, which also means you are a class 3 or class 4 UL impact rated product, and you are in our good and excellent performer category. I think that's Charles there on the virtual side that's got a question. So go ahead real quickly.
So I guess the premise of making hail is that there's not an equivalence between steel kinetic energy and ice kinetic energy. But in the end, isn't it just kinetic energy, and that's what causes the damage? Can you better clarify why hail kinetic energy is different than steel?
Right. Yeah. You're exactly right. The kinetic energy is the same. Okay. But what we've learned is that the response of the roofing product is different, whether you hit it with steel or whether you hit it with an ice ball, and whether that ice ball is a hard ice ball or whether it's one that will shatter or whether it's one that will be slushy. So you're exactly right. The kinetic energy is exactly the same, but the roofing response is different. And so that's why we wanted to recognize that. And then also what Ian was mentioned is that the IBHS protocol does take into account the type of damage that would be more along the type of damage that an insurance adjuster or claims adjuster would actually note as being a replacement. So it does take into account granule loss and some of those other more aesthetic things that 2218 does not take into account.
Yeah, thanks, Charles. That's a good question. So the material properties of both the hail and the material it's hitting do matter. And this is just science catching up. That's all this is. And Brenna's going to hit this too in her talk coming up. Robert, do you think we need to move on, or we got one more question here? Or? I'm the one who got us off the rails in 2018. Oh dear. All right, very quick.
A quick question for Dwayne. What was the motivation for removing testing the backside of the shingle for cracks? Isn't that where you'd expect to find tensile cracks when you have impact on the top?
Absolutely, it is. And of course, first of all, the standard is governed by a standards technical panel. It's not just a UL standard. It's not just UL's voice. It is a consensus-based standard with manufacturers, code officials, and what have you. One of the issues was that looking at the back of the shingle was only there for asphalt shingles. For other type of shingle types, it was only looking at the surface. And so there was discussion with the standards technical panel that they did not want to single out the shingles that were asphalt only. And so basically they felt that looking at the back of the shingle was singling out the asphalt shingle. And so they wanted to just look at a through penetration crack. And so that was one of the
The
changes.
asphalt shingles now getting a free ride.
Well, right now with this change, it was an unwanted consequence, if you will. And so I actually have, I actually have a ballot out right now that is going to revert it back to the old way. Okay. And we're going to see how that works out. But I had to, all transparency, the exact 2218 that we're working with right now does have this change in it. But I also have a proposal to send it back to the way that we've been doing it since 1990.
Great. Thank you very much.
Okay. Thank you for that question.
All right. Sorry to run us off the rails, but well done. It's good to see you.
Okay, you too. Okay, thank you.
Good morning, everybody. My name is Brenna Meisenstahl. I'm one of the research scientists at IBHS, and I'm going to talk to you about high concentration.
In here.
Oh, sorry. I'm Brenna Meisenstahl. I'm one of the research scientists at IBHS. I'm going to talk to you about impact testing of high concentration of small hail on asphalt shingles. A little bit is going to kind of repeat what Ian just talked about, but let's go ahead and get started. So another term for this, snowplow hail, typically produces subsevere to marginal severe hail sizes. So we were looking at hail 1 inch and 3/4 of an inch size. Those are the two that we used. And it could seem harmless. Losing granules, we're not sure. We're trying to understand if it causes long-term damage. So it may not look like there's damage on a roof, so you may not get your roof replaced, but it could end up causing some long-term damage, and those effects haven't been studied yet. I'm actually going to go. Okay, these were 2 videos and they're not going to play. But those were 2 videos from our field deployments. One of them, I believe, was in 2016, and it was just kind of showing a distrometer placement and hail falling on it, about 1 inch to 1.5 inches, I believe. And then a second video was from last June, in Williston, South Dakota, where we had a lot of wind-driven hail. I believe the weather station or the airport nearby reported wind gusts around 83 miles an hour. And we actually had to kind of go into a self-service car wash to kind of keep ourselves safe and our vehicles safe. But it was kind of cool to sit there and watch it. But this is from one of our impact distrometers. This was from 2018 in Texas, and our this distrometer caught about 900 impacts on square inch within 10 minutes. So that's a lot of impacts within a short period of time, and just on 1 square foot. This is the second one from last year. This was about 10,000 impacts in 20 minutes, again, on 1 square foot. So imagine your entire roof. That is hundreds of thousands of hailstones within 20 minutes on your roof. And again, these are small, maybe about 1 inch or so. So these are pretty small hailstones. Oh, actually, okay, it does come up. I'm not going to play it though. Okay, so again, our main objectives investigate into whether large quantities of small hail could lead to notable granule loss on asphalt shingles. Kind of 3 things we want to understand. Can the products hang on to granules over time? Do products perform worse over time after small hail events? So do they, well, kind of going to the third objective, do impacts from large quantities of small hail make larger hail events worse for shingle performance? And that's kind of something that we looked into. So our test plan was we had 12 panels, 6 different products, was to age. We had an experimental group and a controlled group. The experimental group went out into our aging farm. They aged for 1 year. The controlled group was stored in our facility, also for a year. We impacted the products with 500 small hailstones, which, going back to the cases that we had in the field, this is a very mild case. We repeated this process again. So we let the We let the products age for a year or get stored for a year. And then we impacted them a second time with 500 more hailstones. And then we ran the products through the IBHS test protocol just using the 2-inch hailstones. And we had a couple machine vision algorithms that we ran the products through, or are currently actually running them through right now, to analyze this granular loss and analyze the damage. So test specimens, like I mentioned, we had 12 of them, 6 different manufacturers, had a few impact resistant and also a few non-impact resistant panels. We wanted to see if maybe there was a difference between the two, if non-impact resistant panels did perform worse than impact resistant panels. Included standard shingles. We had 3-tab shingles. Shingle color was not, I've gotten that question before, shingle color was not really anything that we considered. And again, these products were chosen based on their market share. We wanted products that are on a lot of homes. And these were large test panels that we used. So this is an image of these 6 current panels that we actually have out on our aging farm at IBHS. And for those that don't know, our aging farm is where we have huts that they're kind of look like that, but they just age our, we let our shingles sit out there and age there in 5-year increments. So every 5 years, there's a section of them that gets pulled, and we do hail, wind, and wildfire testing on them, 10 years, 15 years, and 20 years. We just let them sit out there and naturally weather. We actually have a couple across the country as well to understand how shingles react in different environments after a long period of time. So again, we had our experimental group, 6 panels that naturally weathered at our aging farm in South Carolina, and then a controlled group that was sitting in our IBHS lab facility. So one of the things we needed to understand was how to quantify granule loss, and you can't always see it. So while some granules on shingles sometimes you can see the damage, it's not a practical way to, you can't count every single granule that was lost on a shingle. So our solution was using an image processing algorithm to assess the granules by comparing pre-impact and post-impact photos. So how we did that, we created a custom photo rig. This was to ensure consistency. Some of the photos were not as consistent, but we used this to take pre and post-impact photos. We had controlled lighting. We had 4 LED lights, blackout curtains to keep away any shadows. And then we had some 3D printed molds on each. We had to split the panels into 4 quadrants, which you can see in that top photo, because of the placement of the camera, which was 3 feet above the shingle itself. Above the panel itself, we couldn't see the entire panel. So we split the panel into 4 quadrants. And then there were 3D molds for the Sony point and shoot camera that we used, so that the camera sat in the same position each and every time. There was a little bit of wiggling here and there, but that was adjusted in the algorithm. And then we also use these grids. So the algorithm used the grids to kind of as like points of contact, pretty much between the 2 pictures. And those grids were also helped to compute the granule loss, which I'll explain in a later slide. And then the production of the small hail. So we actually didn't use our large hail machine, which Ian had just talked about. That's generally what we use for impacts. But we don't have molds for that machine for small enough hail that we were trying to use. So we actually got some molds off Amazon. And again, like I mentioned, we use the 1-inch and 3/4-inch molds. We try to keep the stones as spherical as possible. Any ice with large chunks missing were tossed. And we just stored them in our freezer until we needed to use them. So small hail impacts, we do have cannon barrels that we manufactured for small enough hail. We subjected the panels to 500 random hailstone impacts. So they were hit wherever. I know for our standard, there's specific areas of the panel where you can and cannot impact. But this, we shot wherever we wanted to. It was random. So 200 of those, approximately 200 of those were 1-inch impacts, and approximately 300 of those were the roughly 3/4 inch hailstones. And again, this entire process was repeated. So panels were placed out in the aging farm and they were stored. Pre and post photos were taken again, and then 500 hailstone impacts. So like I'd mentioned, we impacted the panels twice with 500 hailstones, and then we impacted the panels with 2-inch hail following our IBHS test protocol. Again, Ian just went over this, but this test protocol is to determine the performance of asphalt shingles based on 3 factors: dense ridges and tears and granule loss. And then they were either considered poor products, marginal, good, or excellent. And another repeat. Again, this just explains how we went through the test protocol. Again, we used 2-inch hailstones, 20 impacts, depending on if it was a 3-type shingle or an architectural shingle, was 40 impacts, because you have single ply and double ply. So you have to double that. And then you have each of the impact modes: hard shatter, hard bounce, and soft. Again, these are just images to explain what the hard bounce, hard shatter, and what soft impacts are. And then we get into the machine vision process. So we uploaded the pre and post images into MATLAB. That's the programming language that we used. MATLAB has this registration estimator toolbox, which overlays the 2 images based on kind of points of contact between the 2. That's what all those little green dots are. We use the pre-image as the fixed image, and then the post image as kind of the moving one that is adjusted to fit the fixed image. And this is the resulting image you get after the registration toolbox. All the red dots, yeah, I was thinking it might be hard to see, but all the little red dots that you see are hailstone impacts, and those are differences between the 2 photos. So those are the granule loss. That's the granule loss that we're trying to quantify. You have a little bit of red around the edges, and that is just cropped out because of the moving photo. Like I mentioned, sometimes the camera isn't placed exactly where it should be between pre and post photos. So that's accounted for here. We just crop that out. And this is just zoomed in to the grid kind of on the top left. We use that to determine the number of pixels that are in the image, which we can in turn get the area in inches squared of the number of granules that were lost on each panel. So second tool that we use is the color threshold. This gives us a numerical number of the pixels or the missing granules between the photos. So we have to take this kind of yellow image and remove all of the colors inside of it except for red. Red is the only thing that we want. So this is kind of a little tedious process. A lot of times I like to have the post image on my computer so I can visually see what it looks like, or I will go out to our lab where the panel is stored and look at it in person to make sure that I'm adjusting the color threshold correctly and I'm not missing any granules, or I'm not adding granule loss, I guess, that's not actually there. So I have 2, couldn't see it. I know it's a little dark on the screen, but I've just circled a couple impacts that you can see. And then this is how we compute the total granule loss. So Q1, Q2, Q3, and Q4 are all the different quadrants of the single panel. Because like I mentioned, we couldn't, with where the camera was set up, we couldn't see the entire panel. So that ratio is it's just the area of the gridded squares. The number of pixels comes from the color threshold, and then we divide the pixels by the ratio, and we get the area in inches squared of the total granule loss on that quadrant, and then it's just added up as the total. So this is an example of kind of why we needed some sort of machine vision process. This panel, it's maybe not as easy to see up there, but I have them circled. So this with the naked eye, you can pretty clearly see granule loss. And in our machine vision, again, it's pretty clear. There were some spots on here that you may not be able to see, but this is one of those examples where you can actually see the granule loss. Here, you can't see any granule loss, but this has been impacted twice. So this has had about 1,000 hailstones on it. I don't believe that, no, this one was not impacted. This picture is not from after the 2-inch hailstones or the IBHS protocol, but this was impacted by 1,000 hailstones, yet you can't even tell. But when you look at the image from the color threshold from the machine vision algorithm, we do see some notable granule loss. So looking at kind of the non-aged panels, I have listed whether they were 3-tab, non-IR, and then their IBHS ranking, whether they were good, marginal, excellent, poor. I believe all we had for this project was marginal and good. We didn't do any of the poor. There may be an excellent in there. I'm not 100% sure. So number of granules lost per round of impact, it's not the total. So there was clearly granule loss after each and every impact. And I do want to note panels 1C was not tested for IBHS impact resistant protocol. The rest of them were. That's why it doesn't have a rating on there. Panel 3C, even though it is on homes today, it is no longer available for purchase. And then panel 4C, we kind of had an issue with our images in the first round of testing. So unfortunately, those were not analyzed. So that's why there's no blue column there for panel 4C. And then kind of going into the aged panels, we definitely see a difference from the IBHS test protocol, which is the gray between our non-aged and aged panels. So across the board, granule loss overall is increasing with age and weathering. Products seem to be more susceptible to damage from larger hail, especially with our aged panels, after small impacts, as opposed to those that were not weathered. But I would assume that the aged panels here are a little bit more important, since those were actually weathered for a year, 2 years. IBHS ranked good products have higher amounts of granule loss compared to some marginal products. So panel 6C and panel 2C are the two highest when it comes to the IBHS test protocol. Those are both ranked as good products. But as an example, panel 3C is a marginal product, and it has total less amount of granule loss even after that IBHS test protocol that it went through. And this is just an overall numerical view. The top numbers are in inches squared, and then we have the millimeters squared underneath. And our two worst panels for aged, again, are panel 2C and panel 6C, and both are, one is a non-IR, one is an IR, and both are rated as good performers with the IBHS test protocol. And this is just an example of what the better, I don't want to say good yet, but better performance. Again, this is an age panel. This is panel 4C. You can see some granule loss in the machine vision image. You can't really see it much at all. I can a little bit on the computer, but can't see it as much after it was impacted 3 times. And then we have one of the worst performing shingles. Again, it's another aged panel. Can clearly see where we have those patches of granule loss missing. And again, it has shown up in the machine vision image as well. So we didn't just want to analyze the granule loss using the machine vision algorithm. We also wanted to run it through our HIPS, which is also what Ian had talked about as well. That's what we run our shingles through after they've gone through the IBHS test protocol. So each of these shingles are individually cut off, placed on a turntable, and about 15 pictures taken of the image of the shingle all around, kind of keeping we use an iPad, so keeping your iPad or your phone at the same angle. Images were uploaded to our HIPS web application and processed through the algorithm. And again, HIPS detects and quantifies the depths of dents, ridging, tears on each impact. It also does calculate granule loss now too, and it can separate between singular granule loss and then patch granule loss, kind of what we saw on that worst performing shingle. And products numerical data and volume of dents. And those values correlate to our IBHS hail ranking. And this is currently where we are in testing, actually. I was hoping to have the results for you here, but we kind of went through a little hiccup with the HIPS program itself. We're working with the developers of it right now. It's kind of halted in the pre-processing. So the images are all uploaded, but it's not processing them right now. So I have no numerical data on any of the dents or tears, or even just confirming some of the granule loss numbers. I don't unfortunately have that yet. And that's really what we need. So kind of my final thoughts and next steps for this: exposure to high concentration of small hail events over a short period of time will at a minimum increase the potential for larger amounts of granule loss for large hail events. Dents and tear, again, the data from HIPS, that'll tell the real story between this testing and then the original baseline testing of the IBHS test protocol, and kind of used some of the products were the same. So in order to make that comparison, we need the rest of the data. We need to do a little bit more comparison between the products. And then we're also going into a next phase too, where we tested 6 products this time. We started actually aging 9 different products. So those are out on our aging farm right now, 9 of them, and then we have 9 of them stored. Those will actually be pulled in early next year, and then we'll start impacts on those ones as well. And with that, I'll take any questions. Yeah.
So I understand the part that's stored in the storage versus the weathering. Mm-hmm. As part of the shingles that were weathered, did you consider having a panel or a section of each panel that was never impacted, and then comparing that to have this was the natural granular loss due to weathering?
No, we actually didn't consider that.
Jamie Beagle here. I would just follow that. That was the question I had as well. So ultimately, for the insurance industry, I think the actionable piece of this is going to be to what extent does a distinct event cause damage versus enhance natural granular loss. That's probably beyond what you guys are doing, but just as I look at it from a claims perspective, it gets gets complicated there. Thank you.
Yeah, I will also mention there are some products on our aging farm right now that one of our researchers currently is trying to, we have a little gutter system on a few of the aging farm hubs. Off the top of my head, I don't know what products they are, but she is letting the granules naturally come off, and they're kind of falling at these little mesh baggies, and they're just counting them afterwards. So it kind of pertains to your question a bit of the quantity of granule loss that actually occurs just from natural weathering. So I know that we're doing that on a couple of the shingles that are on our aging farm.
When you are those panels that you have for aging, what direction are they facing? Are they facing like south north?
They're facing south. They're facing south, yeah. Our aging farm, the huts one side of them faces south, the other side faces north. But for these, they're not as large. They're large panels, but they're not as large as our huts. But we just have them facing south. I don't think there was any sort of scientific reason for that, to be honest. It was just, that's how they were placed.
Any more questions?
Good.
Thank you. I think Matt Phelps is next.
We'll give everybody a minute to make their way back in. There's a few folks out in the hall. A little bit about what we did here is I was retained by Sentinel Systems to do some testing on their digital or electronic Hailpad. And we made some modifications to it through the process. And I'm going to walk you through what it is we did and explain why we did the things that we did. Before we begin, I would like to thank our sponsors, and I would especially like to thank our international guest for being here. Your presence here is very important for our entire industry, and I would like to personally thank you for your attendance. So we started out with using a single accelerometer. It is a 3-axis accelerometer. There's the brand. I don't read the slides. Y'all can read that for yourselves. But one of the things that we realized is that since we have a 3-axis accelerometer, we can measure the response to forces in both the horizontal and the vertical. And this gave us a new idea. And that is that these would be effective for both hail impacts, but also for measuring seismic forces. And since the Sentinel unit is mounted to the roof of a building, it's actually giving you the structure's response to an applied seismic force. And we did some testing on a shake table to confirm that it would read in the X, Y, and Z axes all simultaneously. And the accelerometer performed quite well. Also, the system has a telemetry system that allows it to communicate in real time and can provide notifications of time-critical information. So the system has a clear polycarbonate lens. On the underside of it, you see we have a solar panel, a battery. There's a Arduino processor that includes a cell phone system and an SD memory card. And then, of course, the accelerometer located in the center of the unit. Here are 3 units that were tested here at this facility, out in the parking lot in the back. And this illustrates that the units can be used as a single node for maybe a single owner or a group of buildings. And it also can cover a network that can cover larger areas, even entire states. So this is just a system layout and operation concept. The red dots are where all the Sentinel units might conceivably be located. And that their telemetry system allows them to report immediately, or they can report packets of information later in the day. The unit will report once a day under any conditions and reports battery voltage, battery life, things like that. Then future units, which you've seen the one that's out here at Don Wood's table at towards the entrance. We can add a variety of meteorological equipment to that. It would include anemometers, thermometers, barometric pressure, relative humidity, and even certain pollutants. So there's a large number of data collecting items that can be added to this, all of which will run through the Arduino processor and be able to be uploaded to the cloud server in real time or in packets once a day. So this is the original unit, square. We put in, I believe, 196 1.5 inch by 1.5 inch squares. And then we dropped steel balls on them according to UL 2218. And we ranged our height anywhere from 5 to 20 feet. Then the numbered squares allowed us to record where the impact values were reported. So we were able to do that and try and figure out what is the spatial relationship of impact values. And so this is what we hoped we would find. You know, we have this nice linear academic looking pattern of squares that gives us a really good idea of, you know, what is the spatial relationships of the impact values for the same amount of kinetic energy, the same size ball, the same drop from the same height, hitting at the same impact speed. But they're different values because of their proximity to the accelerometer located in the center of the red square. This is what we really got. Doesn't look much like the other one, does it? And so our plan to derive correlation coefficients for each of the squares around there based upon their position didn't look like that would work very well, did it? So obviously we needed another plan. So if you look at them side by side, you go, wow, you know, it's squares not really a very good thing. That's causing some problems. So those of you who remember Dr. Smith from Texas Tech, he looked at it with me and said, Matt, those corners are going to cause you some problems. And certainly he was proven to be correct in that. So at this point, we began to transition from the square-shaped Sentinel unit to the round one, which is located on the left-hand side and is out in the lobby here today. Here we are doing the test. The pipes you see coming down through the ceiling are inside a larger diameter pipe, and they are used as described in UL 2218. In the center of it, and I don't know that this has a pointer on it or not. I would use it if I knew how, but if you look at the first pipe on the right-hand side coming down, you see a silver object underneath it. That is an electromagnet. And so we started out with steel balls that we would energize the magnet and then raise it up to the prescribed height and then turn off the transformer and the ball would drop. Now that worked really, really well, but you know, even though the kinetic energy component might be the same for steel balls as it is versus something like actual ice or even a wood as a substitute for it, the impact damage is greatly different. And these square-shaped lenses, we broke about 30 of them with 1-inch steel balls. When we switched to the round ones, we also switched from steel to wood balls and used as large as 3-inch, and we didn't break a single one. So that's the difference of how much more damaging steel is than wood. So we repeated our test and collected our data and then mapped it out. And so now we can come up with something that looks certainly not perfect, but is a lot more of the concentric rings that we can work with trying to develop a correlation coefficient based upon the distance from the accelerometer located in the center. Now in this graphic, we show 16 different impact concentric rings. there's only 10 defined rings on the tile. So that's going to be changed a little bit to make it in agreement with what the number of rings would actually support. Now, in order to make a hail impact anywhere that occurs on the tile, make them all relative to a single point, which would be the accelerometer H, the home accelerometer, we have to be able to develop a method for triangulating between the 3 accelerometers we put around in positions 1, 2, and 3. And so this is where we place them. And then we can construct a nomograph from the amount of time that it takes to go a reading from location H to locations 1, 2, and 3. And so you get a nomograph that looks something like this, that allows us to correlate time in microseconds to distance in millimeters. Then from the length of the line from the location at H, accelerometer H, the home accelerometer, to accelerometers 1, 2, and 3, the length of that line would become the radius of the circle that we can construct to create overlapping points. And so that's what we've done here. And this is the exact same way that, that we are able to locate the epicenter of an earthquake. It's the same technology. They use accelerometers that go by a certain name called a seismograph. But it's the same concept. The difference for us, though, is that a seismic event, whether it's the primary P wave or the secondary S wave, makes no difference. They last for some measure of time. In other words, they have a beginning and a clear-cut beginning and an end. That's not really so true with hail hits. They all happen in just an instant. They don't go on for several seconds or even minutes the way that S and P waves will. So by taking our color pattern for each of the concentric rings, we can now find the location where the impact actually occurred. And so that's how we know which correlation coefficient to apply for a given impact. So we just multiply the reading from the accelerometer, which they call G-forces, which are the units of Newton meters. For the physicist in the room, I believe you call that work. So we're using that information, and then we're multiplying it by the correct correlation coefficient given which concentric ring the impact occurred. And once we've done that, we need to make a last conversion, and that is to go from G-forces, which hail energy is never reported in that. Hail energy is reported as kinetic energy. And so we collected data, velocity data with a calibrated ballistic chronograph. And then we could calculate the amount of kinetic energy in our pre-weighed wooden balls. And then we could correlate that to the accelerometer reading. And you see from the regression line here, we've got a pretty decent R-square of 0.97 and change. Now, the system saves all of the data, and it reports all of the data to the cloud. And it will make whatever calculations that we choose to make it, that the customer wants it to make. So there's the Arduino has got a good deal of computing capacity to do this. One of the issues becomes what is the refresh rate of the accelerometer, which is on the order of about 6 microseconds. So I was asked the other day, what happens if you have two hail hits that occur simultaneously? So long as they're more than about 8 microseconds apart, it will register two distinct hits. If they are less than that, then not so much. You'll just get one hit. You'll get whichever one is the larger value, and the other one will be ignored. So there's some good things about this. Number one, it works. It's quite flexible. It can report data to the cloud. We can have it report data to your cell phone. The units that you saw in one of the previous slides that were here at this facility, those were actually being reported to Andy's cell phone. So when the hail was occurring, they were actually watching the data come rolling in real time as the hailfall occurred. And the system, or excuse me, the individual units can comprise a node that may be 2 to several hundred or thousands of units that could all be belonging to one owner or to one group of buildings, let's say a university campus, for example. Then they can be a part of a much larger system that can comprise an entire region or even a whole state. So there's flexibility built into this that allows the users to get the maximum utilization of the data that has been created. So I would like to invite all of you that are interested to please contact me. My cell phone number and email address are up here. If you would be interested in collaborating with me, I'm all ears and would very much like to talk to you. And if you have any questions, please feel free to ask. Thank you.
Well, thanks. Can you just speak to the detection of severe angle, maybe like wind-driven hail, and what that might, how that works with the sensor?
Yes, sir. Thank you. That's a very good question. You may have noticed that one of the options that's available that the units can be equipped with a anemometer. And so if we know wind speed and angle, or wind speed and direction, we can calculate the angle of the impact. And then we can take the kinetic energy that is recorded, and we can compare that to what we would expect that same hail size to have produced as just at terminal velocity. Then if we make some assumptions about the density of the hailstone, then we can estimate the actual size of the hailstone, the angle of the impact, and even its impact velocity. So those things are all possible, but that's all post data collection programming that we do. But we have to have the data to be able to do that. And in this case, that would be, wind speed and direction. Yes.
Couple questions. One, have you had any of the new ones break or the old ones break due to hail?
No, thank you. That's a good question. And no, ma'am, we have not. Okay. Removing when Dr. Smith said, Matt, those corners are going to cause you some problems. Man, I don't know if he realized how right he was, because he was just thinking in terms of differences in the data. But the performance difference is affected too, in the sense that we've got much more longevity out of a polycarbonate lens now than we did previously. Now, in all fairness, at the same time that we changed from square to round, we also changed from a steel ball to a wooden ball. And I think that also made a big difference.
And then my second question is, I know it seems to me right now it's developed mainly for just the hail impact detection. Do you see this in the future being something like a building owner would have on their building for insurance purposes or other purposes to know if hail fell at their location, or somehow getting with municipalities to spread them out over towns and tracking it that way? Is that
right? I don't exactly know the answer to your question, but those are all areas in which we want to collect data so we can make the comparison and we can validate, because there may be a change of some type that we don't know about yet. It's part of what science does. And so that's something that we'll be looking for, but that's still out there in front of us.
awesome? Thank you.
Thank you. Yes, sir.
So as we look for data collection across the country, so what is the ballpark cost for one of these hail pads or hail tiles that you have? What is it retail for?
I'm not exactly sure on the pricing. Don, hold up your hand back there.
What do you think, Don?
See Don.
Can you tell us? We talking $100? We talking 1,000, 10,000? Oh, yeah, they're not on the market yet. Okay.
And we're planning on the reserve for at least 10 years in the cloud per location. And we're also looking at the nodes. One node will wake up the other nodes in nearby buildings or in a quadrant of a city because they communicate with one another. And then the data is all saved. We don't know the full possibility yet of what this device will do. And we're very interested in the seismic, even in building sway from high wind situations. So there's a lot of things that are about to happen with it. And we're trying to drive the cost down into the few hundreds of dollars. Our development cost is, of course, much higher, but we'll be going to market pretty soon with the minimal viable product. And then every year as they're upgraded, we'll swap them out. And so the cost will change and go down dramatically.
All of the units come with a calibration certificate. And so those that are using calibrated instruments, that calibration period is going to last from a minimum of 6 months to a maximum of maybe 2 years. Well, these are outside instruments, so their calibration period is limited to only 1 year. So once a year, the instrument will be picked up and replaced with the current model unit, and then that one will be taken back into our lab, and we will recalibrate it and be able to send it back out again for its next deployment.
Yeah, one more question.
Yes, sir. Go ahead.
Jochen Karl, FM Global, a great presentation. Thanks. I had just a thought if we could apply the same concept to solar panels, in the sense we apply the accelerometers and through regression derive a relationship between the kinetic energy and accelerometers through laboratory testing with hailstones, and then apply this in the field to derive a better relationship between kinetic energies and potential damage. So basically, can you apply this to another surface like a solar panel and not just the tile you have used before? Thanks.
Thank you. I don't know. The only lens that we have tested so far has been the 3/16 inch thick polycarbonate lens. If we were to try to affix the accelerometers to another type of device, another type of lens, then we would, have to go through the calibration routine all over again. But the thing that I would like to encourage is that once we know kinetic energy, we can then make some comparisons for any type of surface that gets impacted. So, there are ASTM standards for impact resistance from photovoltaic cells, also for their hail-resistant covers. In fact, Milton Smith, that looked at this with me, was the author of one of those ASTM standards for the photovoltaic cell hail covers. So there's, I think once we get the kinetic energy component nailed down reliably, then that can be transferable and usable with lots of other different types of surfaces. Okay, well, thank you for your time and thank you for being here.
Thank you, Mark.
I'm Satya from Technical University Graz, and we are working related to radar-based hail signature information and little crop-based hail impacts and also hail protection operations. So I'm going to present an overview about the hail protection operations in province of Styria. And also I want to acknowledge my co-workers and operational providers hail protection area. The main motivation of our operations is Styria also one of the hotspot area in the Europe. We also have every year a lot of damages, especially due to the hailstorms. So this is creating a lot of damage to the, especially for the farmers in the Styria. So due to that, each year severe hailstorms causing damage to crop and also resulting losses of millions of euros. So that is the reason here these hail protection operations are carried out to reduce the impact and also risk of the hail. And my study is majorly focusing on the hail prevention programs, the infrastructure, technical methods, what we are using, and daily implementation of the operations. This is the region of the Styria in the Austria. So where we can see the damage reports from the Austrian hail incidents. This is for 2019 here. Generally, we have this hail season from the April to the September normally. So here we can see the colors of the damage reports for the entire year. Especially more damages we can observe in the south and the eastern part of the Styria there. And especially these regions have a lot of fruit crops, which is very impacted every year. And it has major impact on like vineyards and other fruit related and also pumpkin crops also. So here we can see the damage reports from the municipality level for each year actually. And this is for the damage information from one severe hailstorm which happened in 27th July 2019. Here we can see the dashed line represents the hail damage reports at municipality level. Here the red color shows the reports above the 20 and other colors shows between different ranges from 0 to 10 and 11 to 20. So here we can see this severe hailstorm created a lot of damage in these municipalities especially. And this is the ground truth information from the European Severe Database. Actually, here we can see the hail maximum diameter around 8 centimeters and also 7 centimeters in that particular regions. And these are the footprint information from the Wildon area we collected. We can see the damage which is happened to the crops and especially corn and other pumpkin area. And also it has roof damage for the houses also. So we are also doing some thunderstorm radar-based hail signature information to understand the hail signature areas, especially. So this is the event happened, the severe storm is happened on 27th July. Here we can see the cell track, the yellow color represents the cell track, which is from the origination of the entire life cycle of the cell. And also these cell tracking methods consider different procedures for the entire life cycle. And also we computed different radar delivery parameters to understand the entire life cycle of the cell and how this area volume of the particular reflectivities are changing. And this information also help us to understand the real hail signature information at the location level also. So we did this analysis and we computed some additional radar-derived hail kinetic energy information. So this is for the entire event from the origin of the cell and dissipation stage, how these reflectivities are changing, and we use some proxies from the Witt et al. To compute the hail kinetic energy for each interval of the 5 minutes, and then we summed up, accumulated all the hail kinetic energy for entire region. So here we can see very clearly the high hail kinetic energy above 300 to 700 between existed. We can see that areas are more damaged with the crops, which is shown above the 20 damage reports for the day. And also this high kinetic energy is very well associated with the ground truth information of the hail, which is nearly 7 centimeters and 8 centimeters area. So this information helps us to how hail impacts are hail impacts are occurring in the Styrian region, and it is very important to reduce the risks. Otherwise, the farmers of Styria is facing a lot of losses, especially. So this hail prevention operation is one of the mitigation procedure we are following to reduce the hail risk in this area. So hail protection program in Styria is initiated in 1955. Now it's almost 67 years. In between some years, it's not operated actually, but more or less it is running until 67 years now. Different technologies were used. And also I want to highlight here, in the Styrian province, this especially the protecting the farmers due to the hail also considered since long time. They are trying to find in 1900 itself, they are trying to conduct some conference and trying to find some solution. How can we mitigate these procedures? So since long time, Styrian community is interested to reduce this hail. They initiated these operations, and initially with different technologies. Initially they used rockets. After some years, from 1960 later, they moved to the ground generators. And later this aircraft seeding also initiated from the 1983. And initially we used the burners with the silver iodide. And in addition to the burners, now we are using some flares from 1990. And after 2002 to 2015, 2005, between these operations was not carried out actually. Later the Syrian government initiated to protect from the hail. So they initiated a platform to combat different technology and different resources, infrastructure information. So a platform was developed actually to protect these operations. It was initiated in 2007 with a different platform resources. Here, three defense operators are working for this program at the time: Hail, and Styrian Hail Protection Cooperation and Sudflug. Hail areas they worked until 2009 and 19, and later Hail and Styrian Hail Protection was merged together. And now we have two operators for these operations, and also we get the additional resources from the Austrian Meteorological Institute provide the forecast information, and Austrian hail insurance, they provide the especially crop damage information for each season at municipality level, daily reports. And as a technical institute, we are providing scientific and technical information and operational things for this platform. And this is the protection area. Here, the yellow one is the one operator we are using, this Styrian protection area, and the south one is the Sudflug. And especially here, we are using different airports to conduct the operations. Here, the red button indicates two airport areas. One is Graz and other is Fürstenfeld. Initially, we used 3 airport areas also for these operations. Now we are using 2 airports. And this is the infrastructure information. Especially we are using 2 radars for the operation. Both are C-band radar. And we are using small Cessna aircraft which is equipped with silver iodide burners. Here we can see the silver iodide which is already activated in the picture. These are the 2 radars we are using. One is Gibrit Kugur radar, which is using for the 5 minutes interval, three-dimensional data, and additional radar, which is Rehav. This is the radar we are operating with. It is owned by our hail protection organization, so it's our own radar. And biggest advantage of this radar is it is a rapid scanning system. It's a continuous scanning system. This helps us to understand the initiation of the hailstorm cells, especially where it's happening. The other radar which is occurring for the volume scan every 5 minutes. So sometimes 5 to 7 minutes it will take process and to render the information. So this rapid scanning system help us to take the decision very quickly and send the pilots in time. And this is a vertical profile from the Rehav radar. We can see how the cloud morphological information, how the vertical profile is changing, especially the reflectivity is how the changing from the bottom to the top. So this helps us to understand any rapid changes in the cloud, so we can estimate the severity of the cell and how fast it is growing and to take the proper decision. This is the volume three-dimensional vertical profile information from the another radar. This is especially the advantage of this both radars. One radar will help us to understand the rapid changes in the cloud cloud system, and the other radar will help more to understand the cloud morphology, how the area and dimension and how the vertical profiles are changing. This information help us to take the decision. So as a technical institute, we are providing different scientific and technical information for this platform. So radar data processing, quality checking, and initiating of the different softwares. We provide the weather information software, their nowcasting and additional weather resources were integrated, and also weather forecast information also integrated. And also we developed a tablet PC system, which is mounted in the aircraft, which gives the information to the pilot, especially the position of the aircraft and also radar signature information. And also we have another tool for ALCs, which is developed for hail event analysis, the post-analysis of the hail signature information and the entire life cycle of the cell, how these operations are conducting, whether we reach it in the time or these things can be analyzed. So as a coordinator, I'm coordinating this operation since 2018. As a coordinator of the operation, I have to take a lot of steps, especially based on the expected weather condition. We have to brief the pilots when we have to start the mission, and I will brief about the weather conditions of the particular day, what kind of system we are expecting, whether it is a convective or deep convective or frontal system. Like that, I will give an expected mission operations, and also what kind of risk of especially today, weather and which direction the cells are moving. This all information will be informed in the morning briefly, and I give the particular time when we are expecting the mission, so the pilots will be available in each airport. And later, whenever we observe the potential cells for the seeding, so I will inform the pilots. They will take the official procedure to take off and things, and they will reach the target cell. And this information every time we continuously monitor, and I will speak with the pilots with the radio communication. Each time I will inform from which cell to which cell they have to reach, and all this information continuously informed with the radio system. And also this tablet PC will help us to operations more easily, because the pilots can see their present position as well as the other pilot's position, and also radar status. The nowcasting status will help understand the radar-based hail signature information and the cloud information also. This is the one example of the tablet PC, which is mounted in the aircraft. Actually, here we can see 6 aircraft positions actually, and the advantage is the pilots can see their position as well as the vertical height information about compared to the other aircrafts. Actually, this helps us, especially this helps the pilots to take the safety conditions also, and also which areas has to focus, and is there any downdraft areas and updraft areas. They have to take precautions when they are doing operations also. We inform all this information continuously. And this is an additional to this tablet PC, not only providing information about the aircraft provision, we are using some new sophisticated novel technologies adapted here, and especially to, I can provide the coordinate information from my mobile to the pilots, so they can see in the aircraft. I need not to speak every time with the radio information, because sometimes when 7 aircrafts are operating, it's hard to find the time. And also when in the near the mountain region, sometimes due to this radio signals are not working in that time, this kind of system, this kind of information system will help us to coordinate very quickly. The pilot can see and go, and they can easily direct at the next target cell, and also other pilots can understand. And in addition to that, we are trying to get some crowdsourcing data from the pilot, especially about the updraft information. This is really important, and this helps us in future to understand updraft regions, and this can be helpful for future hail studies also. They give the feedback from the severe and low level, less intensive and medium and high intensive updraft information, and this then data is stored in our database systems. And this is also, in addition to the hail operations, we conduct different procedures to collect the data from the ground-based information. We developed a hail event database system, which is the browser-based and also an app-based. This system was developed. Citizens of Styrian region, they will provide the information for us. Actually, we are collecting this. The unique thing in our data, our system is not only collecting hail diameter and this information, we are trying to get the impact information also. How this impact on agriculture, what kind of damage, how much percentage this damage is happening. This information will help us to understand, and this will also helpful for future risk assessment information things. And also we conducted some pilot studies with the drones also, how drones can help us to identify the ground truth information and how can we retrieve this information with the using machine learning and dense size. This Hailsys information will, Hailsys software help us to understand the complete life cycle of the cloud and help potential clouds, radar-based signature information, and we can compare whether this cell is, because the biggest challenge is here to identify the discrimination between the heavy rain and hail cell, actually. This is sometimes very complicated. That's why we use different radar-based hail signature information to identify potential hailstorms. So we are using this Wald-Vogel and Ayur criteria to identify as a proxies to identify the cloud signature information to take the decisions. This is also an additional derived product for the kinetic energy, which can be computed for particular 5 minutes, as well as we can accumulate for the entire cell period also. Here I am going to show an example of the operations, how we are conducting the documentation of the radar information as well as the aircraft positions. Here the cell was available already, so we initiated the process. Before that cell, we have to speak with the pilots and initiated, they have to get the clearance from the airport and they have to do. So all process already stated, they are reaching the cell in very quickly and they initiated the seeding process already. The 2 aircrafts were already started the seeding and continuously this process is going. Another aircraft also joined with that. So 3 aircrafts are seeding. And in between, we observed the new cell, which is originated here. So the pilot was already informed to reach the cell. So they are continually seeding these 2 cells with the 3 aircrafts. This process is going continuously. And every time I will inform this quadrant information to the pilots and which direction they have to move. And the pilot will reach the updraft region continuously. And we will speak in the potential areas for the seeding always. And I will direct them. So this is the process continues. We can see very clearly the high reflectivities are changing after the seeding like that. And this is the entire operational for that particular cells. And here we can see the complete flight tracks of particular day on 29th, how the complete operations are going from with the 2 different aircrafts with the almost all 4 aircrafts we used for entire operations. These are the major information from our operational things. This is, I want to give an overview how we are conducting these operations and infrastructure we are using. So we did different analysis also based on the radar information since 2008 already. We did some analysis with the seeding procedure also before and after seeding also we found some improvement. And this, especially this radar-based hail signature information is very essential, and these nowcasting tools are really very essential for this operation. Otherwise, it's very difficult to coordinate these operations. And every year we are improving infrastructure and technical side and scientific side to improve the operational information. And we improved very well because especially to the important fact in the sales, the sole focus of our operation as a coordinator is I have to bring the aircraft in right time. That is the most important. As a forecasting and hail signature information, this is one of the hidden mess work because we have to understand and we have to coordinate very well. But we improved very well. We try to reach most of the cell in time for this operation since 5-6 years actually. So still it's improving. Sometimes we also have some challenges, especially as you know, this discrimination of the heavy rain and hail, especially starting of the season and end of the season. Sometimes it's very hard to identify hail signature cells because sometimes we may have heavy rain and hail, small hail. So this is also one of the challenges, and some days are very complicated weather systems. Actually, they develop very rapidly. So the forecasting and things is challenging, but we monitor every time. So mostly we try to reach most of the cell, maybe 1 or 2 cells. May miss sometimes, or maybe just we reach little late, but mostly we reach most of the cells and within the time. This is the information from our side. I'm open for any questions.
Any questions?
A couple questions.
One, do you have a feel about how this impacts the regional precipitation at all? And then two, obviously cells go through just like natural cycling. And so how do you know that the seeding efforts are working? Is that part of the ground-based collection or, yeah, so.
Yeah, as for the regional wise heavy precipitation, because I also worked in the extreme precipitation actually as a climate change. So we are also comparatively since few years actually, because my pilots are working since 2005 and as a discussion with them in the real way actually, they never see such a systems earlier. In 2016, we operated hail operations almost a lot of days we did operation, and the sales also very intensive because earlier they didn't see that kind of intensity when they are operating. And 2016, 17 also we have some extreme severe hailstorms actually. So as for the fundamental climate change information, it's possible to increase that region. So that's why this kind of operations are very essential for the mitigation. And the second point, this is the expected question from this operation. More fundamental thing is how efficiency. This is the thing. So that's why we did some additional because ground-based information, we have Hailpad system, this collection of the things. Sometimes it's very hard to evaluate the thing, but we did some analysis based on the radar data because it is not a randomized experiment we are doing. It's a pure operational. So you should not leave any cell in that particular area. So we cannot compare with the non-seeded and seeded cells actually. So in scenarios, what we did, only seeded cells before the seeding time and after the seeding time, we did some radar-based derived parameters analysis for 2018 to 2016. We found really great improvements. It's a small improvement, but we did almost 7,000 cells actually. So we found a great improvement in that actually. Actually, next meeting, I want to present that result. Now it's because I cannot keep both things because this evolution take long time to show. And also, especially other thing, this inertia to the normal evolution process, because now we are mostly dependent on radar derived verification system actually. In future, maybe we are trying to find like collection of the hailstones and how the particle things and this information also we are trying to do in future actually. Yeah, thank you very much for that question.
There you go.
Are your seeded systems, are they mostly multi-cell or supercell type of systems that produce your hail?
Both, yeah. Both we work, multi-cell and single cell. Because the thing is, here the hailstorms, as you know, sometimes this merging and splitting will, different procedures happens actually, but as a procedure, we should not miss any hailstorm because it has some impact on the crops actually. So we have to take all the cells which is operating that area.
Anybody else?
That was excellent. Thank you. Have you determined any kind of factor, multiplier or discount rate on post-seeding intensity of events?
Yeah, we because it is not very clearly, it's very hard to determine like that because the biggest challenge is each cloud is unique. The properties are very unique. Of course, when some systems, even if it is frontal or convective, what kind of things, but each cloud characters are, almost I saw physically a lot of clouds, but the morphology is very different actually when you want to take the things to determine like this. But we initiated some procedures actually to determine these things for the better assessment and decisions actually. We developed something and in future also we want to emphasize that analysis more. Thank you for that question.
All right, well, we're running a little bit behind, but let's take a 10-minute break and start again.
Thank you very much.
All right, it's 11 o'clock. We're going to continue now. Up next is Cameron Nixon. He's going to be talking about Hodographs and Skew-Ts of hail-producing storms. I've been following his work on Twitter for a while now. He always has a lot of interesting stuff to show with the Hodographs. So especially if you're a meteorologist, or if you want to know more about how we look at the way the winds turn in the atmosphere for these type of storms, really great stuff, and looking forward to this.
So I'm going to do the slow walk because it's very empty in here. All right, so I'm going to be presenting on the Hodographs and the Skew-Ts of hail-producing storms. This is work with my advisor, Dr. John Allen. We're from Central Michigan University, and we're also being funded by the National Science Foundation Prevents Project. And so for those of us uninitiated, the common parameters that we tend to use when we forecast hail, right? We have buoyancy, we have some measure of how much warmer the parcel is than the surrounding environment. We use convective available potential energy, CAPE, and then convective inhibition, SIN, to kind of quantify how much more buoyant that parcel is in that environment. We might use a lapse rate, right? We've talked about how quickly temperature decreases with height as being a predictor for hail. Freezing level height, I've heard that thrown around a lot this week. And some measure of bulk shear. How much do our winds change in speed and direction throughout the atmosphere? And so the question that I had going into this project is, I am a Hodograph guy. I find these things fascinating. I love to try to figure out how the wind impacts the behavior of a storm. And so my obvious question coming in was, well, can the Hodograph predict hail size? And as you could see, as we, in a mean sense in the data set that we've been using, as we go from marginally severe hail to larger hail to giant hail on the right, you see that the shape of our wind profiles and how much shear we have really does not change hardly at all. What does change is our thermodynamics here. And so this is not to tell you that the wind shear is not responsible for changes in hail size and whatnot, because there have been studies that show, especially through modeling, that on a smaller scale, on a case-by-case basis, stronger deep layer shear actually is associated with more enhanced hail production and possibly the odds of a greater sized hailstone. But just because all of our hail sizes indiscriminately seem to love this shape of Hodograph here, we want to talk about it, right? What do we have in this Hodograph? We have weak level shear. Our purple segment, our 0 to 1 kilometer change in wind direction and speed, is generally weak. And this has been something that has been substantiated by a variety of studies down here, especially shear that is relatively straight and creates a more straighter Hodograph without these big, large humps. And we need at least a decent amount of cloud layer shear, right, to sustain a supercell. What we do not really want typically is strong low level shear, right? You can see our hail Hodographs or our tornadic Hodographs significantly depart from our hail Hodographs here, in that they have really strong low level shear. And this has been something that has been directly modeled, especially in these Cumgen studies, to generally hamper the production of large hail through really unfavorable storm relative wind profiles. So we don't want the strong low level shear for hail, and that's been pretty well established so far. But what I wanted to tackle then is, I thought there was some information to be had here, right? I thought there was something cool to come from the Hodograph. And so we tried to take a look at the balance between CAPE and shear, because if you're a tornado buff, you know there is a CAPE shear balance, where if you have stronger shear, you need a little bit less CAPE and vice versa. So the obvious question then for me was, well, what about hail? Because we really haven't established that yet. So in a mean sense, for a little primer, what we found was that if we increase our shear from this little baby Hodograph to this really huge Hodograph, we change our CAPE, right? Looks good. We have a lot more buoyancy up here, a lot less buoyancy down here. This looks like a CAPE shear balance to me. However, when we look at our CAPE samples, we've got our high CAPE and our low CAPE, our Hodographs don't change. And so this is a kind of interesting result, right? Because we wanted to see kind of the opposite to be true. But, this is just in the mean sense, and I've already talked about how in the mean sense, things can, details can wash out. So we want to know about the variability here. And so for the rest of this project then, we use what's called a self-organizing map. And all this is a form of artificial intelligence that we're basically inputting over 7,000 hodographs into the self-organizing map. And what this algorithm is going to do is it's going to say, okay, hey, these 3 hodographs here are relatively similar, right? We're going to cluster them in the same little group here. We're going to put this in cluster 1. And then we're going to find clusters of similar hodographs for all the rest of these shapes. So what we get is kind of this array, or this smorgasbord, if you will, of the most common, I guess, hodograph shapes associated with large hail. And so these are the ones to choose from, and these are the ones that we could study. So for our data collection, we use the SVC's hazard storm mode data set over the past couple decades. We use the ERA5 reanalysis. And then here are the specs for our self-organizing map, and you can ask me about that later. So what we wanted to do first was basically give the self-organizing map algorithm only the hodographs, right? We want to give it these hodographs, feed them this hodographs, and then out of this is going to come a variety, an array of different most common hodographs that this machine learning algorithm found. And so right off the bat, you don't have to know anything about hodographs to tell me that the shapes of these lines are not anywhere near similar, right? So these are all cases that produce 2 to 4 inch hail, the same end result. But we had so many different varieties of hodographs here, right? We had weak shear, we had strong shear, we had strong low-level shear, which I already told you was not a good thing, and then all sorts of different things. So, you know, I'm mashing my head against the wall, like, right, like, is every hodograph a hail hodograph? And so what we wanted to figure out then was, how is the Skew-T playing a role in this, right? Why do we have such strong variability here? And so I want to draw your attention to these cases on the left, which I've generally identified as weak shear, and these cases on the right with generally stronger shear. And you can see there's a big difference, right? We have a lot stronger cape with our weaker shear cases and weaker cape with our stronger shear cases. So that checks out. Again, we have a cape shear balance in this regard. But now we're going to train the self-organizing map with only the Skew-T. It can only see the Skew-Ts now. Now it's going to sort these into its own array. And so these are the most common Skew-Ts associated with 2 to 4 inch hail. And when we look at their hodographs, they are all the same. So what this is telling us is that this cape shear balance might just be one-sided. A variety of shear profiles are conducive for large hail, but this depends on the cape profile, right? Typical cape shear balance. But a variety of cape profiles are conducive regardless of the shear. So let's look at this in more detail. Let's look at just cases then of large hail occurring with weak shear, weak deep layer shear, right? These are teeny tiny hodographs. There's hardly any shear. These are these kind of like surprise cases where you have a 20 knot jet aloft, probably in somewhere in eastern Colorado. And so you could see that the cape profiles associated with these weak shear cases vary so much. You have these really dinky, skinny cape profiles. You have lots of buoyancy here. You have everything in between when you have weak shear. Cape can vary. When you have strong shear, though, there's a common denominator. All of these cases have generally weak cape. And if you don't have weak cape, you have lots of dry air, which is effectively reducing the amount of cape you have anyway through entrainment. So this entire array of strong shear cases, it almost seems like we need weaker cape in order to compensate for that, right? It's not a we can have weaker cape, it's a we need weaker cape. And when you have strong cape, shear could be whatever the heck it wants to be, right? You have all these fantastic array of hodographs here when you have strong cape, and you have the same thing when you have weak cape. You have huge low-level shear, you have teeny tiny hodographs again, right? But if you have weak cape or strong cape, you can have just about any shear profile you want. So to kind of sum this up then, I'm going to use this word versatile. Weaker shear is more versatile for large hail. And with stronger shear, you start to limit the selection of cape profiles that you can have in order to produce the same amount of, same magnitude of hail. So I can't just straight up tell you that weaker shear is better for hail, right? We don't know that. And we've already had studies that can contradict this. But I can tell you that weaker shear is more versatile in hail formation, and that a lot more thermodynamic profiles could support large hail if we have weak shear. And then cape can vary as long as it's in moderation. And I'll cite this Lin and Cumgen study. We really were favorable for hail at that point. So now let's look just in the lower levels of the atmosphere then. And so when we have weak low-level shear, we get that huge variability of CAPE again, right? We can have just about any thermodynamic profile that we can possibly imagine if we have weak low-level shear. But when we have a strong low-level shear, look at this. All of these cases have a huge cap. Some of these almost look elevated. Look at all this dry air here. Look at how unfavorable the low-level profile is when we have strong low-level shear. So this is telling us that when we have strong, especially low-level shear, we need that inhibition. We need the storm to really not be able to feel that strong low-level shear, which we already know is not a good thing in the hail production process. And then when we have weak SIN, right, if we're guaranteed to feel that low-level shear, our low-level shear better be weak, and that's what we see. When we have weak SIN and no inhibition here, we have weak low-level shear because we need to not feel whatever shear there is in the boundary layer. But when there's strong SIN, and this is completely counter to what we would think of when we're forecasting tornadoes per se, but when we have strong low-level SIN here, we don't need a certain shear profile, right? We don't need shear to overcome that strong SIN. That strong SIN is good in and of itself. So then to sum this up then, weaker low-level shear is more versatile for large hail, just like weak deep layer shear is. And then when we have stronger low-level shear, we greatly limit the buoyancy profiles that can support hail then. When we have strong low-level shear, we need to have a lot of inhibition here. We don't want to feel that strong low-level shear. And then as long as low-level shear is weak, SIN can vary. SIN can be whatever it wants to be. SIN is generally thought of to be good for hail production in this sense. So the takeaway for this is that, yes, there does appear to be a CAPE shear balance in hail production, but that balance is only one-sided. Shear is conducive, but that depends on CAPE, right? We can't just say that a certain hodograph is good for hail. We need to know the thermodynamics. But our CAPE profile or buoyancy profile is conducive regardless of shear. So you can look at a thermodynamic profile and pretty much any of them will be decently supportive for hail. So the most versatile conditions then for large hail seem to be shear in moderation. I'm going to make this really general because both our deep layer and our low level shear seem to be most versatile if they're in moderation. And this is just like that Cumgen and Lin and Cumgen study that showed that CAPE generally needs to be in moderation as well, right? So both of these seem to be most flexible in the terms of other environmental conditions that you could have. And then generally SIN in abundance is a good thing. SIN can overcome a lot of the different shear profiles that can have negative impacts on hail. So generally when you have an abundant SIN, you don't have to worry as much, is this hodograph favorable for hail or not? And then from a forecasting perspective, right, if shear becomes stronger, CAPE has got to be weaker in order to compensate, and or SIN has got to be stronger, especially if we're dealing with low-level shear. We don't want to feel the impacts of those shear here. And so I'm going to just speculate here that the shear that matters is somewhere in the effective inflow layer, but I don't know. And this is something, a topic of future study. And then so I'll leave you with this last disclaimer that as much as the environment is very important for hail, storm mode is always going to be a confounding factor. And so this is the storm that produced the Hondo, Texas record hailstone. And you can see there's so much going on here, right? The storm characteristic, structure, intensity, what have you, depends so much on the surrounding storms, more than just as much, if not more than it does the environment. So there's a lot of things the environment cannot explain. But these are the signals that have came from this study so far with our large data set, and I will happily take any questions.
We do have plenty of time for questions, so Victor?
You'd ask one.
Thank you very much, Cameron. We found in our 2021 paper, the machine learning, that very similar to this, the only shear that really mattered was shear in the hail growth zone. So I was wondering if you looked at that or what your thoughts would be.
Yes. And so I think I personally do not like the results that we found that we've been dealing with this data set, that our deep layer shear does not increase for increasing hail size, because I know that's the result that you found. And, you know, intuitively it makes sense. And the Dennis and Cumgen study also makes sense. So there's a lot of support for the fact that stronger deep layer shear in general, in all cases, is better for hail. This is just not a result that came from the study. And I don't like to sit here and say that strong deep layer shear is not good for hail. So that's why I like saying that weaker deep layer shear is more versatile through a variety of environmental conditions. But there's probably some tipping point where if you have the right Cape profile, if you do increase your deep layer shear, it's going to be more supportive.
For the virtual folks, we are not monitoring the chat like we have the past couple of days. So if you have a question, please raise the hand in the Zoom. We'll watch for that, and then we'll have you unmute. So if you have a question, please raise your hand. We still have time for more questions.
One thing I was curious about in a little bit more detail. In some of the data I've looked at, there's often a case where basically if you go across the different Cape values, for instance, there's like in the mid Cape values, there's like most of the high large hail events happen there, but then the most, if you just take like the average of those, the average hail size is still really small. How much of that I guess have you looked at like kind of the relative distribution, or like what is the tail probability of large hail in different parts of these regimes? And I wonder if that would offer more insight than in some of these situations.
So I guess I'm not fully understanding the question. I guess like with the self-organizing map approach, I guess we want to see like we can access all many different parts of that distribution, and we're not going to have like huge Cape, low Cape like lumped into one Skew-T, right? Because they're going to be like discretized anyway. Right. After the SOM approach, is this? Yeah, like I'm not on the right track.
I guess on your rules of thumb here, how much are they, I guess, based off of the mean of the distribution versus the tail of the distribution?
We're assuming here, I guess, that the self-organizing map approach is representing the entire distribution, which is our assumption.
Okay, yeah, that makes sense.
That's a good question. I want to chat with you later about it.
Yeah, let's follow up.
Okay. Yeah.
So the Hodographs are storm relative Hodographs?
No, that's a good question. These are shear relative photographs. So we want, because we don't have the storm motion in these data sets, we consider the shear profile a more reliable estimator of storm motion. So we rotate these based on the 0 to 3 kilometer shear. So this is the shape of the Hodograph.
Okay, thank you.
Yeah.
I have a quick question. Is geographic variability considered in this? For instance, getting large hail in Denver versus the lee of the Appalachians is a much different process.
Right. We in our paper, we're going to kind of show where these locations occurred. But there's a quote earlier this week by Sarah Bang here when she was on the panel here, or when she was speaking, whichever, and that, like, you know, the ingredients don't matter where you are, right? And so that's what I'm trying to figure out. So, and we had a question over there.
Cameron, 2 quick questions. Have you thought about using SOM on both the thermodynamic profile and the shear profile concurrently instead of separately?
Yes, I think we wanted to tackle each of them separately. I don't see why we couldn't try that.
And another quick question, I think helping us wrap our heads around what's going on here, if you could run some CM1 simulations with some of these profiles. Although looking at that one you got up there, I don't know how we trigger a storm, but we could at least try.
Right. That's something that I was talking with Matt Cumgen offline yesterday, but, you know, like a lot of these environments you see are hostile for CI. Like a lot of these large hail cases are hostile for CI. So these environments might have to be something that evolves over time after you've already gotten a supercell.
All right, thank you very much.
Yeah, thank you.
All right, up next we have John Allen talking about searching for predictability in environmental conditions preceding large hail.
So if Cameron hasn't depressed you enough, I've got more. Just to note, Julian, Cameron has actually looked at that overlap, and it's kind of interesting. So today I'm going to talk about some work that I have been pursuing for a couple of years now, and it's kind of sad that the results have proven relatively difficult. Not surprising, given some of the stuff that Becky's talked about, that Matt's talked about, and similar. But there is hope. Okay, we'll start off with a little bit of hope. I don't want to go completely negative from the outset. So the question is, well, what are the sort of conditions that drive different sizes? That was where we sort of started with this. We have a whole bunch of hail forecast parameters. Victor's work recently sort of quantified, how poor some of the parameter performance was. Significant hail parameter turns out to be exceptionally poor. It actually has a really special ability to not predict things in the southern plains where it was designed for. We also have other things like the Large Hail Index. It was developed on relatively limited samples. The problem that has beset a lot of these studies has been sample size. 1,000 samples was kind of the high bar. Victor went and used a huge amount of storm data to get around some of that and to look at that with random forest, logistic regression, other similar methods. So what I want to sort of get at and start talking about a little bit today is there utility in parameters? Is there any hope, right? From a forecaster's perspective, we want a little bit of hope there, right? Even if it's a small bit, at least it's something. Is there dependence on storm mode, regime, region? Are the parameters well designed? And I think that may be part of our problem. So previously, and unfortunately it's gone with an older slide, so I apologize, there was another piece to add to this. We've shown that SHIP doesn't work particularly well. It works worse than the southern plains. Basically, anywhere we have strong mesocyclones in the storm mode data set, it tends to do worse. Most of the environmental parameters actually do way worse in the southern plains and the southeast of all places. So what we did was we looked at a series of rankings effectively of these variables using optimized thresholds, and then looked at the high key skill scores and then ranked them based on this, and then sort of came up with an overall rank. What sort of things fall out, right? And we see some common parameters, but even these parameters don't have particularly high key skill scores. We're talking about things in the range of 0.25, right? That's not a particularly great prediction. As Becky showed, that's kind of problematic. Generally speaking, SHIP and LHP, you're almost better off just using CAPE. And that's kind of a sad state of affairs. When we look at mesocyclone strength being stronger, that's when our environmental parameters tend to do worse, which makes a lot of sense, right? Where the storm dynamics themselves are picking up for some of the environmental parameters, there's more variety of way to get there. So I'm going to throw this out to the audience and do it a little bit differently. What is the biggest problem for determining environment parameters favorable to large hail? What are our issues? What's that? The ground? Yeah, that's a bit of an issue. Yep, not good. I can show you plenty of evidence of that. Large parameter space, right? Cameron's work kind of points towards this. He gets the cool fun talk. I get the more sort of boring talk, but that's fun. Our environment's useless, right? Becky will tell us that environments are useless. That's what the start of a talk. Hail is a stochastic random process. Gosh, that feels depressing. We aren't really very creative when it comes to parameters. We are incredibly boring when it comes to parameters. It's some variation of CAPE, it's some variation of shear, and beyond that, we really don't quantify part of the space. Part of what Cameron's work is trying to get at is, should we be using more of that profile instead of just saying, hey, we integrated from here to here? Because there are differences that occur in regimes, right? There are differences that occur in regions. If you've got a northwest flow event, it's going to be very, very different from an event initiating on the low-level jet. Can we really use reports? Maybe. What can we do with that? People are our problem, big time. Sampling biases, censoring data sets, storm data saying, hey, let's increase it to 1 inch and that's all good. Changing of data sets, well, different data sets, you get a different result. Can you believe it? Sample size overall. Here's my problem, the one that I think is the biggest issue: data quality and cleanliness. So why do I raise this point? I spent a couple of years playing with this SPC storm mode dataset and started to get increasingly frustrated about the sample. It wasn't until a paper went into peer review that someone happened to reveal to us that that particular dataset, the small hail data were actually clustered to 2 years. They were included as an afterthought, and it's a problem. So the data that you're using to train that, for example, some of the SOM stuff, is fundamentally flawed. It is particularly problematic for regional signals because the sample size is on the order of 10,000, right? If you start subsampling to, I want the southeastern United States, the northeastern United States, you're dropping the sample size, right? Statistically, that's not a good thing to do. So I decided to go back to the drawing board, and that's kind of where I'm just getting into the details of this. And I've built a new data set which uses MPing, CocoRAS, and storm data. And you're going to see why using the three of these together starts to get us towards something that's maybe a little bit more representative of hail size actually, and gives us a much better fitting procedure with much higher skill scores. So how do you get a verifiable data set? Well, that was a problem that I spent a fair bit of time stewing on. How do you get an independent sample? Well, we go with a daily grouping. We only get one sample per day. We're not going to oversample a given day. We're going to make sure that they're spatially dislocated. We're going to use a KD tree to ensure that we're getting independence of location in the reports. So, that's making sure we're outside of about 3 grid points in the ERA5 reanalysis. And we're going to avoid duplicates between data sets. So if 2 data sets report the same thing, we're going to take that information. We're also going to apply buddy checks, right? So people who are familiar with data assimilation are used to the idea of a buddy check. You check a couple of stations against each other. Well, we know that SPC storm data has a problem, that you end up with roofer estimates of hail or other similar issues that could end up with biases in the overall size indicated. So why don't we check with nearby reports to make sure that something's not way out of left field? So from that, we end up with 4 different data sets. I'm including the storm mode data set slightly separately and then checking it doesn't overlap with the historical data just so I can use that as a reference point. If we look at CocoRAS, one of the interesting things that we found in a study with Kim Elmore is we actually looked at MPing. MPing is a crowdsourced app-based. It's got relatively good geolocation, good timing. It gives us a different distribution. It has its own issues, but it does give us different information than we're getting out of storm data, right? If we look at that storm mode data set I've been using, California is pretty sad, as Oregon, as Washington, or even places down in the southeast off the East Coast, right? So using these different data sets and their spatial properties together, we start to get towards something that maybe is a little bit more spatially uniform and regionally representative, instead of just being censored for the center of the high plains. If we look at CocoRAS, right, clearly it's very, very popular in the Front Range. It's pretty well distributed. It's very popular in Chicago as well, interestingly enough. But it gives us additional data points. But what's really interesting is when we start to get into the size, and I'll show you the size distribution influence of this. But what comes from using something other than storm data is observations less than 1 inch. And if you want to train a null sample to do an environmental predictor, you need something to be there. 1 inch is not a great discrimination point because it has all sorts of issues driven by the way the data are collected to verify warnings. 1 inch hail is not a representative data set. So if we combine these, we end up with something that approaches a decent spatial coverage. And in terms of overall number of reports, we're looking at around about 85,000 independent events from the period 1990 through to 2021. All these data sets have different lengths. So these have all got an associated environmental profile from ERA5 using both a nearest methodology, hour before sampling, and then also sampling around the area to find one where it actually has instability, where you have boundaries involved, etc. Let's look at the distributions. And this is where things get a little bit scary, right? So you can notice that for storm data, for SPC's historical data sets, there seems to be a little bit of an offset going on there, but it's still just that bad, right? You have issues with censoring towards reference objects. We've talked about this a lot through this week. But if you look at CocoRAS, wow, we actually populate that small stuff. If we look at MPing, we get some stuff that we don't have. It's reporting on a 1/4 inch. It's a little bit easier for users to use. You don't get the end user changing the overall category, which is a problem with the storm data set. And so if we merge these guys together, hey presto, we have a distribution that starts to look something like what we expect. Clearly, it's got issues, right? It's not a perfect distribution. I chose the binning to make this look really bad, right? But you can see that, you know, certain reference objects get reported more frequently, but at least we've got something to work with, right? Instead of having a sensor distribution below 1 inch. So previously, I talked about optimized parameters and sort of thinking about, okay, if we go and give them all a threshold and then we start looking at the high key skill scores, we start ranking them and start comparing them just on a single parameter basis, just to see what happens. Now, I'm going to say right now, don't read into that for a result. That's using the SPC storm mode dataset. You're going to see very, very different things when you start using this new dataset. So looking at other characteristics, distributions as well, but this is a nice sort of high level way to think about it. The sample size was pretty small. Now we're talking for 1 inch hail, so greater than 1 inch versus less than 3/4 of an inch, and see where the parameter skill starts falling out. And all of a sudden, the parameters that weren't turning out in the storm mode dataset are showing up. No surprise, more CAPE is kind of useful if you want to get between sub-severe hail and severe hail. Not so overall surprising results, but we've still ended up with more skillful predictions. And this has been cross-validated as well, but I'm not going to talk about that today. What's kind of interesting actually is for the 2 inch case, that big elephant in the room of sin jumps straight out the top. You'll notice some other common parameters that we see, but what's kind of interesting is that this CAPE is still not optimized. If you start to play with it where the CAPE is distributed, that becomes regime dependent, regionally dependent, and you start to think about that as well. And that's somewhere where I'm going with this as well. 0 to 3 kilometer lapse rate. But notice the mid-level lapse rates do not make an appearance. You'll also notice the effective bulk wind shear becomes more important for the larger stuff versus the sub-severe to severe transition. So I did something different here. Let's just flick between the two of these again. Notice the parameter importance changes somewhat. Well, this particular data set was built using data where we were just sampling the nearest ERA 5 point. Clearly, the 1 inch data is sensitive to this, the 2 inch data is not. And so what's actually happening is you're ending up with a whole bunch of zero CAPE cases, which is biasing your distribution. So be careful with these data sets and make sure you understand what the associations are before sort of doing that, right? So applying 100 joule per kilogram CAPE threshold, so a reasonably unstable environment, not particularly, but at least there's instability, helps somewhat in refining out the predictors. So let's do a little bit of regional, and I'm going to call this whole area west of that black line there, west. Be really creative. But we're going to go with Northeast, Northern Plains, Southern Plains, Southeast, and sort of look at the breakdown of this particular data set. So interesting things start to happen. In the Southeast, for some reason, we're more skillful than we are in the Southern Plains in general. A lot of parameters work a lot better in the Southeast. And that's something we actually saw as well in the storm mode data set. It was just the sensor distribution didn't help us as much because there's a lot of the smaller stuff occurring in the summer in the Southeast. It's actually seasonally dependent, just to make it more interesting. In the Northeast, again, similar parameters turning out. So there's some commonalities, right? But as we've just heard in Cameron's presentation, there's a variety of ways you can get there. What about if we look for these sub-severe cases for the Northern Plains and the West? I want you to pay close attention to what that top variable is in the Northern Plains and in the West, the third variable. That's just topographic height. So topographic height is a strong predictor for going between sub-severe and severe hail. If we look at other variables that are popping up there, we start to actually see things that are common with what's been experienced in Europe. If you look at fitted environmental distributions from ESWD, what you tend to see are things like SPLCL works, LCLs turn out, freezing level heights turn out. That's something we don't see in the storm data set if you just fit it normally, right? Freezing level height is something that we've badgered and beaten and said, hey, this is not particularly relevant. Well, it is. It's just relevant for a certain size of hail, not necessarily what we think about, which is the really big stuff. So some interesting things that I've still got lots of work to digest, but I just thought I'd point that out because it's kind of interesting to see some of the patterns we've seen elsewhere emerge when we start to use the data set a little more carefully. Other things that I'm playing with, and this is from the old storm mode data set, but I want to sort of highlight this. These take a long time to run. So this is basically taking the input variables and then looking at every single possible combination for interpolated data between 250 millimeter layers to 500 to 1,000, etc., all the way up. What you want to see is if a variable had some relationship, that you would see an increase in hierarchy skill score. Now, clearly, these are just single level parameters, right? We've got 81 points vertically from the interpolated data set at 250 meters. And anywhere you see that sort of shift to the right, hey, maybe there's some variable importance there. I have a similar thing coming for Kate. If you're coming to SLS, get ready to be excited. It's kind of cool, but I don't want to show it here. Lapse rates, right? So the way to think about lapse rates is, well, if we calculate every possible combination of lapse rates, which one should we pick, right? There's plenty of variations. You could just ask someone and you'd say, oh, this particular lapse rate's great for my area. What you should see is clustering towards the right, and that tells you that there's potentially predictability in that layer. Now, clearly, environments are going to vary, right? It's regime dependent, but you're going to see clustering that shifts towards the right. Now, lapse rates in general, just look at those high skill scores. Real useful parameter. But if we go to something like shear, where do we see the concentrations of the data? Well, why does 0 to 6 kilometer shear or 0 to 8 kilometer of BWD shear work? It's not because necessarily that it's a great choice. It's because it actually captures 2 shear peaks where there's predictability. So this is where I get into the point of saying parameter design is a problem. And we probably could do a lot better if we actually went back to the drawing board and did that. And I'm hoping to share some new stuff coming soon. So another thing, just to throw this in here. So this is some work from Jiwei Zhao, who works with Qihong Zhang, I think, who is probably in attendance, where we looked at satellite data, and then looked at the environments from ERA5 associated with this, and then used a self-organizing map to cluster them by similarities. What I want to draw your attention to, pretty map, there's these types. We'll talk about that in a second. But just here is the variation in regimal or locational types that occur over the continental United States. Part of the reason the predictors have been hard to fit is that we're not paying attention to the synoptic regimes, which is something that Susanna Moore pointed out on the first day. So this range of diversity, it's kind of interesting. That purple one, that's a high terrain one, which is where we're seeing that Z signal, right? The yellow cases here are relatively low cape, relatively high shear. The blue cases are cases where it is relatively high shear, high cape. So the classic sort of supercell thinking environment. And you can see those pink cases also get in there. Those are instability driven. So just to summarize, I think that part of the challenge that comes from predicting hail is that, yes, we've got a variety of ways of getting there. But I don't think it means it's hopeless for the environment. I think we're just going to be a little more careful about how we go, what data sets we use to address this problem. I think there is definitely regional variance dependence on parameters. Yes, if we get the same environment in a different location in the world, we will get the same result, most likely. But that doesn't mean that we saw a good example from Tim Ropach of the latitudinal dependence, right? Subtropical versus the mid-latitudinal signal. You could easily have situations which are not captured by the phase space that you could ever train. So applying these parameters ubiquitously regionally is problematic. There is definitely regimes, there is definitely model and reanalysis dependence. Do this with RAP-RUC, you get some other interesting things. ERA5 has actually has an interesting bias that is relatively low cape. And so that's going to influence the overall parameters fitted. So if you want to apply it operationally, you've got to be careful. I think the storm mode data set is horrible. That is my conclusion. And I think that we need to use this data set. So my goal with this data set is to be able to put this out to you guys in the community and let everybody loose on this thing. And let's actually see what we can really come up with and see if we can actually bring some hope to forecasters, because I know there's a few forecasters in the room. And that layer-wise cape, I'll leave that as a hanger. So thank you very much.
We have time for 1 or 2 questions. Anyone virtually have a question? Raise your hand. We do have one. You could, if you're virtual, go ahead and unmute and ask your question.
Thank you for the presentation. I have just two questions. So the first one, I know the SB cape is the MU cape is the most unstable cape, right? So what about the SB cape? Is that like stable or something? I don't understand what's the SB.
Sorry, ML, did you say ML?
MU is most unstable cape, right?
Yes.
So the SB cape, what does that imply?
So that's the surface-based parcel. So technically the MU cape can be the surface-based or anything up to 700 millibars, which is the most unstable parcel. So there is some overlap and they're clearly collinear parameters, right? That's the other thing to note there.
Okay.
Lots of collinearity that you got to worry about.
Okay. So my second question is about the height key. I don't know if I pronounced that correctly. The high key skill score. So is there it's possible to like play around with that threshold, like instead of the 0.3 that you used in your work? So if we use something lower than that, I noticed that it will consider more parameters.
So the high key skill score can vary down to negative 0.3, which means that you've made a forecast that's way worse than climatology. It also goes up to 1, right? So the reason I showed the 0.3 is that's kind of the benchmark we've seen from other studies and some other previous work. So I just wanted to illustrate that we can get past there with 1 parameter. We don't even need to go to something that's more fancy with that if we're careful about it. So the high key skill score in this particular case, what I've done is I've taken every value of threshold and run that high key skill score test to sort of find the peak in the distribution to set the thresholds automatically. That does lead to some interesting things if you're not careful.
Okay, thank you.
I have to come up here since I got called out. Can you say something about the predictability of small hail versus large hail? Do you feel small hail is more predictable, and why?
Yeah, so that's actually a really great point. I didn't show the stuff that's like 4-inch versus severe, or 4-inch versus sub, or 4-inch versus 2. What's kind of interesting is the predictability diminishes as we get to the larger sizes, which kind of fits with what we expect. For the 2-inch, I think 2 inch is probably predictable. I think there's just too many ways to get to the 4-inch. And I think, so that's, I think, the issue. For the smaller hail class, for going for like sub-severe, severe, I think we actually have predictability there. And I think that's part of why some of the logistic regression models and some of those simple models actually worked. Because that is actually, we didn't know what we were doing in some respects. We didn't have that data to check, but I think that was there.
One more question, go ahead.
Hi, I'm very intrigued talk. So I have 2 small comments. So the first one is that the environment conditions include aerosol. I probably will mention that because in some of the studies, actually in 2021, we published a paper showing that among all of the environment conditions, particularly for SGP region, we use the machine learning method and identify aerosol actually is a very important factors for the hail in SGP region. So this is something I also would like to actually challenge this group. Well, we need to also consider, when we consider hailstones, what kind of aerosol environment it occurs. That could also matters. Another comment is about the small scale meteorology, thermodynamic environment conditions. For example, the urbanization. If it's near the urban area, then urbanization could change your small scale meteorology and circulation a lot. That also, because I love here you look at more like large scale, probably from Reanalysis data, right?
So the point there is that as I sort of showed in that initial part, right, the storm mode does have a negative influence on predictability. If you have strong mesocyclones in particular, I'm not going to talk too much about that study you're mentioning because I know it used a lot of MCSs, right? I don't think we have a good idea of what hail occurs in MCSs. I also don't think we have great measurements of aerosols, right? So I think that if we had a good, reliable set of aerosol measurements, maybe we could test that hypothesis. for every case, we would need to have that, right? To get at these questions, I think we need to get at the, aerosols are there, right? What processes are they influencing? I don't think we're able to quantify that easily. We can do it in isolated cases, right? I mean, I know in some of your work, you looked at modeling some of these cases, right? But the question is, how do we make that representative and then sort of pull that out from all the other variability, right? I mean, as Becky's pointed out, there's a lot of different ways to get there, right? So how do we distinguish between the storm mode, the aerosol mode, right? We're trying to reduce, what we're trying to do is, I think, reduce the parameter space.
Yeah.
That's, I think, the key here.
Mm-hmm. So aerosols, indeed, there's some products like LD and surface PM 2.5 measurements. That's something you can try, particularly with machine learning. You can use it as predictors to try to see how it's matters. Thank you. Yeah.
Thank you, John. Up next is Ben Scarino. He's going to be talking about deep neural network and estimating severe hail.
All right, fair warning before I go further. I think between Colorado climate and some lively chats last night, I've almost completely lost my voice. So I've been taking some cough drops though, so I expect those to kick in any moment now. But we'll get through it, I think. So I'm going to use a few precious words to thank my colleagues first in putting together this work. You've been instrumental in that, so much appreciated to you for that. So I'm kind of steering focus towards the satellite view of estimating hail climatology, looking at the severe patterns that we see over long time periods. We have this record of geostationary satellite data that's just been quasi-globally observing severe convection at, in the case of GOES, 15 to 60-minute intervals for over 40 years. With the second generation of GOES, from GOES 8 through GOES 15, which has been observing from 1994 to 2018, we have this long single instrument sort of record of events happening in the northern and southern hemisphere that we can tap into and really use that to get a diurnal understanding of severe storm risk throughout the day. We have the environmental parameters, and keeping in mind what John said, we do have some understanding of what the ingredients are for active hailstorms from those ingredients, and we can capture those with MERA2 and ERA5. So the idea is that we combine the reanalysis and we combine the tight pixel level identification of these severe storm happenings with satellite data, put it into a deep neural network to come up with a way to estimate a severe hail likelihood. And in this case, we're using mesh as our truth. And we've heard many times throughout this week that mesh is not a perfect proxy for hail size, but at least we have it everywhere that we have North America satellite observations, at least in the CONUS, and we have a good understanding of both the likely occurrences of larger mesh as well as the non-likely occurrences, and that's important for training the neural network. So the satellite observation perspective or inputs from this come from work out of NASA Langley, where we've developed automated methods for coming up with or for identifying and characterizing likely updraft regions and the anvil and the extent of those anvils. And we start from normalized infrared temperature relative to tropopause, and then we identify these anvil cells. And we look within those anvil cells and we look for these embedded cold spot areas. Those embedded cold spots for ECS, we use statistical functions, we some human expert input compared to the NEXRAD OT detections. We analyze the temperature differences, the air rail extent, the texture of those storm tops, and kind of put that together to come up with a probability for OT for each of these locations. And if we aggregate those OT probabilities, we find that they are generally consistent with larger temperature differences. They're consistent with the radar identifications of OT. So we want to know how these properties from the satellite are distributed for severe hail producing storms and non-severe hail producing storms. The analysis process for the neural network starts from our truth set, which is the 95th percentile mesh Again, for our threshold, we're using 30 millimeters. That's not going to be a perfect proxy for 30 millimeter hail in truth, but it is a good balance point for our neural network and getting a comparable class representation for null and severe cases, and we get pretty good results using that. That mesh is aligned well with satellite properties, the temperature differences, the ECS difference with this surrounding anvil, OT probability, which I mentioned, and the area of those cold spots as well. With that and information from the environment, we can map those inputs to a likelihood for potentially severe mesh, I'll call it, for every ECS location. This was going to be an animation, and it would show that the mesh maxima are just generally consistent. The mesh maxima in this image are the smaller field contours within the broader field contour of the IR minus tropopause difference. But we find that those are generally consistent with the occurrence of very highly probable GOES overshooting top detections, which are shown in the white and gray blobs. But we won't get to see that move, but there's a snapshot of it. So we've seen plots like this throughout the week. This is a climatology of our truth data set, the mesh for a threshold greater than 30 millimeters in the A panel there and greater than 40 millimeters roughly in the C panel there. This is just for our 5-year data set, which we have used for training and validation of the neural network. And we see the same hotspots generally popping up in the central plains, the northern Gulf Coast there in central Florida, muted much more in the SPC reports, which are shown on the same color bar in panel B there. Then in the bottom right, we have the great data set from Sarah and Dan of the microwave radiometer probability of hail, and she showed much better figures of this earlier in the week, but we have higher concentrations again in the central plains, northern Gulf Coast and Florida there, but we're also highlighting maxima along the Sierra Madre in western Mexico there, northern Mexico as well, and then along the Gulf Stream, which is our areas that are outside the reach of mesh or outside of any training availability for our neural network. I'm not going to read all these, or I don't expect you to read all these, but for interest, we have many predictors for mesh available at our fingertips from both Reanalysis, a whole host of them, as well as from the satellite inputs. And then we combine these in certain ways across many different neural network experiments to kind of assess what the sensitivity is of the predictive scale of the neural network when you give it both satellite and reanalysis. Or what if we give it MERA2 or ERA5? What if we only give it the reanalysis? What if we only give it satellite data? So these sensitivities are interesting to investigate. There's also a row there for GO16 ERA5. We don't train the neural network, not yet, with the GO16 data, because the idea is we apply this to the longest record we have available, which is with the second generation GOES at the moment. But for interest, we trained a neural network with GOES13 that was scaled to kind of represent the temperature and aerial measurements it might expect from a GOES16 pixel, and we applied that to GOES16 data. We can look individually at the parameter space of these different predictors, and I picked out a few here, not all of them in the same panel, but of how they relate to the different mesh size bins. So if we go from the left-hand side of the box and whisker plots, the right side, you're moving from 0.1 to 1 inch mesh all the way up to 3 inch mesh or larger. And we see patterns that are expected, as you would find in other studies, where mid-level lapse rate sensitivity is moving with mesh as you might expect. Significant hail parameter does have a signal with mesh, so there's promise of that variable, maybe perhaps combined with other variables and coming up with a multivariate determination of what would be a larger mesh size. So overall, we see that the largest mesh are coincident with patterns that are 5 Kelvin colder than tropopause, up to 3 times wider and 60% more likely to be associated with overshooting tops. So we can combine all this information together to come up with something that's predictive. Here's a more robust view at all the collinearities of these variables. It's kind of a noisy plot with lots of blues and reds popping out here and there. The deeper the blue or the deeper the red assesses or indicates a stronger collinearity, such as those two bulleted there. We'll focus in on what the relationship is of a truth relative to all these parameters individually, and we see that the mesh and microwave hail probability show roughly similar magnitude as we go across the columns. Significantly weaker relationships found with the SPC hail size, which has some drawbacks that we all are aware of. But the point is that we have all these individual inputs that are relative to our truth, but there is complex interactions, multivariate determinations going into what is a skillful prediction for mesh. And that's best, it's well left to a neural network to figure out those relationships that aren't obvious. I'm not going to talk heavily about this. This is just the summarize of the architecture of the neural network, and those that find this interesting can talk with me about it if you like, or you can look at the hyperparameters in the table in the upper right. But the bottom line is we have our satellite inputs, we have a reanalysis input, and in the end, we're coming up with a model that is computing a likelihood at each ECS location for the production of the 30 millimeter or larger mesh, which is our potentially severe class. And we evaluate this skill with k-fold cross-validation, which I'll go over in the next couple slides. Before that, though, just looking at a bit of a sanity check of how our neural network predicted maximum expected size of hail is changing relative to a validation set. So we have the actual maximum or the actual mesh on the y-axis, and then we have the predicted likelihood on the x-axis, and we see that the neural network is assigning highest likelihoods to storms that have the greatest mesh sizes, which is assuring. More specifically, we're looking at the actual skill metrics. We did a k-fold cross-validation approach where we train on 4 years of the data set, validate with 1 year. Then we rotate that holdout validation set through all the years. So we do it 5 times, and then we average the final skill across all those evaluations. And the table summarizes the various skills that we can come out of that. And at the very top, we have GOES 13 and ERA 5. Combine together those inputs to come up with a rather, I'd say, decent prediction of occurrence of the potentially severe mesh with pretty good probability detection. False alarms doing decently well. We're both having a pretty good performance in recognition of non-events as well as positive recognition of positive events, which are kind of 2 distinct flavors of false alarm that you might investigate. And this results in rather good high-key skill score of above 0.36 and CSI of 0.55. So it's not doing too bad. And if you compare that to the third row, which is the same thing, but with MERA 2, it's rather comparable. You can also compare the second and fourth rows. That's ERA only or MERA 2 only. There's no satellite input there at all, except for the initial identification. I mean, you see that skill is rather comparable between the two as well. So there seems to be no significant difference at this point between use of those reanalysis products, but both are outperforming, interestingly enough, when you have just satellite on its own with no environmental input. So it seems that that environment is rather useful in painting the greater picture of what is going to be a likelihood for higher mesh. I will point out, though, that because we are evaluating this at already predetermined ECS locations from the satellite, the reanalysis results are biased towards areas of convection that's already occurring. So there might be a little bit of boost in the skill that the reanalysis on its own is getting from that. And then the GOES 16 results have a rather good skill as well. And remember that those were using a scaled neural network for GOES 13 applied to actual GOES 16 data. So if we aggregate these results from the neural network with our overshooting top climatology for 5 years or our embedded cold spot climatology for 5 years, those headers got misaligned, but the right-hand side should be the overshooting top and the left-hand side should be the embedded cold spots. For larger severe hail or smaller severe hail as determined by a likelihood for the neural network to predict, and that kind of tracks with the box of whisker plot that we saw a few slides earlier. We see hotspots occurring where one might expect, and that changes depending on whether we have a higher or lower probability from the neural network in the Central Plains and northern Gulf Coast in Florida. But also we see it popping up in the Sierra Madre in northern Mexico and along the Gulf Stream off the East Coast there, which is outside the view of what radar had, but is coincident with what the microwave data have. So that's a little reassuring that we're getting corroborative results there. If we focus in on a specific case study, and we looked at multiple case studies, but here's a particularly severe and deadly day that occurred in May of 2017. We had very widespread areas of overshooting convection, very expansive areas of cold cloud tops, high OT probabilities. And what we see is that the most prominent cells are generally occurring consistently with areas of greater than 50% likelihood of severe hail as predicted by the neural network. So the neural network's doing properly estimating a pretty good job of estimating the high likelihood of mesh, where we saw high mesh as well as storm reports, tornadoes, and hail at the ground. You might wonder, well, we can look at GOES 16 at the same case. That's in 2017. We had GOES 16 available. So first, we want to understand what the kind of parameter sensitivity is difference between GOES 13 and GOES 16. As you might expect, GOES 16 is going to see colder pixels, or just overall colder measurements because its pixel size is smaller. But it's going to see larger aerial coverage of things like the OT area or the ECS because of the smaller pixel size, which is illustrated here. So when we apply even a scaled neural network to the GOES 16 data, we get results from GOES 16 they're much more amplified compared to the GOES 13. There's higher distinction from the GOES 16 based likelihoods shown here, but it's kind of reassuring as well, kind of demonstrating that satellite is important in really highlighting the streaks of where higher mesh is occurring. The mesh value is on the right hand side. I just realized that the headers are also messed up here. The left hand side is GOES 13 mesh. GOES 13 based likelihoods, which we saw on the previous slide. In the middle to our GOES 16 based likelihoods, the left hand one is 1 minute GOES 16 scans, and the right hand one is 5 minute GOES 16. And that's compared to 5 minute mesh that's on the far right hand side. So just kind of draw attention to the fact that streaks in the GOES 16 data are more tightly aligned with the mesh streaks. And we're seeing fewer points in the GOES 16 predictions that are outside of outside of areas that also had a concurrent mesh measurements. So there's, although the magnitude of these GOES 16 predictions might warrant further study, and we certainly would want to train a neural network with actual GOES 16 data rather than scaling it, the aerial coverage of the GOES 16 is more comparable with fewer false alarms to the actual mesh results. So I'll just briefly talk about the summary slide here, but I think this is maybe a novel approach that it uses the satellite data to first pinpoint where we want to look, and then coming up with an estimate for the severe hail at that location. What we want to do is develop a very long record, as long as possible, highest resolution as possible, of combining satellite and reanalysis to come up with a predictive scale of severe storm likelihood or severe hail likelihood, and take that across the globe where satellites can see in regions that don't have good radar coverage. And in those cases, perhaps use the microwave radiometer hail probability as our truth, and do this in continued support of work done in partnership with reinsurance and insurance agencies and their CAT model development purposes. So thank you. Got through it, so appreciate your attention.
We'll take one question if there's a question. We have a hand up virtually, so Tino, go ahead and unmute, and it's all yours.
So may I make my question?
Yes, go ahead.
Okay, I'm Tino from Italy. I want to make my congratulations to you and Chris and all the group, because it is really a wonderful work, a long job, and with very good result. My question is, if I understood correctly, you said that the parameters from satellite are more useful and are enough to do this forecast than using also parameters from environmental derived from air analysis and so on. But if this is true, it means that this method works only for nowcasting, for when you are really near, close to the event, and you have all this nice feature from satellite. You are already seeing the storm. Instead, if you find something that have a skill also from the environmental parameter, you can try to do a forecast in short range, or also for 1 day, for example. While your method now, I see, can work only in very short range. And 30 minutes, something like that.
Yes. Well, first, let me clarify something. Maybe I wasn't clear. I want to point out that the best skill comes from the combined use of reanalysis and satellite together. Either one on their own didn't offer as good a predictive capability or estimation capability as using them together. I think both are important. The satellite is important for identifying where the features of interest are occurring. But the satellite alone in the neural network, even where we know where features are occurring, wasn't as skillful as combining that with the reanalysis. And then the second point, yeah, this isn't, you're correct. It's not really a forecasting tool. It is more of a nowcasting application, because we have to have the satellite observation to start with. There has to be an OT, there has to be, or at least a cold spot to be able to tie this to before we can make the neural network estimation. But this, has usefulness in we want to expand globally in estimation of climatological patterns of hail occurrence or likely hail occurrence.
Okay, so it is more a diagnostic tools than a forecasting tool.
Right, not a forecasting tool.
Okay, thanks.
Thank you.
Thank you.
Thank you.
And we now have David Gagne. He's going to talk about an intercomparison of real-time machine learning hail guidance.
All right. Good afternoon, everyone. Last talk of the session. We're going to now move from the nowcasting diagnosis realm to the forecasting realm and see how a few different hail algorithms perform. So let's forward. So the motivation for this work is that over the past, say, 6 years or so, we've gone from having basically one machine learning hail forecasting algorithm applied to convectionaling models to a whole suite of them that have been running in the NOAA hazardous weather testbed. This is taken from one event in 2021, and you can see we have kind of everything ranging from simple statistical calibration to deep learning methods, different random forest flavors, also applied to different models. So we have models with the href. We also have machine learning on the GFS and the HER. And they all kind of highlight similar areas, but each have their own kind of characteristics of where they're saying hail is and where hail isn't. So I think one of the big questions is, with all these different flavors of machine learning going on out there, which algorithm performs the best in different convective regimes and different times of year, et cetera. But also, what aspects of the hail guidance approach have the biggest impact on performance? Throughout the talks, especially in the session, you've seen a lot of emphasis on which parameters should you use, which kind of data source, how good are your labels, which algorithm, and these are all, I think, very important questions, and more importantly, where should you focus your attention? For this particular study, our data, we're pulling our model input data from the NOAA High Resolution Ensemble Forecast System, versions 2 and 3. It's run at 3 kilometer grid spacing over the continental US. We have 5 different dynamical cores that go into it, plus times 2 initiation time. So it uses like the HER, there's like an FE3 core, that's like the NSSL WRF. It's a kind of ensemble of opportunity is the polite way to call that, plus a time lagged ensemble that goes into it. It's performed really well in various tests of the systems, so it's one of the stronger ensemble systems out there. For our particular evaluation period, we're focusing on May 3rd through July 31st, 2021. We started with the hazardous weather testbed spring experiment period and then kept the models running through the summer. And we're focusing on Storm Prediction Center convective outlook time period, so the 24-hour period from 12Z to 12Z each day for the US. Our labels, we're using the NOAA storm report data set for this particular verification. We have mesh data for this whole time period, and I want to do the evaluation on that too going forward. So there's three different machine learning models in this comparison. I'm not going to go into all the details of how each one works, but the key thing to note is that the different ones have different levels of pre and post processing associated with them. So the Burke random forest does an object-based approach, extracts a whole bunch of environmental parameters and storm parameters, throws all that into multiple random forests, which then produce your probability of hail and hail size distribution. That has to be then upscaled from the individual storms to a kind of neighborhood probability. So there's multiple steps of calibrating that and smoothing that go on. On the other hand, the Loken random forest, which also uses a random forest, but does a very different pre-processing approach. The big thing it does is it averages and smooths everything out from the convectionality models. So instead of dealing with hour by hour forecasts, it just like takes all this data and flattens it out. And then so you have means of things like updraft helicity and shear and cape and whatnot. And the model itself is run on an 80-kilometer grid that is then linearly interpolated back to a 3-kilometer grid after that initial running of the random forest at 80 kilometers. So in some ways, it's kind of ignoring the really high resolution aspect of the data, but we'll see if that becomes a strength or a weakness in the results. Finally, we have the Burke deep learning method. So this, instead of using a random forest, it uses a kind of neural network called a UNet, which is used for image-to-image translation. Instead of giving it the whole suite of convective parameters, we're only going to give it geopotential height, temperature, dew point, and UNV at 850 and 500 millibars, and try to let it figure out how those are all related to each other using its deep learning magic. This is also trained on mesh, but by kind of a pixel by pixel basis. And then we like have it make its probabilistic predictions and then use a neighborhood smoothing and averaging across different ensemble members. So now we're going to start by looking at a few case studies. The kind of comparison points, Loken RF is in the upper left corner, the Burke UNet is in the upper right, the Burke random forest is on the bottom left, and then the SPC outlook is on the bottom right. The black dots show you where the hail reports are for each case. Some things to note from the different models that'll become ever more present is the Loken random forest has a much larger area where there is non-zero probability compared with both the UNet and the Burke random forest. It generally covers more of the hail reports. As a result, the Burke random forest tends to be a bit more confined, but it's also missing some events as a result. And the UNet also has a slightly different coverage of reports. So like it gets the report in Wyoming that the Burke random forest missed, but it doesn't have any probabilities over on the East Coast. And they all kind of align pretty well with the Storm Prediction Center outlook for this event. We can go to pick another case. This one, we also get pretty good coverage from the different methods. The UNet is kind of interesting in this case because it separates the Iowa probabilities from the Indiana hail probabilities that kind of the SPC and the Loken and the Burke random forest method all link together. Overall, they generally, again, pick up on the main hail area, but then kind of have variations and struggling on some of the other secondary hail areas for each of these days. Show a couple more examples. This is a 8th of July case, kind of in the northern plains. All of them kind of capture the main swath of large hail reports, but the extent of their probabilities, again, vary quite a bit. And some of them also have mixed coverage of hail going on in the east. And we'll show one more of that. And again, we see a similar pattern, but then it misses some hail reports that are going on kind of in the southwest. So the algorithms are doing pretty well. They're aligned with the humans. Sometimes they pick up on things the humans don't, but they're not perfect. So how does that translate to overall verification? So on the left, we have a performance diagram. Ideally, you want to be in the upper left-hand corner. Everything's sort of on the closer to the bottom right, but we do see some stratification across the different models. The colored bars are the bootstrap confidence intervals resampled by each day to give you a sense of the uncertainty of these metrics. The purple line is the Loken random forest, which consistently does the best in terms of discrimination and reliability. The SPC forecasts are the light blue and dark blue lines. They're kind of in the middle. And then the Burke random forest and Burke deep learning are both about the same level, kind of on the trailing end. in terms of reliability, which is shown on the right, all the methods basically show that they have a higher relative frequency as you increase probability, but the how close they are to the one-to-one line varies. One thing I find interesting in this diagram is that SPC is generally overconfident at lower probabilities, but then becomes underconfident when they get to the upper end of their probability range. So they may be a little bit overly conservative in issuing those really high hail probabilities. Otherwise, the random forest is fairly well. Like at low probabilities does pretty well. The Berk one, it tends to be overconfident at higher probabilities. If we break this down by month, we see some other interesting trends happening. The Loken method is consistently high area under the rock curve and Breyer skill score, and consistently higher than the SPC outlooks for the same time period. All of them show a kind of decreasing performance going into the summer, which isn't surprising. The Berk random forest has a lot of variance in its Breyer skill score going from May, where it does pretty well, to June and July, where it basically loses all reliability. One thing that may be causing this is that the method was weighted toward cases that happened in May in the training process. So that seems to be bearing out where it helps it improve in May, but then it worsens performance at other times of year. Eric Loken, one of the co-authors on the study, did a deeper dive into looking at the parameter space of verification. So we're looking at SHIP, the severe hail parameter, versus maximum updraft vertical velocity on the y-axis. What we see here is basically hail is more common as you get into the high max UVV and high SHIP space. But we wanted to kind of look at how each method did across the space of parameters. In our data set, we have most of our cases are still confined to the lower end region, but we do have some representation for the higher ones, just relatively infrequent. Kind of looking at some of our different models in the space, we have, let's see, the general pattern we see in this is that the models do pretty well, and when you have strong updrafts and high SHIP across all the methods, but then when you have low SHIP but strong updrafts, all the methods, but in particular the Berk random forest, do particularly badly. The SPC seems to do a bit better in that regime, so they seem to be better able to like when there's strong updrafts but not the greatest environment, seem to pick out those events a little bit better than the other methods. And kind of point this out here again in terms of relative to the SPC in terms of the scores. And then the Berk method has mentioned tight gradients in its performance, so it has good sharpness, but there are also cases where the probabilities are higher, but no reports were received. So there were definitely cases where it had confidence, but no hail was reported. So the kind of the takeaway with some of this is that performance is relative in different regimes, and the Berk method being key to more on storm objects that can improve its performance and look at the probabilities, but may result in missing some of these kinds of events. Another way to look at this data is to actually use kind of a meta machine learning approach. So I wanted to kind of see, given these different approaches, where are they focusing their attention in terms of the input space? So what we did was fit a random forest basically from smoothed inputs from the average fields from the href to the probabilities coming out of each of these methods, including the SPC. So we can actually get a sense of what might the emulator of the SPC model consider important versus the emulator of all the machine learning methods. Some interesting patterns shake out of this. One is that the SPC at both timeframes considers updraft helicity really important, as does the Loken random forest method. The Berk random forest and the Berk deep learning method, on the other hand, they focus on other things. They really care about updraft speed, and Berk random forest in particular really cares about CAPE, whereas the other ones kind of discount that a bit more. The Supercell composite parameter was also particularly important for all the methods. We can also look at this a bit further, something called a partial dependence plot, where we can look at the sensitivity. So the key thing to look at here is where is the slope of the line really long versus where is it flat? And so we see that in terms of discriminating low versus high probability hail forecasts, updraft velocity, all the methods have a similar slope to them, but some have a basically higher range in their changes than others. Most of the methods agree with their general slope. It's just like how much they emphasize each one is a little bit different. But this kind of allows us to get a sense of which the Loken method seems to be closer to how the SPC is important things, whereas the Burke-Random Forest and Burke-Deep-Learning methods are focusing on different things, which may be useful in a forecasting context to help capture threats that may not be as maybe out of the line of thinking for the forecasters. So diversity in ensembles, even if they aren't the most skilled members, can still be helpful in getting overall performance better. One other thing I wanted to advertise here, because there was a lot of talk about storm mode and how it ties to hail. I've been working on a project using machine learning to predict storm mode from basically the high resolution rapid refresh data. We've done some analysis of comparing the predicted storm mode given a certain storm mode, what's the probability of different kinds of severe weather reports? And what we found with this is that there is a very different conditional probability between supercell and QLCS, especially for hail. It's consistent across different methods we've tried on this. We also have, the data is all currently available. We have a nice little web viewer so you can go look at different cases from the past spring and summer if you're interested in seeing how storm mode varies. And also if you're interested in a bunch of storm objects, I have a big data set of these from the HER, and there's code to generate more if you're interested in that. So in summary, some lessons learned from this. The Loken random forest method consistently outperformed the other machine learning models and even the Storm Prediction Center outlooks in terms of discrimination and reliability. Of the different modeling components, the pre-processing, I think, is where a lot of the key differences are made in these methods. So we saw a big influence on smoothing the probabilities together over time and space, or smoothing the inputs over time and space really seemed to help the performance. Adding lots of different post-processing steps seemed to be a diminishing return approach and adds complexity to the system. So this is one of those talks where even though where basically I'm saying my method did the worst in this, and there's some interesting lessons from that. I do think there's some value in potentially doing XAI on emulators, so you can use it in more of a descriptive mode than a forecasting mode, and that might allow us to get us insights into into not just like one forecasting system, but comparing across different forecasting methods. So with that, happy to take questions or talk to people over lunch. Thank you.
We can take a question or two. If anyone online has a question, raise your hand in the Zoom. Anyone here?
Really interesting stuff, DJ. Nice work on this. Question about the interesting kind of peaking up of the updraft helicity, right? It's updraft speed and vertical vorticity. Mm-hmm. Which, do you think it's more of an indicator of the storm mode that they're picking up on? Because taken by themselves, neither one would be necessarily great for hail production. So can you comment on that? Yeah,
I've seen some of my other work too, that updraft helicity has a pretty strong discrimination skill at picking out severe hail. I think some of it is it's picking out supercells, but there's also you can get high UH and squall lines, especially when they're transitioning from supercell to that linear mode. And often in that case, you can get the big wind-driven hail, or where the storms are merging with each other and stuff. In my 2019 interpretation paper, that signal also seemed to pop up in the broader fields. So I think there's definitely more going on there. What was interesting with this particular work is that it was actually averaging the UH across different fields and smoothing it out, and that seemed to improve the signal from UH. So I'm not 100% sure where's the causal mechanism. My best guess is that by smoothing it helps account for the inherent uncertainty in where storms are occurring in the cams, because they're often all over the place in the cams. So the fact that strong storms are happening somewhere is probably the most important signal to get from the cams, not the explicit structure of the storms. But from the storm mode stuff, there does seem to be some information there too. So I think there's a lot of data to, like, we now have all these cam runs. I think there's more secrets to unlock by digging into them further.
One more question? If not, thank you very much.
Thank you.
All right, if you haven't noticed, it's 50 degrees and raining outside. It's not exactly conducive to eating outside unless you're into that. That's cool, but we don't have a lot of tables down here. There's a cafeteria up on the second floor with a lot of tables. So if you go up the stairs or up the elevator to the second floor and across the front of the building, there's plenty of extra seating in the cafeteria up there. We'll be back here at 1:20 with a keynote from Wayne Sand talking about flying through hailstorms.
Okay, we're going to start. I am personally thrilled that Wayne agreed to give a talk today. Wayne, I met Wayne during the Henry days, and he was the T-28 pilot and has some very interesting stories to tell us. Wayne got his PhD in atmospheric sciences from University of Wyoming, and this week he's been teaching some classes in California, I think. So with no further delay, I'm going to have Wayne give us a really interesting presentation.
Well, thank you, and I truly hope it's interesting. It's some interesting history, I think, and hopefully put some things into perspective along the way. And Dandy talked to me a lot about, and we were good friends throughout the Henry days, and there's some good memories from back then, and I always like to look at some of the history of things. And I kind of view this as a bit of a history lesson because it's interesting in that the airplane we used back then, the T-28 out of South Dakota, was new and is now new at the time. It certainly wasn't a new airplane then, but it was a new design, and I'll tell you some about the development. But the fact is it's retired now and in a museum in Omaha, Nebraska. And so it kind of puts things into perspective a little bit. It's been a long time. The work I'll be talking about, and a lot of the flights I will be talking about happened in the 70s, and so a long time ago. So with that as a little bit of an introduction, and I'll elaborate on some of what I've been doing since as we go through here, but suffice it to say this was a very memorable part of my career, and I'd be eternally grateful for the opportunity I had back then, but it was unique at the time and probably still is. So I give you a little bit of background. Back in the 70s, some things were happening, and I'll give some of my background to precede this. This was Vietnam era stuff, and in the 60s, I was in college and trying my level best to avoid the draft without success in the end, but nonetheless, once I finished my bachelor's degree, I was looking to go into the military because I knew it was inevitable. And I took a job for the summer to go to Colorado to fly for the Colorado State University. Had a hail research project going on back this was 64, 65, 66 time frame. And Dr. Dick Schleusner was in charge of this program, and I just went there to fly for the summer because I was a pilot at that time and had worked on building cloud seeding generators for Oralos, the guy who invented and held the patent on the acetone burner to seed clouds. And so I knew how to work those. I was a relatively new pilot, but I'd been checked out in T6s, and so I went there as, quote, the local expert, 2 years, 1 year out of college, whatever it was. But at any rate, once I got there and we did a summer, Dr. Schleusner offered me the opportunity to stay and fly for them for for the foreseeable future, and furthermore offered me a graduate research assistantship to go to school there and pursue a master's degree, which hadn't been on my horizon at that point, needless to say. But to make a long story short, I did that for a couple of years, ended up going into the military, flying in the Navy for 5 years. And then at the end of that 5 years, Dr. Schleusner had said, hey, if you ever need a job or want to come back and finish your master's degree, be sure to call me, which I did when I was in Spain. Called and said, hey, what are the chances of coming back to school? Because by then he'd moved to the South Dakota School of Mines and started a graduate program up there in atmospheric science meteorology. And he said, boy, you called at the right time. Not only do I have a position for you to go back and finish your master's degree, but I will give you a full-time job flying an airplane. And I was, well, that sounded good since I've been flying for 5 years. And well, I've been flying since I was a teenager, basically. But at any rate, he said, come on back here and we'll have a good deal for you. And the question was at that time, and this was the National Hail Research Experiment, was just beginning. And there was a theory at the time advanced by the then Soviet Union, which basically said they were successful in hail suppression efforts, they claimed, and their theory was that there was an accumulation zone of super adiabatic liquid water in the center of thunderstorms, and they were firing rockets into that key target area and claiming some success. And the scientists in the United States, and especially the National Science Foundation and those who were involved with ENRI at that time, said, well, we're not so sure, but we need to go look, basically, and hence the innovative idea of, hey, we need to build an airplane that will go look into these places and see if, in fact, there is a super adiabatic liquid water content, and we need to understand the guts of hailstorms a little bit more. So they set about getting this T-28 and armor plating it so that it could fly into hail. And the idea was that it could fly into hailstorms with hail up to 3 inches and come back without significant damage, but routinely fly in 3/4 inch hail, which is what we ended up doing. And the idea is to come back safely, but then they needed somebody to fly it. And prior to the time I arrived on the scene, they'd had nothing but trouble with the airplane. And I arrived at the South Dakota School of Mines, fresh out of the Navy, flying brand new A6 intruder airplanes in Vietnam, and saying, hey, I think I could do this, because I was flying the T6 before I went into the Navy, which was a similar radial engine, old military trainer type airplane. And I think Andy will probably remember some of the conversation at that time, actually, because I've had numerous people approach me and say, you have got to be out of your ever-loving mind to be doing this, because it's just so dangerous. Who in their right mind would fly into hailstorms? And my response at the time was, well, wait a minute, guys, I just finished flying in Vietnam, where I'd take off from an aircraft carrier in the middle of the night. People would shoot at me, and I'd end up landing back on the carrier in the middle of the night again and dropping bombs in the meantime. And this isn't bad compared to that. I thought it was kind of not a big deal. But at any rate, I was young and dumb and didn't know any better at the time. So I proceeded and took this position, and hence started flying the T-28. And here's what that's a little bit of background. And I want to talk some about the airplane modifications that we did at that, actually most of which were done before I got there. And I kind of finished them up with some mods that I'll talk about. But when I got there, the airplane had been modified to withstand hail, but it lacked a bunch of the other modifications that really needed to be a reliable airplane. So I want to talk about that a little bit. And the National Hail Research Experiment was going on full bore, and or I shouldn't say going on at that time, it was really just getting started. And I want to talk some about instrumentation, because we had some kind of unique gadgets on the airplane and that we used in an attempt to make some key measurements inside thunderstorms. And then talk about some of the experiences and sensations of flying through thunderstorms. And then I want to talk about some of the results. Well, I haven't changed much in all those years. Back in the T-28 days, I kind of looked like this. My hair was a little bit darker and didn't have to wear glasses. But outside of that, I haven't changed a whole lot. I want to talk a little about the airplane modifications. Like I said, before I got there, they had put mods on the airplane to make it look like this, basically. And this was kind of an after into the program type picture, air to air. But this is what the T-28 looked like for those of you who might not be familiar with it. It's a big old military aerobatic trainer. So it was stressed in a carrier. It was capable of landing on carriers, and it was tough enough to do aerobatics and get horsed around by student pilots learning how to fly high performance airplanes. And before I got there, the airplane had been modified. It was originally an Air Force airplane, and it had been modified from the original 900 horsepower engine to a 1200 horsepower engine. And they had then put armor, I'll show you pictures of this in a second, armor plating on the leading edge and on the cowling and the canopy, and made a few more mods to the airplane. But at any rate, it had a 1200 horsepower engine, and the South Dakota School of Mines and Technology had put on a fresh one of these engines after an engine failure before I had arrived. And so when I got there, the airplane had a fresh engine. The problem is that the rules in South Dakota at that time were you will buy these when objects become such and such expensive, you will buy from the lowest bidder. In other words, they required bids. So they had the lowest bidder engine hung on this airplane when I arrived, and I flew it for a few hours, promptly had an engine failure. And so we put on a replacement engine, again, from the lowest bidder. I flew it for a few more hours and had another engine failure. And then we really got serious about this whole thing. But let me talk more about that in a minute. First of all, I want to talk about some of the modifications to the airplane. Well, with the normal curved windshield in the airplane, the concern was that the 3-inch hail would come through the windscreen, which it certainly would have. So they put on real small flat pieces of 3/4 inch, I guess it was officially called stretched acrylic, but plexiglass basically, and fired 3-inch hail balls against this thing to see that it would not come through the windshield. And while I'm thinking of it going by here, I didn't trust this. So whenever I flew the airplane into hailstorms, by the way, the seat had an incredible vertical stretch to it, to the point that I could lower the seat enough that the top of my helmet was just barely above the glare shield. So I really couldn't see anything forward, nor did I need to, because there really wasn't anything to see. Side panels were done the same thing in the canopy, just big pieces of flat in there, and allegedly to beef up so that if we in fact did fly into 3/4 inch hail or 3-inch hail, I'm sorry, and it did happen to come through the windshield, it wouldn't get you. Okay, here's can you all see my pointer on here? I can't tell I don't really. I see a no and I see a yes. No, okay. Well, let me talk about it then. The cowling around the engine was especially vulnerable, they thought, when they first designed this mod. So they put an 1/8 inch additional doubler on there, if you will. So this is added plating, and you can see the weld seams along here. This is the intake for the air cooler or oil cooler, I'm sorry. And so they were concerned about big hail going in here. So they put a grate on that was designed to break up the hail before it went into the engine intake and not do damage to the oil cooler. And what else? Oh, the pushrod housings. This is the radial engine pistons. The valves were up on top of the engines, and there were push rods came up through these tubes. And so they put plating. You can see actual hose clamps to attach a piece of pipe on top of the pushrod tubes to keep it from breaking. And the same thing with the ignition harness here. They put a cover on that to keep it from being damaged. One of the other mods they did to the airplane to protect it from hail was put this big cover on the propeller governor was sticking right out front, and they thought it was fragile enough that it needed protected, and it probably did. It was not a very strong cast piece that housed it. Same thing on the air intake to the engine grates up here again. And one thing that really helped here, by the way, if you're familiar with ice protection on airplanes, we didn't have very much de-icing, anti-icing equipment on the T-28. The one thing that it did have was an alcohol dispenser on the propeller, which used alcohol instead of electric heat to keep the ice off the prop, which was an old technology, but turned out it was quite effective because it also de-iced the vanes on these intakes and kept the cowling fairly clean, and actually helped keep the windshield fairly clean by the alcohol that was slinging off this propeller, keeping it clean. So all of those mods were done to the airplane, and the leading edges were the big ones. And they put a 90 thousandths doubler on the leading edge, 90 thousandths thick aluminum plate, and hence getting the armor plating. It goes from here to somewhere on top of the wing, back towards the spar again. But suffice it to say, with all of this armor plating on the airplane and protection, it withstood encounters with hail quite well. The only thing that we had trouble with, let me back up a slide, were these cooling fins on the cylinders themselves. They were a little soft, and they frequently got dented up. And we frequently got in there with a pair of what's called duckbill pliers and straightened these out. And we actually, in the course of the time I was flying the airplane, had to change cylinders once in a while because those got so bent up that they weren't effective anymore, and we had to replace the whole cylinder for damage to the cooling fins. Okay. Enough about the background and the armor plating on the airplane and so on and the mods. And then when I started flying it, as I said before, we started having some problems with the airplane, and I'll go through those fairly quickly, hopefully here. But here's one of my landing sites. After an engine failure on the airplane, we ended up putting it on a road. And this is because Andy wanted to hear about some of the adventures here. The fact is that I was flying right smack over Rapid City, South Dakota, when the engine self-destructed from the inside out. And it was shaking so bad that my first response was I've been trained in how to parachute out of airplanes. I blew the canopy open and was preparing to get out of the airplane because I thought the engine was going to physically depart the airplane. And I finally got the prop slowed down enough to decide that it wasn't going to do that. I saw a highway south of Rapid City, and there was very obvious I couldn't make it back to the airport, even though it was quite close. But I chose to land on a highway. And here's my landing spot with the 3 skid marks indicating the 3 landing gear. And the fun thing was when we were towing the airplane back down the road, the guy driving the truck tug stopped and said, "Hey, we're going to have to take the signs down." And I said, "No, it'll fit." Because I had gone this sign, the wingtip just barely passed through it, landing on the highway. So again, one of those fortunate things, but again, landing in the middle of the road kind of helped. And here it is sitting there in all its glory. At that point, oil running all over the place. And here's what happened is the master rod, again, this is probably more than most of you want to know, but the master rod on this engine broke as near as we could tell, which broke off a whole bunch of other connecting rods. These are what's left of pistons. Some of the rods are broken completely off, as you can see. And here's what happened to at least one of the cylinders. One of the connecting rods went right up through the side of the cylinder, and hence all the vibration that was taking place in the engine. And it was definitely a bucket of bolts at that point. So we ended up saying, because I had just gotten out of the Navy, the guy in charge of the NCAR flight facility was an ex-Navy guy. We had good contacts with the National Science Foundation. So we got an agreement with the Navy to run this airplane through the Naval Air Rework Facility at Pensacola, where they rebuilt T-28s for the Navy. And so we disassembled the whole airplane, put it on a truck, hauled it to Pensacola. And here I am doing some fine tuning on something with this small hammer here. And we had it rebuilt. And what they did in Pensacola is they had it down there for, I don't know, a few months. I don't remember the amount of time now, but they really did a mod on the airplane. And one of the issues I had with it is because it had been modded from 900 horsepower to 1200 horsepower, they put additional fuel tanks in. And they were all independently selectable, and the fuel management was an absolute nightmare in the airplane to keep it from running out of fuel, which it did frequently because I wanted to get every single drop out of a 15-gallon tank for an engine that burned 50 gallons an hour. It took a lot of attention to fuel management on this thing. So we had them put in a whole new fuel system with a simple on-off switch for fuel. The landing gear, because we decided also to upgrade to the Navy's type engine, which was 1,425 horsepower, get another 225 horsepower out of it. And so we had the best engine built that we could find and no longer went to the lowest bidder. And based on a discussion that Dick Schleusner and I had in the middle of the highway with this thing dripping oil all over the place. But nonetheless, we got a good engine on the thing, and to put that on, they had to replace the whole nose gear torque box and the nose gear, and ended up replacing all of the landing gear on the airplane for us, doing a bunch of structural mods to beef it up to Navy T-28B standards. And this is sitting on the ramp at Pensacola when we took delivery of the airplane back from the Navy, and finally got it to work. So this got us back into ENRI. So what ENRI was trying to do, and most of you hopefully know this, but they were interested in hail suppression potential. They had, as part of it, it was a random cloud seeding experiment. Some of it based on the Soviet theory of this accumulation zone. And they wanted to take, as part of the experiment, wanted to take these in situ measurements, which was the T-28 basically. And I think that's all that was in the cloud at that time. There's some around the edges, but not much. We were the ones that were really tasked with doing this. And it was a real developmental period for radar also. And so a lot of radar measurements were taken, a lot of ground network out there to measure hail, precipitation on the ground. And so it was a fairly large effort, and Andy can tell you all about that probably in at least as much detail as I can. Talking some about the instrumentation, and I wanted to include this to just give you a perspective on some of the ideas we had back then. But this was a hail sensor, and it was a momentum device that had a pressure transducer behind it, and it was designed to measure the strength of the thump if you encountered hail and count and size hail. So that was the purpose of that device, and we carried it for a while. One we carried a lot was a foil impactor. This door opened, and there's a little serrated drum back there with a roll of aluminum foil. that cranked it from one drum to the other at a certain rate, and in essence gave you two-dimensional images in the impressions on the this serrated drum that this aluminum foil was going across. And then some poor unsuspecting graduate student got to size and count all of these things, which was a horrible job. I looked at it some, but I will have to admit I didn't do any serious analysis of this stuff because it was pretty awful. One of the big questions we had that was trying to be addressed at that time was this accumulation zone theory again. So Tom Kyle from NCAR developed this device to look for really high liquid water content. Basically, it was an evaporator. He measured the amount of, if I remember this right, the amount of energy required to totally evaporate the water that went into this little hole, and it was a device to measure liquid water content is the whole purpose of the thing. Tom and I are guilty of publishing a paper that actually got it published that said we found superadiabatic liquid water, but on further study, it was an instrument error and we didn't find it at all and never did find it. Here was another relatively new probe at that time. It was a temperature sensor, reverse flow, again, to keep the supercooled water and ice off this thing. The idea was the air would come in the back of this tube, go forward and come out these little prongs, and you can see some hail damage to this thing from flying in these kind of storms. We put some of the first particle measuring systems probes were put on this airplane. We started measuring the cloud droplet sizes and concentrations, of course, with the FSSP and two-dimensional probe. We measured ice crystals. Then we had these unique little gadgets up here where we would capture samples of water, bring them back for analysis, and actually look for silver iodide to see if we could detect any of that. Again, very laborious, time-consuming kind of thing. And in the end, I'm not sure got us any real results of consequence. Here was another probe we flew for a while. It was basically monstrous 2D probe with this was the sample area or sample dimension in this axis, and it just had a whole bunch of sensors in here, and it shined a laser light across between the two pylons from this pylon to this pylon, and it shadowed the sensors over here, somewhat like a 2DC. It worked very similar to that. But it was large scale, looking for hail again. And again, some data, not a lot. And then another scientist from NCAR, Ted Cannon, designed this camera. He was really into photography, so we flew a camera system with a strobe, which was designed again to take pictures of hail. And some of that data is around. Well, some of the experiences that I thought you might be interested in is hail. First of all, that was the object of the exercises, to study hail. So did we get in any? Yes, a lot. I mean, we routinely would fly into 55 dBz reflectivities. That was acceptable. And if we accidentally got into something larger than that, the airplane was supposedly designed to deal with it. The 55 dBz at that time, we were equating to 3/4 inch hail, which has turned out to be about what we would routinely encounter without worrying about it. Once the radar operator on the ground determined please message me. I'm not sure what that message was about, but at any rate, let me continue I kind of lost my train of thought. But at any rate, the radar operator would set up a path through here, and we would target the most intense part of the storm. Once he gave me a heading to penetrate the storm, unless I really freaked out and panicked, I just lowered my head and charged forward. And I didn't deviate from a heading. So I tried to eliminate as many variables as I could and eliminate as many balls in the air as I could, if you will. So once I started, I just went straight ahead and maintained a heading and just took what hail we got. Turbulence, It's a question that's often asked: how hard and how severe was the turbulence? The best way I've ever found to describe that is that I spent most of the summer with black and blue shoulders and black and blue straps across where my lap belt would go across my waist, because it did pound you around really, really hard. And I flew the airplane by myself, so I didn't have anybody else to worry about. But it thumped you around really hard in the airplane. But as far as G's go, they were not horrendous G's. I mean, we had a G meter in the airplane, and I typically got more G's on a hard landing than I did flying through the thunderstorms. But I'll talk a little about the technique that minimized that. Lightning, again, that was a real issue. With the T-28, it was almost a non-issue, however, because we took lightning strikes all the time. And it really didn't do much to the airplane. It had welded spots all over it on the wingtips and the prop and in the tail and trailing edges. And it was a pretty common event to get hit by lightning, but with that particular airplane, it was almost no consequence to it at all. We really didn't do much damage to the airplane outside of what I was talking about before, is the bent up fins, but it really survived quite well, I thought. And I've already talked about this, but the flying techniques are probably worth a mention, because what I decided you really had to do here was that attitude was important and airspeed was important. And like I said, heading was important. Altitude was not. And a typical instrument pilot, the command from air traffic control is climb and maintain a certain altitude. And that's what they try to do, is they go to an altitude and try to stay there. And that is absolutely not the right thing to do when you're flying in a thunderstorm, because we would see horrendous updrafts. 6,000 feet a minute was not uncommon. And so I would just ride it. I would try to keep the airspeed at maneuvering speed and just stay right there and take whatever I got in terms of altitude and didn't worry about it. A couple of the other things that I should add to this is icing was always an issue, because we were flying in the growing part of the thunderstorm. So we got a lot of ice on the airplane. And again, the T-28 was very well behaved aerodynamically. I've done a lot of work on icing since, but this airplane I never had a problem with controllability with ice, even though we had a lot on there at times. And the technique is I just waited until I got so much ice the airplane wouldn't stay at altitude anymore. I didn't have enough power to stay there. And I would just descend to a warm altitude, because there were warm altitudes below me, melt it off and go back and do it again. And that was our way of dealing with icing. Okay, I'll give you my take on some of the results from Henry. Andy and others may disagree with this, but in summary, I don't think we found any accumulation zone of super adiabatic liquid water to support the Soviet theory. I think it was, at least we couldn't find it, let's put it that way. And to this day, the stuff I teach and so on, I tell the people who are interested in icing that if you are finding values that are super adiabatic based on your analysis of the sounding, there's probably something wrong with your measurement probe. And so we found nothing more than adiabatic liquid water. And again, I'd worked a lot in hail suppression before I went in the military and been around it a fair bit. And the natural hail variability, at least based on Henry stuff, it was so overwhelming that it was hard to be conclusive about a seeding experiment. So I think basically they came out as inconclusive. That I think that's still the official word. I could be mistaken there, but some of the stuff we did learn. We learned a lot about thunderstorms, a lot about cloud dynamics, a lot about cloud physics, and we learned a lot about flying around thunderstorms with multiple dissimilar airplanes during a weather research project. And I flew later for the University of Wyoming for 12 years, flew their King Air, and some of the lessons that came out of Henry for operating were quite valuable in terms of working with the FAA, we developed techniques for talking to those guys and taking a plan to them that we got to do some really weird stuff over the years. And a lot of that came out of some of the lessons we learned in Henry, and I was very grateful for that later on. It was very, very useful. And weather radar, of course, this was when CP2 was being developed. And so I know the radar people learned a lot about weather radar. I learned a lot about how to use it. And I'll talk some about that a little bit later. We don't run out of time here. I'll keep moving. But I'm a real believer in radar and what it can tell you. And I think a lot of that came from here. Well, one of the other things I got out of it is I got data for my PhD thesis, which was kind of nice because when I finished at South Dakota and went to the University of Wyoming, it was because, number one, they wanted to hire me as a pilot, but number two, they had a PhD program, and I had the support from the National Science Foundation to do the analysis for my PhD and the money to do it, and I could do that through NCAR. So it was a nice win-win deal for, I think, everybody involved. And what came out of this was a conceptual model synthesized from microphysical and dynamical observations of a multi-cell thunderstorm. It was published as an NCAR tech note. And what I want to do is show you a few figures out of that to show you what my conceptual model is that I determined based on an analysis of T28 data and CP2 radar data. And I might say that the radar picture was much more detailed, of course, when I was doing the analysis, but this is a vertical section, and this was all done by hand based on slant range displays and interpolation and contouring and all that kind of stuff. But, you know, now we can do this kind of thing with a touch of a button. I spent months doing this by plotting it up in big charts on the wall and drawing pictures and so on. But at any rate, the conceptual model I developed a cross-section of the visual cloud, the anvil, feeder clouds, and in various parts of the 45 dBz contour, which I chose because that's typically what shows up red on an airborne weather radar, and it further augmented and supports the idea that for pilots to stay out of the red, and put in some other features here. But since I had the theory and the data supported it, that a cell started here as a small convective element can grow, and then and I have a figure that I use oftentimes where this is the cumulus stage, the mature stage, and the dissipating stage as you go from left to right across this figure. And so I think it fits very well with our classic model of a thunderstorm, but I also think it really points out what a multi-cell thunderstorm is about, how it works. And I've used this extensively now for icing work, saying that the icing is all in the left-hand part of the figure in those feeder cells. And I'll show you a little bit more about that in a minute. And this is the vertical velocity envelope. And again, show you that these cells out to the left, I'm sorry you can't see my pointer here, but the cells out to the left, these little feeder cells, yeah, plus and minus 1,000 feet per minute typically in those. Once you get into the mature stage of the storm, you have numbers at 6,000 feet a minute or 30 meters per second updrafts in those. And that's where we flew with the T28 to get these numbers. We would just march right through this whole storm left to right or right to left. And that was the idea, to measure everything. And in the end, I felt that I could distinguish between the different cells in the greater than 45 dBz part of the storm. And here's a liquid water content profile. And again, here, this has come to play most often in the icing arena, where this is maximum intermittent icing conditions in the left side of the storm, where you have peak adiabatic values, and this is the place you get truly adiabatic liquid water content in this part of the storm. Back in the right-hand side of the figure, in the 45 dBc contour, for the most part, this is converted to ice. There's not much supercooled liquid water in there. What's happened has already happened. And as far as it's a historical part of the storms, the way I think about it, and there's not much going on there anymore outside of turbulence, lightning, hail, and a very, very uncomfortable ride. So looking at some streamlined patterns, again, starting in the left-hand side of the figure, typically what you see is a downdraft, a very strong updraft, and then a downdraft, and so on through these individual cells until you get back into the 45 dBz contour area, where it's dominantly down air and dominantly very turbulent more than anything else. There really isn't a lot of up air here. Things are falling out for the most part, and the hail is falling usually right here at the edge of the first hail that gets to the ground is right at the edge of this, where the 45 dBz contour intercepts the ground. Is when hail starts arriving at the ground. And look at a plan view again at the altitude I chose here at 6.7 kilometers. And you see the individual cells starting at the left side, the little circles here. You see the updrafts surrounded by downdrafts, the stippled areas. And you can see those first three cells. And what I teach nowadays is for the icing people is that's where you want to work to get, good, heavy, max intermittent icing. By the time you get back into the downdraft area, this all the stipple stuff on the right and inside the 45 dBz. There's no icing to be had back there, but there's all kinds of potential to do damage to the airplane in the mature part of the storm. You don't want to be there. I mean, there's some good data to be had, but you don't want to be there. And again, here's the airplane kind of as I finished up with it and where it is, and it's my contact information. If somebody wants to get a hold of me, that's how you do it. I currently live in Montana and do teaching. I teach for the University of Kansas on continuing education programs, and do a lot of consulting with reconstructing the weather surrounding airplane accidents. That's what I've been doing since I left NCAR. So I've left myself no time for questions, so sorry about that. Seriously, it's your call. So it's back to you, and I can't hear you, so.
Okay. You should be able to hear me now. We have time for a quick question or two if anyone does have a question for Wayne. Good.
I'll ask the obvious. So what's going to be replacing this? I mean, there's got to be somebody with some deep pockets that can donate a craft and armor it.
Yeah. What the process has been, and I haven't talked to the people and the seats of power on this issue, but they've been trying to obtain a A-10, a Warthog, an Air Force airplane that is a ground air or close air support airplane, twin engine jet, and it's a real high left wing, very maneuverable, and is a jet. If they can make this work, that's what they're trying to replace the T-28 with. I think there's still lots of things to be learned from poking around inside these clouds. I thought they learned a lot. And of course, the airplane flew for a lot of years after I flew it, and continued to do this kind of work. It was in Europe for a while doing this kind of work. And, there's a lot of good data that came out of this after the original 5 years that I was with the airplane. And, but the A-10 is the proposed replacement for the T-28.
All right. Thank you very much, Wayne. That was incredibly interesting. Let's give him another round of applause, please.
Thank you very much for having me, Andy. I really appreciate it. And we'll talk to you again one of these times.
All right. So we will move on to our session. or resume our session, I should say. We have Matt Kumjan. He's going to be talking about two paradigms for radar-based hail size estimation.
All right. Thank you, Brian. Thank you, everyone. I'd like to acknowledge my co-authors on this work, former student Rob Schramm, Ian, who you all know, Josh Soderholm, Kelly Lombardo, and then Yuju. So everyone here in the room. So just jump right in and kind of discuss what we mean by two paradigms. And I think Witt and Nelson in 1991 summarized it eloquently, so might as well use their words. But basically, radar-based techniques for either detection or sizing of hail can be organized into two different categories. Basically, those that directly detect the hailstones based on their scattering properties, and then those that indirectly infer the presence of hail based on something about the storm structure. So kind of just jump right into some of a summary here. And I guess the point of this talk is essentially to kind of go over what we've been doing, what I think we've been doing wrong, and maybe some directions that we can move in the future. So for the paradigm one, the direct detection and sizing based on scattering properties. And this goes way back. We even heard Wayne talk about this too. The maximum Z in the storm, particularly is reflectivity, is why I'm using it to symbol Z here. Radar reflectivity in the storm, the maximum reflectivity at low levels, certain values, and this can be traced back into the early days of weather radar. There's also more recent polarimetry-based techniques, and I'll show an example of that. So here, and on the left column is the reflectivity factor from the storm. The middle column is the differential reflectivity, kind of tells you a little bit about the shapes of the particles. And then on the right is the hail differential reflectivity, which if you want to see Jake's poster over there, he's looking at that too. And then there's a couple of hail reports there. Circled here, 2.5 and 4.4 centimeters. And basically you can see that when you have a larger HDR value, using both the information about how much energy is scattered back and the shapes of the particles, especially those that are kind of spherical, it's inferred the presence of hail. And so this has been a pretty popular technique for detection, at least, and now getting a little bit into the sizing. This is kind of the summary of the current NEXRAD hail size discrimination algorithm. I know that Alexander is speaking right after, so I don't have to go into too much detail. But the idea here is that it's going to capitalize on the different melting behaviors of small, large, and significantly severe hail as they descend. So this is sort of showing you can think of it like a PDF of the expected reflectivity in the left column, Z versus ZDR, differential reflectivity in the middle, and then the correlation coefficient in the right column. The black lines are for small hail, blue is severe, red is significantly severe. And as you move from top to bottom, you're going from above the melting layer to increasing melting as you move towards the ground. And really what I wanted to point out here is that you see this sort of implied relationship that as the hail size categories get larger, you sort of see that expected reflectivity is increasing from left to right. You also see a bit of a relationship in the Z and ZDR space that they've built into this. Again, trying to capture the differences in behavior in the melting of the hailstones. And I'll point out that the correlation coefficient, once you get below the melting layer, there's not a lot of change going on there. So I want you to keep that in mind. Also, a thing here is there's another polarimetric radar variable that's not used here that I think is important, and we'll get to that in a little bit. There's also some of these methods have been using the low-level hail kinetic energy flux. I know Andy's very fond of this. I can trace this back to Waldvogel. And so just for the equation here, basically the factors that go into it are the hail size distribution. How many of each size hailstone do you have? And then this V here would be like its fall speed relationship. So theoretically, this should actually work out really well because you can see n of d to the third power, and velocity is usually something between to the 0.5 to the 0.7. That gets you pretty close to d to the 6, which is, at least for small particles, what reflectivity is. So theoretically, there's a good correlation there. But the problems with this is that the n of d is always something that's really hard, the hail size distribution. You've seen lots of talks about trying to get that. And I'll just sort of comment here that the time integrated distributions that we get either from a Hailpad or from averaging aircraft data, or from any of the other sort of mechanisms that we've been seeing this week, generally are not equal to the size distribution that's captured within the radar sampling volume. The only time those are true is if the hailstorm is perfectly homogeneous in space and time, which we know is not true. Also, the velocity here, Andy's done a lot of work in this, but I think he would agree that there's a lot of scatter in those relationships. So there's some uncertainty there, and it's also variable. right? Even a given hailstone will change its fall speed as it's falling based on its tumbling behaviors and things like that. So there's a lot of uncertainty there in practice, which leads to sort of correlations that aren't quite as nice as those theoretical ones that you can look at. So this is actually from the Waldvogel paper showing the sort of inferred from Hailpads on the x-axis and the kinetic energy flux from the reflectivity observations on the y-axis. The reported correlation is 0.67. You can see that scatter is considerable. We'll leave it at that. So when we specifically focus on sizing here, that's why I've highlighted it, the implicit assumption that underlies all of these different approaches is that the largest hail is going to dominate the backscattering or the scattering properties. And we know that's not true. And we've known that that's not true dating back to 1940s and 1950s when these calculations were first done. So just as a little flavor on the bottom here is the hailstone diameter on the x-axis versus reflectivity on the y-axis. The dashed line shows that the true calculations for spheres, spherical hailstones. That solid line is what it would be if everything followed that d to the 6th relationship that everyone kind of hears about for reflectivity. And you can see it peels off of that really quick, right? So that the size dependence kind of gets lost very early on in the hail size. And hail is pretty unique in terms of hydrometeors and radar because it's one type of hydrometeor, at least for longer radar wavelengths, that can be an appreciable size of the wavelength, can actually exceed the wavelength in some cases. And that leads to some really interesting scattering behavior. So what this plot is basically showing is a big hailstone, and it shows a snapshot of, say, the radar wave, this little green thing, at any given point. And at any snapshot, any instance, you can see that across the hailstone, you're getting a different electric field from the radar's transmitted wave. And that means that all the little molecules in this hailstone are going to be oscillated out of sync with one another. And all of you probably know if you mix waves that are out of sync, you get constructive and destructive interference. And that kind of causes a lot of complication in the scattering patterns. So what this actually looks like for simple cases of dry spherical hailstones, as a function of diameter on the x-axis here, here's our reflectivity normalized as if you had 1 per cubic meter for 3 wavelengths: S-band, which is about 10 centimeters wavelength in black, C-band, 5 centimeters in gold, and X-band, 3 centimeters in green there. And basically the point being that you see these wiggles, right? Those wiggles are because of this resonance scattering effect, because of the destructive interferences of the different parts of the hailstones scattering in and out of phase with one another. And it's also not monotonic, right? So anytime you're trying to use a measurement for size that's not monotonic in size, it's going to lead to some issues. So just as a kind of a fun thought experiment, this is a kind of crazy looking plot, but on the x-axis here would be the reference hail size. So imagine you had some hailstone of a given size here. You can pick your favorite size. And if you wanted to match the reflectivity contribution of stones of that size to the reflectivity contribution of stones with some other size on the y-axis, then you would need to multiply the number concentration by the factor shown here on the log scale and on the colors. And so basically that means that if it's purple, you need more stones, green, you need fewer stones. And I just want to show a couple of fun areas. Like, for example, if you have a 9 centimeter hailstone and you want to match the reflectivity contribution with 4 centimeter hailstones, you actually need either the same amount or less, right? So the sort of size and number dependence on reflectivity is something that gets really complicated. It's actually worse than that. Those were all for spherical stones. These are real stones. So we took the IBHS and Soderholm collections, those lumpy things that you see in some of the pictures, and we can do the scattering calculations for 770 different orientations of those stones. So each cloud of points represents one of those stones. The circle is the arithmetic median of that, and then the bars are basically the 10th to 90th percentile of those. And I just want to zoom in on one little area here just to kind of show you the differences in variability. So here's for, like, let's say a 3 to 3.5 centimeter hailstone. There's 2 clouds of points that are sort of washed out. So stones of very similar size can have huge differences in variability. One of them, no matter which orientation you have, has a pretty same reflectivity that you get. But the one that's got the really tall vertical line there, it's over 10 dB variation, just depending on how you turn that stone. And so if you imagine tumbling behaviors, you're going to get very different responses to the radar. So some of you have asked this week, what about multi-frequency? So this is something that's ideas that's been gone back for a while. So here's S and X in black and S and C dual wavelength ratios in red as a function of hailstone size. And so basically, if you wanted to get size information out of this, you would want to see some sort of good relationship I don't really see one here, at least in terms of as a function of size. I will note that if you kind of look at the difference between the black and red dots, there may be some value there in triple frequency. That's something that maybe can be pursued, but I really don't see a lot of information coming from the dual wavelength for either SNX and SNC. Why is this the problem? Again, the complicated scattering patterns inside hailstones, because of their lumpy shapes and their large sizes, just leads to a lot of complications. So this is just a snapshot if you illuminated a lumpy hailstone with two different polarizations, and the colors represent how strong the electric field is inside the hailstone because of all these little interferences. And you can see these lobes are having a big effect, right? At each polarization, you get a really strong electric field, and a V polarization is actually a little null there, just in that little lobe. And that's going to end up changing the way that this hailstone scatters radiation. So another one that's maybe sort of, some of you heard, three-body scattering signatures is a classic example, is reflectivity. Here's your hailstorm. And then radially away from the radar, behind the hailstorm, you get this little flare of reflectivity. It's a good indicator that you have hail present. So if there's a detection, it's quite good. What about for sizing? Zernich et al. Looked at the reflectivity of this and found there was no good size information out of that. With a student recently, we've been looking at the velocity information. So this is some hot off the press stuff. So if you look at the velocity, you can do a fit to that. And the original Zernich theory said that should be related to the fall speed. So in this case, the sort of estimates of hail size that we get based on these velocity data are shown by the histogram. And then that green dashed line is actually the maximum reported hail size for this case. So of course I cherry picked a really great case where it looks pretty good. But as you can probably imagine, there's some cases where it doesn't look so good. And the reason is the same as what I've been harping on for the last few minutes, the same problems with reflectivity, with scatter. What's shown here is the backscatter curve again in green, showing your reflectivity as a function of hail size. And this magenta line shows what I call the downscatter. So that's the radiation that's scattered kind of towards the ground that creates that three-body scattering signature, follows the same pattern. So again, you're not going to see the maximum size stone because it's probably not going to dominate the scattering properties. So what are some possibilities that we can do here? I really think the time resolved hail size distributions using those really nice time information we get from either Ian's probes or some of the work we saw this morning, I think would be really helpful in at least constraining the scattering calculations. And I really think that we need to incorporate information from all of the radar variables. I'm hoping that Alexander will say something about this next, but specific differential phase, KDP, and its sort of counterpart in the attenuation, specific differential attenuation, ADP here, is actually going to be really useful for small hail quantification. I know there's a lot of talk on the first day about lots of high concentrations of small hail. You can get unambiguous detection of those types of areas using KDP. So we can talk about that later if you have questions about that. Right now, that's not used in any of the hail sizing algorithms that are operational, at least. So that's something that should be used. There's also the idea of attenuation for large hail quantification. Attenuation has to do with forward scattering. And forward scattering is not marred by all those resonance effects. It continues to go as d to the sixth. And so we end up getting a sort of a better relationship between hail size and attenuation if it can be reliably measured. That's not easy in practice, but it's perhaps something that can be pursued. Better use of the cross-polar component in cases that they do exist. We heard John Hubbard talk about that earlier. Unfortunately, that's not available operationally, but the correlation coefficient rho HV could be used a little bit better. And then bistatic receivers. This is some work that's been going on at OU and their ARC. The forward scattering, again, is something that is going to increase monotonically with size. So you might get a little bit better chance of seeing some of those bigger stones for sizing if you were to put some bistatic receivers out kind of in the forward or near forward direction. And then also knowing where to look. A lot of the work is focused on looking at low levels close to where the hail's falling out. But I think if we examine the common growth pathways, and especially before it has a chance to do size sorting like it always does, you have a better chance of sort of characterizing the hail. And so this is just an example of a hailstorm simulation that we did. Embryos inserted every 30 seconds for a period of about a half hour. And you can see the storm sort of evolving here. It's every single severe hailstone that was produced in this case. And you see that they generally follow these sort of pathways that come around the mesocyclone and sort of loop up. And we see this very clearly in polarimetric radar data in supercell storms at least. And so focusing in on those areas where we know the hail is being made can help potentially with some of these issues. Paradigm 2.
indirect detection and sizing based on storm intensity. So the implicit assumption here, and we've seen a lot of talk about mesh and things like that this week, is that taller storms or stronger updrafts mean larger hail. That is a fundamentally flawed assumption. It's not generally true, which means that a lot of these proxies are fundamentally flawed from their beginning. These go back, again, you can trace them back to Waldvogel. For example, given height of a reflectivity contour above the environmental 0-degree sea level, that's the basis of the probability of hail used in Europe. It's the basis of the European mesh, which is different than the US mesh. That's also used across Europe. So how does that look? Here's some data. If you compile observations from a number of different cases, those are the blue dots. The maximum height of the 50 dBz reflectivity contour versus the maximum reported hail size. This mesh's algorithm that's used is shown by the pink stars here. And I'm not that great at statistics, but I don't think that line fits very good to those blue dots. So I think maybe there's some issues that can be addressed with that. Similarly, if we look at our hailstorm simulations, these black dots and the stars are representing what we actually get from our simulated hailstorms. Looking at the maximum height of a reflectivity contour versus hail maximum size. Again, it's a very weak correlation there. You're really not seeing much. And we shouldn't expect to be because it's a fundamentally flawed underlying assumption. Vertically integrated products are quite similar. Things like VIL, we've heard about VIL, vertically integrated liquid, vertically integrated ice, VIL density, mesh. There's a whole suite of them. We've seen this figure already. This is from Kyle's paper in 2018. If mesh and maximum hail size are actually had any skill, you would hope they would follow along the line. They don't. There's no correlation there. And in our simulations, we also don't see any sort of pattern or correlation. So here's hailstone Dmax versus mesh. You see that basically Dmax is a big wide range over all these different storms, but mesh is about the same. Because in these simulations, we had a very sort of closely matched sort of temperature profile. And so the storms all reached the same height, right? So the storm height had nothing to do with the hail size in this case. We've seen some stuff from the newer mesh from Alyssa and Cameron, mesh 95, mesh 75, right? These lines don't fit the data at all, right? They're not going to because it's just not a good product. What else is there? So Doppler signatures. This is something we've maybe heard a little bit about, like rotational velocity or storm top divergence. This is one that I got a little bit excited about. If you go back to the original WIT paper or conference paper, the green dots here show a little bit, so like a 0.4 correlation, so kind of moderate correlation there. Blair et al. Had some obs that show up here for larger hail sizes. For the gargantuan hail, we're up here. So, if you sort of draw a line there, there's maybe a general increasing trend with increasing hail size in terms of the Doppler rotational signatures. But it turns out, I think there's actually a lurking variable here. In these cases, when we only change the CAPE, we see that the mesocyclone strength as inferred by a Doppler radar increases. So what we may be seeing in those data is a proxy for CAPE, again, a proxy for storm intensity. If you want to know the dynamics why, you can talk to Yuju or read her paper because she explains it beautifully in her recent paper. So what are some possibilities? We heard Jeff Trapp yesterday talk about updraft width. Updraft width is more important than updraft speed when it comes to hail size. And we can see that with the radar. Bound in weak echo regions, we saw Wayne just gave a nice example in his conceptual model of the weak echo region. It's not the full updraft, but it's a portion of the updraft and it's related to the updraft. So measuring its area, quantifying its area gives us some indication about the size of the updraft. Similarly, in the polarimetric data, we have things like ZDR and KDP columns that can be used. Again, not the full updraft, but they are portions of the updraft, and we can use that to quantify the updraft area. There's also ROHV or LDR enhancement signatures up there as well that can be used. There's already some work being done on ZDR and KDP columns. Jeff Snyder has an earlier paper, but here's a recent one by Mike French and Daryl Kingfield. I'm actually starting to quantify these updraft areas from the radar data. It can be done from satellite data too. I think these are really promising avenues to go through. Again, the ROHV hole and the LDR cap area is something that could be pursued as well. And then finally, monitoring in updraft horizontal flow patterns. We've really been harping on this from our simulations. And these are things that we can see with a Doppler radar. So specifically, left splits, for right-moving supercells, when a right-moving supercell takes a turn, anticyclonic vortex shedding, we found that these are very highly correlated with the sort of periodic bigger hail production that we end up seeing in those simulations, and we see a lot of evidence even this week for that in observations as well.
So I know I'm out of time, so I'll put everything up here, but I really, really want to focus on this third bullet point. Just let's move on, right? Hail size is not correlated to updraft strength or the depth of the storm, right? What we're seeing with mesh and all these different proxies like that is basically proxies for deep, tall storms. Do you need a good, strong storm to produce hail? Yes. But there's a lot of other factors that go into it. So let's start to look at those other factors. So I'll take any questions if we have time, but I'll be here later to the talks. Thank you.
We can take one question if there's a question real quick. If none, we'll go ahead and move on. Thank you very much. Thank you. All right. And once again, for those who are virtual who might have joined late, if you have a question, we're not monitoring the chat right now because that laptop is not available. So raise your hand and we'll catch you on the screen here. Up next is Alexander Reichkopf. He's going to be talking about operational polarimetric NEXRAD algorithm for the detection of hail and determination of its size.
Okay, do you see my screen or not?
Yes, yes.
Okay, good afternoon, everybody. It's good to continue after the Matt talk because he actually explained some of the ideas very eloquently, which I simply would like to repeat in some sense. All right. How can I, trying to figure out how can I forward this?
We will advance the slides for you. We're not able to give you remote.
Please advance. The next slide, please. Okay, so there are several rather algorithms using operationally for hail detection, determination with size. Matt mentions some of those: wheel, vertical integrated liquid, then Z-based severe hail index, maximum expected hail size, which are very popular and do not use any polarimetric information, and also dual polarization algorithm that is currently implemented on the NEXRAD network. And this algorithm distinguishes between hail of small, less than 1 inch size, large between 1 and 2 inches, and giant hail exceeding 2 inches. Next slide, please. Matt already mentioned this HSDA and basic principle behind this HSDA. This is a polarimetric fuzzy logic algorithm that uses Z, ZDR, and ρHV, not KDP at the moment, as well as temperature information. And the different sets of membership functions for the 3 rather variables are used in 6 temperature layers determined by wet bulb temperature from the model. There are 2 layers, A and B, above the freezing level, where wet bulb temperature is equal to degrees, and 4 layers below the freezing level. Just first kilometer below the freezing level, second kilometer, third kilometer, and the surface layer stretching down to the surface. And 3 panels at the bottom show statistical distribution of the radar reflectivity, differential reflectivity, and cross-correlation coefficient at different height levels for no hail, for small hail, for large hail, and giant hail. And those are, this is a summary of the measurements from the large data set obtained during the NSSL severe hazard analysis and verification experiment, SHAVE, conducted from 2010 to 2014 across the conus. And it is clear that if you're looking at A and B levels above the freezing layer, it's clear that radar reflectivity is a primary discriminator between hail of different size above the melting layer, but polarimetric variables are very useful at the levels at the lower altitude, C, D, E, and F. So where hail is melting. And these distributions of ZZDR and RHV depend on the degree of melting which actually motivated the separation of different height intervals in the HSDA algorithm. So these experimentally obtained distributions are very consistent with the output of our model of melting hail that uses equations and parameterization from the old and famous papers of Rasmussen and Hainsfeld in the mid-80s, which are coupled with our polarimetric radar forward operator. Next slide, please. So this is basically a 1D spectral beam model that described in our 2013 papers. Matt Comjian is also co-author for this paper. This model was originally initialized with certain assumed size distribution of dry hail above the melting layer. That is that was shown. This is by exponential size distribution. For no hail, typical small, typical large, and typical giant hail. Those were based at that time on a couple of Paul Smith and company conference papers in the 70s describing in situ measurements of hail on board this legendary T-28 aircraft. So we were pleased to find out that these theoretical distributions were not much different from the ones reported in the later study by Paul Field and others in his 2019 paper. And I believe that if we get actual T-28 size distribution from the Andes group on T-28, then we can repeat model simulations with realistic size distribution rather than sort of theoretical one, which will help to optimize existing membership functions in the algorithm. Next slide, please. As Matt mentioned already, it's unfortunate that the current HSDA version doesn't use KDP. This is definitely a omission on our side, especially given recent observation evidence that high KDP combined with moderate radar reflectivity indicates small hail in high concentration, whereas moderate or low KDP associated with high radar reflectivity is usually indication of large hail. This is clearly supported by the results of our simulation shown on this slide, demonstrating the contribution of different parts of particle spectra to Z in two left columns and KDP in the two right columns at different heights below the melting layer at S band and C band. And it's clear that the largest hail size is a primary contributor. It's basically we build these graphs based on the size distribution, simulated size distribution of a relatively large hail. So it is clear that largest hail sizes primarily contributed to radar reflectivity at S band. You see very strong increase of contribution of very large hailstones to radar reflectivity, but not at C-band. That may tell us that the algorithm, something like mesh, have very limited utilization for C-band because very large hail, say with sizes more than 25 millimeters or larger, okay, may not even contribute to radar reflectivity significantly. The radar reflectivity may be associated with a hail with a relatively moderate size from 10 to 20 millimeters, as this simulation show. So, but also clear that the hail with sizes less than 15 millimeter dominates KDP, specific differential phase. So that with the full agreement with the couple of recent papers that Matt Comjian and his group published, showing that indeed this high KDP is associated with small hail and high concentration. So therefore, we plan to add membership function for KDP in the modified version of hail site HSDA. Next slide, please. Another issue with HSDA has been discovered relatively recently. It turns out that quite often the tropical rain that commonly lacks any hail, basically, it is misclassified by HSDA as small hail. And this is due to the fact that tropical rain, similarly to hail, is characterized by low differential reflectivity combined with high radar reflectivity. So in this plot, locations of Z and ZDR pairs for different type of rain, ranging from continental rain dominated by large raindrops resulting from melting ground and hail, versus tropical rain that doesn't have any hail, and basically it's a warm rain process, and the rain is characterized by high concentration of very small raindrops. So, and for a given value of radar reflectivity, tropical rain has the lowest value of differential reflectivity. And this is what is expected for small hail. Next slide, because, well, next slide, please. Okay, and this is exactly what the membership function for small hail show. So there's huge overlap. In order to avoid such misclassification, we plan to utilize vertical profile of radar reflectivity because vertical gradient of radar reflectivity is very high in tropical rain and usually low or non-existing at all in hail. So because we've seen a lot of indication from our partners in for radar hydrology, they try to associate extremely intense rain rates very often to small hail, judging from the output of the HSDA. Now this will be fixed. Next slide, please. This is an example of the HSDA classification output at the lowest antenna tilt, 0.5 degrees, for the case of giant hail reported near Hondo in Texas on 28 April 2021. So very high radar reflectivity, negative differential reflectivity, and very low cross-correlation coefficient indeed indicate giant hail that was reported to the surface. So giant hail is marked by yellow, followed by large hail and small hail, immersed in large hail and small hail. Next slide, please. Yeah, and the corresponding hail that was recorded on the surface was really a record site. It's 16.3 centimeter. It's not absolute record, but close to one. So the same storm moved to northeast to Oklahoma and directly hit Norman, causing widespread catastrophic damage. And maximal hail size reported in Norman was almost 10 centimeter. Next slide, please. But this is not the point. The point is that this particular giant hailstone that I showed in the previous slide actually fell near the edge of the storm, which is marked by the star symbol. But it fell just below the storm location, aloft where giant hail it formed above the top of convective updraft, manifested by a tall differential reflectivity column. And it had very low negative differential reflectivities, can be seen from this, from the right bottom panel. An extremely low cross-correlation coefficient also shown in the left bottom panel there. And the bottom line here and the major conclusion is that hail designation or nowcasting at the surface has to be linked with polarimetric hail signatures aloft. Unfortunately, the existing hail classification algorithm implemented in the Radar Operations Center or on the NEXRAD network is local. In other words, classifications are made separately and independently at different elevations. And we definitely have to link them in order to and look into vertical structure of the storm in order to make appropriate warning at the surface. Next slide, please. As Matt mentioned already here, I mean, because of constructive, destructive interference, we may have differential reflectivity negative, although the horizontal dimension of hailstone may be larger than its vertical dimension. And this graph shows that, for example, ZDR of melting hailstones, either melting hailstones or hailstones coated with the water shell when hail is being grown in the wet growth regime at the top of the convective updraft. Indeed, I mean, for S-band at least, we see this blue curve on the right panel. It goes down below 0. And very often we see differential reflectivity as low as -4 dB. Yeah, that's exactly what was the feature that we have to take into account, basically. So this, therefore, if negative differential reflectivity is observed at S-band, so then this is an evidence of giant hail with size exceeding 5-6 centimeters. And again, it's also evidence of a strong size sorting effects. If we, in other words, if we integrate this curve over the whole size distribution, we won't get any integrated positive differential reflectivity because of the contribution of small hailstones that have intrinsic positive differential reflectivity. So that means that there should be a mechanism that separate those bins, size bins with sizes more than 5-6 centimeters from the rest of the size spectrum. And this indeed because largest hailstone definitely have higher terminal velocities and they overtake the longer one on their way to the surface. Next slide, please. Yeah, there are remarkable virtual artifacts. Matt also shows some of those in the fields of all radar variables caused by particularly large hail. So they are particularly clear and distinguishable in terms of cross-correlation coefficient, which is anomalously low. Differential reflectivity usually low, but negative, but not always. So, and these artifacts include the three-body scattering, which is indicated by the streaks in the radial direction containing hail with respect to the radar, which is well known to the community. The question is, as Matt mentioned, can they be used for hail sizing? The radar reflectivity definitely maybe not. But if we combine ZDR, cross-correlation coefficient, and maybe KDP, if we have those, so then we definitely won't see any KDP because cross-correlation coefficient is so low that KDP would be very, very, very noisy and not useful. But anyway, this is still a room for the study to see how we can capitalize on these features. And my last slide will be the next one, in which I simply summarize the forthcoming modifications of the operationality, the algorithm for detection of hail dimension this size that we are thinking about at the moment and putting in our plans. So definitely we would like to use those T28 unique measurements from this legendary aircraft collected by this legendary pilot. I learned a lot from this amazing talk at the beginning of this section. So when we can use realistic hail size distribution measured by T28 to optimize the parameters of membership functions. And there is no doubt that specific differential phase KDP has to be used in HSDA along with ZZDR and cross-correlation coefficient. It's generally simple and low-hanging fruit to eliminate false designation of small hail and tropical rain, and we will do that using vertical gradient reflectivity. Visible artifacts might be might be used as well, but again, there are some issues that has to be addressed with that. And again, the polarimetric, we need to look into the whole structure of the storm. We need to look at the polarimetric signatures in loft, such as say negative differential reflectivity, very low cross-correlation coefficient on the top of differential reflective column. That implies automatic detection of these differential reflective columns as a proxy for convective updrafts. And we have to link together polarimetric signatures at higher and lower levels. Thanks for your attention. I'm ready to take any question if you have any.
We can take one question if, go ahead.
Hi, Alexander, this is Chandra. So question for both you and Matt together. I've been starting to look at this quote unquote giant hail that you hold in people's hand. It's in two hands. And historically, if I had talked about this, it would have been an insane question. That is, it almost looks like two hailstones fused with each other. And then otherwise I can't imagine some sort of a growth model that could explain things all being elongated in one direction. If I said this, if I didn't see a picture before, it would have been considered nonsense. So either of you want to comment on this?
You know, Matt, can you comment on that? Because you did something on that, right, or not? I can comment, but probably you are more qualified to do that.
Yeah, thanks, Alexander. I guess to answer the question, Chandra, these large irregular stones, at least the ones that have been thin sliced, still have the one nucleus, and it's definitely one stone that grew in that. The fact that it's non-spherical definitely indicates that random tumbling is not the predominant fall behavior as it's growing. And so, and also the negative ZDR that Alexander just showed also indicates that random tumbling cannot be the fall behavior, at least up there. But yeah, spinning does happen. Sometimes you can see there's some great videos that Kyle and Sean can show you some weird stuff. Yeah.
All right. Thank you, Alexander.
Thank you.
Now I'll move on to Vincent Forcadelli, who is going to talk about neural networks and dual pole radar.
Okay, thank you. Do you hear me?
Yes.
Okay. Do I have to share my screen? No. Okay. Perfect. Do I tell you to change the slide?
You should have remote control.
Okay. Doesn't seem to work, to be honest. I don't have remote control, sorry.
We will advance them for you.
Yeah, thank you very much. So good evening, everyone. So first of all, I want to thank you, and particularly for the organizers to have organized this workshop. It has been really interesting so far. and thank you for that. So today I'm going to present to you my work on the convolutional neural network for the classification of hailstorms by dual polarization radar. This work has been done in collaboration with Météo France and Descartes Underwriting, which is a company specialized in parametric insurance worldwide. I also want to say that this work is being written at the moment and that it will be proposed to review in the coming weeks. Next slide, please. So the aim of my work is to harness the potential spatial signatures specific to hailstorms, thanks to a convolutional neural network applied to radar images. So first I go into an introduction, then I will explain the construction of my data set, then I will go into the model and the features, and I will then conclude with the results and the conclusion of my work. Next slide, please. So hail signatures within weather data have been studied for a long time now, using different techniques and different data sources. While numerical weather prediction soundings can suffer displacement error in space and time, some studies show that possible spatial radar signatures for very big hail storms can be seen. Those signatures can be alleviated by deep learning techniques if we have enough ground truth report to validate that. And I also want to highlight let's say the problems we can face with hail size detection based on scattering properties that was highlighted by Matthew 20 minutes ago. So based on these aforementioned studies, we have chosen an approach to answer that is to constitute a strong supervised data set with hail reports to train a CNN with radar data able to use the parent storm structure to discriminate storms from hailstorms. Next slide, please. So a reliable neural network is very often based on a high quality data set. The better the data set, the better the performances of the machine learning method. So here we developed the deep learning method onto 150 kilometer domain in the southwestern part of France, near the city of Toulouse. What you can see here in black dots are a relatively high dense network of Hailpads from the ANELPHA association. So based on that domain, we developed two parallel pre-processing techniques. Next slide, please. Thank you. The first one being for the positive data set. So first, for every hail report in the data, we gathered radar data in the vicinity of those reports. And we corrected it for attenuation in both reflectivity and differential reflectivity. Then a manual filtering was carried out. So for every report in the data set, we extracted the best time step where the storm was passing above the pad. And from this filtering, we went from nearly 600 raw reports to 461 positive reports. And for each of these reports, we gathered the data around them. Next slide, please. So the second parallel method, it's for the negative part of the data set. So for that, we used composite reflectivity product from Météo France. We gathered data for 10 months during summer 2019 and 2020. And within our whole domain, we picked the maximum reflectivity pixel on the domain. And if first the reflectivity was above 45 dBz and 2, if there was no hail report at all reported on the same day, then we extracted the location and the time step of this max reflectivity pixel, and we made it a negative report. So that way we ended up with 715 negative reports, where we also gathered the data around them. Next slide, please. So now that we have both positive and negative reports, we process the radar images that would be fed into our convolutional neural network, our CNN. So because of non-uniform beam resolution, we interpolated the data around each report with a 40 kilometer by 40 kilometer domain at a 250 mil resolution. And also because of a lack of samples, particularly for the positive data set, we oversampled this 40 by 40 domain with 20 kilometers by 20 kilometers patches. So these techniques allow us to multiply by 5 the size of our data set so that the machine learning method will be fitted to it. Next slide, please. So now that the data set has been constructed, let's talk about the model and its features. So the architecture of this CNN was chosen based on several criteria. First, the performances, of course. Two, the reproducibility of the results among different parts of the data set. 3, the frugality of the training. And 4, the rapid convergence towards the minimum loss. So based on those criteria, we ended up with an architecture based on 2-dimensional inputs and 2-dimensional kernels. For the features, we have picked maximum ZH over elevation angles and maximum ZDR over elevation angles. Why did we do that? Is because we wanted to see and check even with simple features if it was relevant to, and if it was giving actually good performances even with maximum and 2D features. We also tested other features, radar variables. So we added KDP, we added OHV, we added FDP, and the combination of ZH and ZDR was the combination that was giving the best performances on the binary classification task. So the structure is the following: 3 convolutional layers containing each of them containing a max pooling and a ReLU activation function. At the end, we have a dense layer that is feeding one neuron, which the output is the probability for the image to contain hail. So we are on a binary problem here, whether we have hail or not in our image. Next slide, please. So here I'm going to talk about the results of that binary classification task. So we compared the results with our two algorithms, state-of-the-art ones. The first one being Alsaka fuzzy logic method, and the second one being basic semi-supervised clustering method. So those two methods gives hydrometeor classification at every radar pixel. The performance for these methods were computed as follows. If the area of hail taking the max over elevations of classes for this algorithm, if the area of hail was above a certain threshold, then this image was classified as positive, and if it was under this threshold, the output of this algorithm, the two state-of-the-art algorithm, will be classified as negative. So you can go to the next slide, please. So here you will see, you see a summarized table that fairly summarizes the results for different well-known metrics. So I want to highlight the presence of a random forest here, which is, we applied it, even if it's a redundant method on this particular problem. We just wanted to see what it gave. And actually, it's quite, let's say, interesting to see that it can compete with more or less with state-of-the-art methods. We also tested a CNN with only ZH in it, as a feature to see if the CNN was able to find relevant information to classify storms. And actually, it competes really well with state-of-the-art methods, particularly the best one being Alsaca. And at the end of the table, we have our chosen CNN, ZH plus ZDR, that gives overall slightly better results for compared to best Alsaca, and slightly better results overall. So next slide, please. So the results now shown as a rock curve. So here you have two legacy methods, the one from Alsaca, the one from Basic. And you can go to the next slide, please. So the main purpose is to be at the upper left part of the graph. So here you have basic thresholding method, taking the maximum over elevations, of course, of reflectivity, and if there was any pixel more than 50 dBz, it would be classified as positive sample. And you can see that it gives performances, but slow, let's say, not that better performances compared to Alsaca. Next slide, please. So here we implemented, next slide, please. Yeah, thank you. Here we implemented the CNN only with ZH, and you can see the increase of performances compared to basic dump method being thresholding. And we are even competing with Alsaca method here. And next slide, please. And here is the method we are retained based on ZH and ZDR. So we can see an increase of performances when we add ZDR to the problem, meaning that ZDR has meaningful information for the classification of storms in hail or non-hail storms. So basically what we want to know now is why does it give this kind of results and is competing with the best state-of-the-art methods. Next slide, please. So what you see here is a positive sample. We know there was hail in it. And I'm going to show you gradient maps. So what you need to know about them is basically they represent areas within the image where the CNN is extracting its information from. So basically here you have this is what we call saliency maps also. So here you have the saliency map for the CNN using only ZH, and you can see that it contours well the area of high reflectivities, but the gradients are quite spread out, and it only just contours the reflectivity, and it's quite it doesn't give any more input about let's say how does it choose to classify it as positive. Next slide, please.
Vincent, if we can move to the end, we're getting quite behind here.
Oh, okay.
Thank you.
Okay. Yeah, sure. Okay. This is okay. Next slide, please. Okay. So here we can see that the CNN with ZH and ZDR. Next slide also, please. And I will end after that. No, the one before. Well, no problem. The CNN structure, well, these two radar features only slightly better performances for the binary classification task of radar images, and the CNN inference time is faster compared to legacy method. Also, we have a CNN that captures well ZH and ZDR signatures that are well known in the hailstorms that we didn't see here because I'm running out of time. But basically, it's what it does. Thank you very much, and sorry for being late. If you have any questions.
Thank you, Vincent. In the interest of time, we do need to move on. We have one more presentation before break. We are joining Isabel Greco in Australia, where I believe it's early in the morning. Good morning, Isabel. The floor is yours.
Yeah, awesome. If you just want to share my slides, that would be amazing. Awesome. Should I have control over this? And if so, how would it? Should I be able to change the slides, or will you change it for me?
You should be able to change them now.
Oh. What if I do this? I think I've just requested remote control. Does that work? No. I'm just trying out how exactly to control the said screen. Oh, beautiful. I'm not entirely sure how exactly I'm doing this, but we'll see if I can make it work. Okay, awesome. So to start off, I would just like to acknowledge that most of this work was done on the lands of the Bedegal and Gadigal people of the Eora Nation, and I'm currently lucky enough to be zooming in from beautiful Ghana country. There was no treaty ever signed with the First Nations people of Australia, so this always was and always will be Aboriginal land. Thank you so very much for having me. I'm really excited to share what I hope will be the start of a very exciting master's thesis that I'm currently completing at the University of New South Wales in Sydney under the supervision of my co-authors Steve Sherwood, Tim Ropak, and Gab Abramowitz. So I know on the first day of the conference, Tim and Jordan did an amazing job at taking you through, I guess, the state of hail observations in Australia, but I might just quickly rehash that because a lot has happened since then before introducing you to the problem that I'm hoping to solve and I guess how I'm hoping to do it. So let's get started. So this, I guess, is the good, the bad, and the ugly parts of Australian hail reports. So we've got the Severe Storms Archive, which is managed by the Australian Bureau of Meteorology and does an awesome job at collecting severe hail reports from around the country. So severe in Australia is above 2 centimetres, and that's what I'll be referring to throughout this talk. What becomes immediately apparent in the figure there is that the reports are where the people are. So mostly around the East Coast, a little bit elsewhere, in a trend that's perhaps or perhaps not linked to the climatological frequency, which can make using this data a little bit challenging. So just to look at, say, one storm season, this is 2013-14 storm season, you can see there aren't an awful lot of reports. I guess to put it in context, Australia is about the same size as the continental United States. We just have 300 million less people. So underreporting is a really massive issue. So here I've just popped a little circle around Melbourne, one of Australia's biggest cities, and would expect to kind of think that, oh, okay, no reports here in this storm season, perhaps no severe hail. But a quick Google reveals that Melbourne was in fact hit by hail during the storm season. Possible that it wasn't severe, but given the damage reports, that's kind of unlikely, and just serves to highlight how even in quite densely populated areas, hail is quite likely to go unreported in Australia, which can make using these reports directly really challenging. On the bright side, we do have, as both Jordan and Tim mentioned, an amazing radar network. So the east coast of Australia is quite well covered. There are some areas that are really not very well covered. These are kind of mostly through the centre of the continent and do include some really important agricultural regions. And I guess I'm hoping that by the end of my master's, I guess I'll have something to say about hail frequencies in these areas. But at the moment, we're focusing on a much smaller problem, which I'll introduce you to, pardon me, now. So this is an area of Australia you're going to become very familiar with over the next 10, 15 minutes. So we're on the east coast of Australia here. That sort of diagonal line is the border between Queensland and New South Wales. And this area includes the city of Brisbane, which is a known hail hotspot. So that purple area is the swath, well, kind of coverage, sorry, what's a better word, of the Mount Stapleton radar. And those green dots are hail reports in this season. So what we're trying to do in this piece of work is to construct, I guess, a bit of an understanding of the probability of hail at any given grid point. We sort of cut this up into quarter-degree grids and 6-hour time grids. So probability of hail in any of those space-time boxes across this season, informed by both the radar and the hail reports. So let me just talk you through how exactly we're going to do this. So there's some, I guess, pretty obvious things around data quality. We all know that the edges of the radar domain aren't great, the beam spreads, so this purple area has removed them. We also took a really close look at the report timings. So a lot of these hail reports come with comments around it. And there was a reasonable amount of inconsistency between, like, some comments will say, oh, hail fell at 6 p.m. and then the recorded time will be something quite different. So those were cleaned up manually. And we found that once doing that, there were no more reports in our 2 sort of early morning bins, and all our reports were in our sort of afternoon evening bins, which fits with when we know hailstorm frequency peaks. And so given the data availability, we only use these 2 afternoon bins in the following analysis, which probably does mean we've missed some hail, but that's just what the data gave us. Lastly, I did mention that the reports are really closely aligned with where the people are. There is actually sort of a east-west kind of road running out of Brisbane, but you can see some of those reports concentrated around. So to deal with that, we also got some population density data from the Australian Bureau of Statistics and put that onto the same grid. I should also mention while I'm here, the radar quantity that we're using. I know there has been a lot of discussion about why things like mesh and the severe hail index SHE aren't ideal. In this case, we're not using them to estimate size, but we are using them here, the maximum SHE in each grid box, as an indicator of potential for hailfall. So the mathematical machinery I'm using for this model is primarily Bayesian modeling, and I'm aware that maybe not everyone is super familiar with it. So if you are, now's a great time for a 2-minute micro nap. If you're not, I'm going to try and run us through this with a bit of a sort of toy example. So let's suppose we're interested perhaps in modeling hail over the entire Australia on an entire Australian continent on any given day. Perhaps our model, which is kind of bad, but just roll with me for this example, is that every day is independent of every other day and that there is some fixed probability at which hail will fall. Now, we don't know this fixed probability. That's why we're doing this modeling. But we have some ideas about it, right? We know it's not 0 because hail does fall sometimes. We know it's not 1 because it definitely doesn't fall every day. And let's suppose that this purple curve here kind of represents our confidence in or our feelings about what this value might be. But we're good scientists. We're not just going to go on what we think. So we go and gather some data. So let's suppose the sort of all the 0s are our non-hail days that we observed, all the 1s are some hail days we observed. And then we might just think of calculating the mean as a way to sort of estimate what this unknown probability is. And if we're frequentist statisticians, we might stop there, but we're Bayesians now, we're very cool. So what we're going to do is we're going to try and mix our prior ideas of what we think this probability is with the data. And in doing this, we obtain the posterior distribution, which describes, I guess, our data-informed view on this probability. So we can see that because we've seen so many non-hail days, we've really sort of got rid of this idea that it's quite a high probability, but we've still left this kind of uncertainty from which we can do some really cool analysis around. In the real world, I guess, quote unquote, these distributions are often, what's the word, multi-dimensional. They're not also very rarely analytic. So we won't be able to draw these nice graphs. I set this model up this way for a reason, so I could draw a nice graph, but we'll be able to analyze them numerically, which I'm not going to go into much detail about, but really happy to take questions on that if there's time. So my model is slightly more complicated than the one I just outlined. So let's suppose we've got a spatial grid cell. It's at place I time t, and then we're going to have some binary indicator R for whether a report was made or not. We're not worried about the size, just whether someone reported hail, severe hail, given we're looking at the severe storms archive. Then we're also going to have this unobserved variable. This is about whether, this is H, and this is about whether or not hail fell. And this is the variable that we're actually interested in. But we don't observe it. So we're going to try and use what we do know to understand something about this variable H. So we're going to suppose that given some predictors, it's going to be that maximum significant hail index in the grid box and the population data, population density data, and some parameters, which I'm just going to ignore for a second and call them theta. I'm going to say, given these two quantities for that grid box, then that reporting variable is just a Bernoulli random variable with some probability, and that probability can be decomposed into the probability of a report given that hail fell and the probability of hail falling. So there are a couple of assumptions underlying this model. So the first one is that there are no false reports. We assume that if a report was made, then that is definitely related to the fact that hail did actually fall. Given the Bureau of Meteorology kind of quality check, all these reports are full, putting them in the database, that's probably not a bad assumption. Another assumption we made, which is a bit more questionable, is that if there is no SHE detected on the radar, then no hail fell. We know that there's reasons why we might not have SHE and see hail fall. Beam blocking is a really obvious example. I'd love to look at ways to relax that assumption, but for now, that's what we're doing. And the last one is we assume that once we have these parameters and these predictors, all the cells are now independent of every other. So once we know about the radar, we know about the population density, we stop caring about the radar, population density, and other stuff in the surrounding cells, which I mean isn't a totally terrible assumption, but I think would be interesting to relax. And I'll come back to that a little bit later in this presentation. I've kind of glossed over though what the hell this theta is. So essentially theta kind of controls how we parameterize these two sort of factors in that pi probability. So for example, in that first piece, we're saying, well, once hail's fallen, we're gonna sort of not really worry about the radar data. We already know the hail's there. What we are concerned about though is the population density. So when their population density is low, we think we are less likely to get a report, high, more likely, and theta just kind of controls what that less and more likely means. In the same way, for this sort of second factor, we're gonna say, well, the storm doesn't care where the people are, but the radar can tell us something really useful. So we're going to say that when there's a low SHE value, we're less likely to get hail, high, more likely. I realize I'm being a little bit hand wavy about this just because it's too late in the conference for lots of heavy mathematics, I feel. But I will show you this one just to kind of indicate what our priors are. So I'll direct you to the bottom plot first, where we're looking at the probability of hail given that given a SHE measurement, and we can see that the uncertainty, so those gray bars around the mean, which is the dark line, is pretty big because we don't observe this actual hail fall and we don't really know what this probability should be. So we're willing to have a very large, like a very uncertain prior and let the data try and speak. On the other hand, on top, we've got the probability of a report given that hail fell. And we can see that we've been a little bit more confident here because there is some, I guess, loose empirical evidence which suggests that there is some kind of relationship. So you can see here, this is the probability, this is using a really, really rough like mesh threshold to get sort of a hail incident. And we expanded over a couple of years just to sort of get some non-zero results. So too few results in 1 year to too few reports in 1 year to really estimate these empirical probabilities of a report. But you can see there is, once we ignore the stuff on the edges of the radar where we know the data is a bit weird, we can see that there is some kind of trend here, and that's what informed that prior. So exciting stuff, results. So when I'm presenting these results, these are stuff that's now drawn from the posterior distribution. So we've had those prior beliefs and we've observed the data, and this is now, I guess, what we're seeing, how we've sort of updated our beliefs. So this is the posterior probability of a report given that hail fell as a function of the population density. And we can see, I guess, as we expected and as we kind of designed, when the population density is low, this is quite a low probability, and when it's higher, it's much higher. But what's really interesting is the way the uncertainty kind of balloons out. So we're really not sure at these high population densities what this reporting probability is, which kind of speaks to the fact that I sort of alluded to earlier, and that clearly there's a lot more than just population density that is influencing whether or not a hail event is reported. Similarly, here is the, I should have mentioned, the line is the mean of the distribution, and then we've got confidence intervals around it. But this is the posterior probability of hail given SHE. And again, really low SHE readings, we're seeing very low probabilities of hail. And again, at high SHE readings, we're much more confident, we're fairly confident about hail falling. But here, our largest uncertainty is kind of in that middle ground, where we've got a reasonably high SHE, but we're sort of on that boundary between like, is this severe, is this not? And which perhaps speaks to a way as well we can improve our model to try and reduce some of this uncertainty. To evaluate it, I guess in a sort of different way, we construct a sort of, I mean, maybe climatology is a strong word given this is one storm season, but a sort of bit of a spatial analysis of where of the expected number of hail days from these posterior distributions. So that's mine on the left, and on the right we got one from Rob Warren in 2020 using the same radar. So we are expecting similar trends given we're using the same radar. And if there are differences, that might be because we've been able to incorporate these reports, which hopefully give us some extra information. And you can see the numbers are kind of on par, given the probably error bounds in both of our results. We're both estimating 5 or 6 hail days over Brisbane. So that's a good sign. Similarly, here's one from Josh Soderholm in 2017. This is a slightly different area. This is using the Marburg radar, which is northwest, pardon me, of the Mount Stapleton radar. And again, we can see some kind of similar spatial patterns, even though this is from a different radar, which is generally a good sign. Another way of looking at these results is on an event basis. So this is a pretty big storm that went through Brisbane in 2013. So there's a radar image on the right from the Bureau of Meteorology. And we can see that given our model is informed by the radar, we're not surprised that we're seeing these similar spatial patterns. And also we're seeing that the reports are lining up with these areas where we're quite likely to get hail, which is good to see. So I think I sort of hinted at some, I guess, things I'd love to improve about this model. Some obvious things, obviously, like trying a tighter spatial resolution, seeing what happens, trying a smaller time resolution, seeing what happens. But there's a couple of, I guess, 2 really key, I guess, more structural issues that I'd love to have a quick chat about before I finish up. So the first one is how we can improve the kind of radar part of the model, the whole probability of hail given a radar. And part of the problem comes from the fact that we're gridding. So this is the grid that we're using. It's a quarter-degree grid. And this is an example of, I don't know how well it's showing up for you, but there's a sort of pink star. I'm not sure you can see you can't see my mouse, whatever. There's a pink star there, right near that sort of northernmost blob of the, maybe blob's not the right word, swath. You can tell I've been up all night. Swath of the Xi measurement. And what kind of happens is that storm quite moves sort of northeast and almost moves around the grid cell boundary. It's amazing in some ways. But what it does mean is that the highest Xi measurement, the highest sort of Xi measurements weren't in that grid cell where the report was made. They're actually sort of in this neighboring grid cells. And so as a result, we've got this case where we're sure hail fell, but the Xi reading was quite low. And I think it's cases like this that are contributing to some of that large uncertainty that we observed earlier. So I'd love to maybe see if we can relax the independence assumption around these grid cells in some way to sort of avoid this issue, if we can. A second one that I would love to take a look at is this idea of hail being reported. We sort of assume that all hail is reported equally. And this quote, I mean, do it both intuitively. This is a really lovely quote, which kind of highlights it in the sense that there's a lot more than just the population that impacts whether a report is made. That is one part of it, but by no means the only part of it. For example, we know that we're pretty confident that if a really massive hailstone falls, we're much more likely to make a report. There'll be media, there'll be a bit more excitement about it versus if, a 2.1 centimeter hailstone falls, which is severe, but far less kind of dramatic in most parts of Australia, at least. So I'd love to, I guess, have a think about how we can incorporate that. And even there are such other kind of local issues which are kind of fascinating. So if you look at the plot on the left, this is the expected posterior number of hail reports in each spatial grid cell over the course of the season. And on the far east, that darkest blue grid cell, that's the Gold Coast. For those of you not familiar with Australia, the Gold Coast is a bit of a, it's fairly densely populated, but it is a bit of a report city. It is a bit of a resort city where people are too busy sipping their pina coladas by the beach to make reports. And that's partly why perhaps you got this underreporting bias. I can see that I'm probably running out of time, but thank you so very much for listening. And I hope you have an amazing last little bit of the conference.
Thanks, Isabel. Yeah, and we will forego questions because we are a little bit behind here. We'll be back at 3:30, a small break here. We'll be back at 3:30 with the panel. Thank you.
Okay, before we get started with the panel on future of forecasting, Andy Detweiler has a quick clarification announcement regarding Wayne Sand's talk. So I was going to give him a second quick.
Hardly anybody's here, but Wayne gave a great talk. And I'm the second Andy that's been working with the T28 after the first Andy. And I was involved in the A10 project that Wayne discussed. And he doesn't know, but the project is done. We got it started, but things didn't work out and NSF has basically canceled it. So there's no current plans to develop another storm penetrating airplane.
Thanks for the bad news, Andy. All right, we're going to go ahead and get started with our Future of Hail forecasting workshop. We have a half an hour carved out for this, and we've already used 5. So let's get started. In terms of our panelists, the top right of the screen, you will see Jenny Pittman. She is the Science and Operations Officer at National Weather Service Topeka. Middle screen, we have Ryan Jewell, who is a forecaster at the Storm Prediction Center in Norman, Oklahoma. And to my left, live, we have Rebecca Adams-Seelam from AER. And so I have some canned questions here to start the discussion, but I welcome, as in the similar format for the other panel discussions, questions from our virtual attendees as well as those in person. So I'm going to start with Ryan. I'm going to pick on you first because you are probably the most routine at issuing hail outlooks.
Yeah.
You routinely issue hail forecasts at SPC, not only for day 1 convective outlooks, but in terms of even looking ahead, day 2, day 3, and even the upcoming week, perhaps. So I'm just curious, what are your go-to products, parameters, indices, et cetera, for hail forecasting? What are some of the major things that you consider when putting together, say, a day 1 or day 2 convective outlook?
Well, me personally, my answer is, it'll differ among forecasters. But I'd say, given that I've been there over 20 years, the primary thing I use is just kind of the catalog of events in my head, which not necessarily all, gut or whatever, but I would say looking at soundings, we're heavily sounding based at SPC, probably everyone that works there. And obviously, I have, composite charts just to draw your attention to an area, basic Cape shear, things like that. And of course we have the hail model that was that Becky's been working on a lot, and some other analog tools, which is integrated. They're all integrated into our N-Sharp sounding display system. But I would say, there's hail coverage and then hail size. There's sort of 2 different things. But yeah, we're focused on, okay, what's the max size going to be since we, forecast SIG. And so a lot of it is trying to forecast if it's going to be above or below the somewhat arbitrary 2-inch threshold. For our SIG hail purposes, if it's mostly golf ball and maybe 2-inch, we typically won't do SIG, but if we expect a lot of baseballs or larger, then we'll do SIGs. But so really the thing I look at most to determine max hail size is just my initial impression of soundings, just poking around the country, different grid boxes, looking at various models, obviously, RAP soundings and NAM soundings and Euro soundings. I mean, that's the first man to beat, so to speak, is just which model is correct. But in general, our hail tools, like Hail Model and the SARS analog, that'll draw your attention to an area. And, those bulk parameters, they, like a lot of Matt Cumgen's recent research, there's a lot of subtleties, and honestly, I'll just load a sounding and look at it and say, oh, that doesn't look right, a lot of times. And sometimes it's hard to quantify that. But like I said, I'm pulling from a catalog of events I've collected, over the years. So experience is a big thing, obviously. But I will segue back to you, but I'll just say that a lot of Matt's research that I've been keeping up on, it's exciting because it's kind of like putting into words concepts that I've sort of seen as I've worked throughout the years at SPC. It all makes sense. I'll just say that. So I think we're we're probably ready to move forward. I would say to
we need to get your catalog in your brain down on paper. That would be step one.
That's, you know, I generated 25 million hail soundings recently, which you are aware of. And so, yeah, hopefully, I think we're maybe on the cusp of some pretty good statistical hail guidance, I would say. So
awesome.
Anyway.
Thank you, Ryan. The next question is going to be for Becky to start. You do a significant amount of modeling to improve hail forecasts. Right now, what do you think the biggest limitation is with some of the models, i.e. Hailcast, that you work with?
Oh, good question. I think probably one of the biggest things is our lack of ability to resolve or understand or reproduce the updraft. There's a lot of research that's shown that updraft has a lot of effects on hail, particularly updraft width or updraft volume. That's something that we tried to kind of get around with this updraft parameterization in Hailcast, but it doesn't, there's lots of things that we just don't know. So yeah, the lack of information about the updraft. That now that's assuming you get the convection in the right place to start. That's not my problem. I'm the hail modeler. So that's a big problem on its own. But once you do, then understanding the updraft.
Awesome. Jenny, this question is going to be for you. So when, I think day-to-day forecasts, the forecast that has, the possibility for tornadoes in it, I think gets perhaps a different response from the public than a forecast with hail, unless perhaps you're in agriculture. So from your perspective as a Sue, what sort of difficulties do we currently have in communicating the threat of hail forecasts to the public, and what is there that we can do better, I think, in terms of communicating the forecast threat of hail, especially for large hail, sig hail?
Yeah, I think it's difficult, especially because the threshold at which we issue severe thunderstorm warnings is generally not super impactful if you're inside. Usually we're looking at, unless it's wind blown, but we're looking at 1.5, 1.75 for dents in your vehicle, broken glass, that kind of thing. And we're issuing at 1 inch. So a lot of people don't really care about that. And that leads to some fatigue when we are issuing severe thunderstorm warnings, even severe thunderstorm watches for primarily smaller hail events. So I'm not exactly sure what policy-wise needs to change, whether we need to continue to raise that threshold for severe hail and where we're issuing those warnings, or if we need to do something different communication-wise, alert-wise, with the different IBW thresholds, impact-based warning thresholds. And when we do get to those larger sizes, then those are communicated differently. We've started to do that with WEA, with WEA, where people are only alerted for significant hail or significant wind. But I think that's only the beginning. Because it's that 1 inch hail, not everyone's going to get it. The largest hail is in a relatively narrow swath. Most people aren't even going to see severe hail when we do issue a base level severe thunderstorm warning for 1 inch hail. So perhaps raising that threshold, or at least looking at that threshold in the way that we communicate it, is probably the first step to making people care about hail as much as they do about some of the other severe weather hazards.
Yeah, that's a great point. This question's for everyone, so whoever wants to jump in first, but we continue to reduce the horizontal grid spacing of our NWP models. So for those of you not familiar, forecasting, right, one of the major components of forecasting is numerical weather prediction. And really over the last 10 years, we've reduced our grid spacing in the models. We made a pretty big jump about a decade ago going to what are called convection allowing models, somewhere in the neighborhood of 3 to 4 kilometer horizontal grid spacing, and they continue to increase. Do you see this reduction in grid spacing and greater resolution continuing to increase, or have we sort of hit a critical threshold where maybe the grid spacing is going below where we really have observations and we're going to just start seeing a lot of noise? What's the future of CAM-based NWP for hail forecasting? Becky, I'm staring at you
All
because
right.
you're the modeler.
Okay, fair.
But I'm going to let everybody chime in here.
Fair. Okay, so I'm going to answer this first from maybe a science modeling perspective, and then again from an operational modeling perspective. From a science modeling perspective, no, my God, we got to go finer. We can't resolve an updraft at 4 kilometers. We got to get down to 100 some meters, and we need to do large eddy scale simulations, and so we can see what's actually going on. But from an operational perspective, there's a giant gap between 3 kilometers and 100 meters that computational efficiency wise, you're not just going to get there tomorrow. So yeah, I think you're absolutely right. There's probably a lot more that we could figure out how to extract and how to improve still at this coarser, like 3 kilometer convective allowing resolution. At least that's my take. But again, I'm not a forecaster. I'm not trying to take information from these CAM models.
So from the Weather Service side, how often do you see yourself or forecasters in your office using this type of output to make hail forecasts on any specific day?
It really depends on the time frame. When we're looking 12 to 24 hours in advance, the resolution is fine. We're looking at the potential for supercells, because then I'm expecting significant hail, especially in my area where I'm in the plains. It's usually in our traditional convective season. You have a supercell, you're getting at least golf ball size hail. So we're looking at more of a broader scale forecast for supercells, and then determining that hail is likely possible in that case. When you're talking about WAFs or TIM, in that case, we really haven't incorporated that into our warning decision making yet. There's definitely a future for it. But right now, a lot of the decisions that we're making on either a watch warning gap scale or within the warning time frame is really more based on mesoscale environmental information and then the radar signatures that we're seeing. So where we are currently, I don't see a need to continue to improve that resolution, but I'm very curious how things will continue to evolve as WAFs continues to improve. Even things like updraft helicity tracks can tell us that storm's rotating and that there's a hail potential there. So I see the potential for it, but it's just not something that's a current limitation for us.
Ryan, what's your take? How often do you use CAMs in your day-to-day, especially for hail size? Are you looking at stuff like that when you're issuing?
There's so much. First of all, there's so much to look at now. We go all, personally, I go all the way from just a real large scale overview, and of course, since we're doing the whole CONUS, it's even larger overview sometimes, all the way to into the oceans and everything. All the way down to the CAM guidance. So, for example, the HREF website we use a lot. I would say, there's a lot of good experimental tools, especially in our in-house version of that site. Try to there's tornado probabilities, and there's a hail and all severe and wind and all those things, kind of post-process things. Those are useful. I would say that for us, the most useful aspect of the CAMs is the ensemble of the CAMs, which will kind of show you where the centroid of the activity is going to be. And then I would say also the UH, that's a nice, very, draws your attention to, the supercell, maybe tornado, delving down into the low levels and everything. But I think it's very useful in that regard. As far as resolution, at some point I would love to see a perfectly modeled thunderstorm, and who knows, quantum computers and who knows eventually, but until then, we have to sort of read between the lines, and 3 kilometer versus up or down a few kilometers. I'm not sure it matters too much until you get the just ultra good crazy AI type thing. But yeah, so we definitely use, the high res information. It is useful. Like I said, really, since we're doing outlooks on a national scale and, kind of maybe a first guess, it's, for example, the HRF thunderstorm probability. And the cams are pretty good at producing thunderstorms or depicting thunderstorms. And then if you get an ensemble of them, it's kind of my go-to as far as the general thunder line on the outlooks. You can sort of get the outer bounds. It's a very good first guess. And, maybe a few tweaks here and there, especially in the mountains. But yeah, I think it's very useful, especially the ensemble. So.
All right, next question is going to be, can't be a good forecast without verification. Help us understand the biggest issues with verification and how we can do better in the future. Field campaign.
I can jump into that one. So I participated on Hailstone for 5 years, which was a field campaign in the early 2010s. Our representation of hailfall is not good. And that's because a lot of hail falls in the plains and not a lot of people live in the plains, and cows are not super good at reporting. So we're really not capturing the largest hail size. We're not capturing the narrowness of the swath. And it's really a limitation because it's difficult for my forecasters to continue to follow the science and say, I have a robust supercell. I haven't heard anything. I'm going to continue to put golf balls. It's really difficult. But the science is indicative that you need to keep pushing those larger sizes, even when you're not hearing anything. And it's really a limitation. We need the field campaign so that we can continue to prove to operational forecasters that when they're not hearing anything, it doesn't mean that nothing's occurring.
Yeah, good point. Any other perspectives on verification?
See, yeah, obviously we need more information. That's a gimme, and yeah, field campaign would be a big help. I think there's also an interesting piece that how you verify can be interesting. Whether and some yeah. So some of this comes down to the issue of we don't have the reports, and then also how convection initializes in your model. That's not always right. So you do smoothing, or you do object matching, or you do upscaling. There's all these different ways to go about it, and it hasn't necessarily been evaluated. Oh, this technique is either best, or forecasters want to understand this kind of verification score. I think we do kind of need to look into our methods of verifying to see what people want, what's useful, et cetera.
Yeah, good point. Well, we have just under 10 minutes, and I'm going to open it up to questions from our virtual attendees and or those in the room that would like to ask these three hail forecast experts any questions, or you could provide a comment that could spur discussion. I do have extra questions if everybody's hitting that afternoon sleep lull, but please feel free to come up and use a microphone and ask a question. Anybody? Oh, John's on his way up. He couldn't help himself. Brian, question for you.
Related to training of new and onboarding of new SBC forecasters, it's great to have your level of knowledge, right? But how does SBC handle that sort of training for things like hail forecasting, where there's pattern recognition, you're using that information and other forecasters are? Kind of interested in that.
Yeah, so, okay. Yeah, so, we, there's two main tools that we use, which is the hail model, which Rebecca's been working on, and originally as Julian Brimlow. I think we have a WAF paper about that. That was early 2000s, but it's fairly simplistic hail model. But it in certain situations it does pretty good. So what we do is we run that on the full NAM or RAP grid, and we contour it and plot it. So we can go forward in time 2 days or, every 3 hours. And you can see the areas of, large hail from the hail model across the US. So that's one input. Then the other input is the sounding analog method that I produced. I only have a preprint for that for reference, but it's fairly simplistic. It uses typical Cape shear, but also mid-level lapse rates, the mixing ratio of the most unstable parcel, 500 millibar temperature, 0 to 3, 0 to 6, 0 to 9 shear, just to try to get a good fingerprint of the sounding. And then it's a fairly small database. It's about 1,300 observed modified proximity hail soundings. So so for example, the forecaster can load up a model sounding for 48 hours from now, and they can get the hail model, hailcast size, and they can get the sounding analog best guess size. So right off the bat, those are actually pretty good. I mean, especially from a historical perspective, years ago, there was very little to go off of except, Pinot Noir and things of that nature, which, wasn't very useful really. It's just very Cape heavy, but so we have those tools. And then on our href ensemble website, and I'm pretty sure there's different versions of that website. We may have more things on ours experimentally. But yeah, there's some other statistical, probability of hail, which I haven't been involved with producing any of those. But so there's several things we can look at. And then of course, things like storm mode, hail is highly dependent on the storm mode. So if we're going to get a squall line, it doesn't even matter. We're going to limit the hail size probably, around 1 inch or, certainly not significant hail over 2 inches. And then, supercells along the dry line in the Southern Plains, it's, fairly obvious, or in most cases we're getting sig hail. So does that answer your question?
John's not up at the mic, but yeah, I have just one last comment here because we're wrapping up, and I'll open it up to the panel. The theme has been more observations of the surface, right? So I think back to a successful campaign like Shave, right, or Hailstone that did collect these observations. Do we need something at like a grassroots WFO level that is really encouraging people at these spotter training sessions, right? Let's not just report a wall cloud, like make sure you're reporting hail. I mean, how do we really begin to ensure that we're really capturing everything that's happening? Because obviously we can only do so much with radar.
Yeah, typically when we're involving the public, they get really enthusiastic for like 2 weeks, and then they don't get severe weather and the enthusiasm dies. So what I really think we need are these focused hail studies that occur for a couple of weeks at a time, whatever's possible for our researchers. And then we're able to go back and look at that versus MESH, versus the reports that we did get, and interpolate, because we're not going to get the general public to participate on a daily basis. They're just not enthused about it. Even our co-op observers don't always report severe weather to us unless we make them. So I really don't think we can leave it up to the general public. I think we need these really focused studies that are out in the field for a couple of weeks, take those back, interpolate, and be able to use that for future cases when they're not able to report to us.
Yeah, that's a great point, Jenny. Ian, I'm going to leave Ian with the last comment to spur discussion.
I might add one more.
Oh yeah, go ahead, Becky. Yeah, jump in quick.
No, I completely agree with everything Jenny just said. But I also think then we have to share the data. We can't just all keep it to ourselves and everyone has their own little bits and pieces here. But if we can share it and put it all in one giant database, John showed how powerful.
Imagine if we had all insured
losses. Okay. All right. Go ahead. Go ahead.
Oh, might as well get that one in. Okay.
I had to.
I'm gonna stay on the societal side though, and this is kind of for everybody to kind of wrap this up. Given what we've talked about the limits and our ability to come up with precision hail forecasting, what do y'all think the societal implications and impact has been? Globally this year, actually, we saw far above normal hail injuries and we saw fatalities occur globally.
Yep.
What are we doing? What have we done? And I'll leave it at that.
I think you just dropped the mic, Ian. I'm not even sure if we need to respond to that. Anybody want to take a stab? Well, I think one really right. I mean, the field campaign session yesterday, hopefully, I think does well. So, all right, I'm going to cut it there because it's time, 4 o'clock. Thanks, our panelists.
Thank you.
And I will turn it back over to Brian, session chair, to continue on with the rest of the talks this afternoon. Thank you, everyone.
All right, thank you, Victor. This is our last hour, and we're going to try to keep on a very strict time limit. So if we bump up against 20 minutes, there will be no questions. We want to make sure we get people that need to take their red eyes on time. So next is Dan Cecil. He's talking about diurnal cycle of satellite-derived hailstorms.
What am I using to advance here? Is it this? Okay. Okay, so I'm going to start off, if I can advance this, with, well, let's see. There we go. I'll start off with diurnal cycle of lightning because what 2 basic reasons. Large hail comes from thunderstorms and lightning is a lot more common and easier to observe than hail. So we have a lot more data and we can map out the diurnal cycle of lightning with a lot less need for smoothing. And you see the pattern here that you would expect, really strong afternoon pulsing of the thunderstorms over land, especially in the tropical regions. Some of the places, especially outside of the tropics, that are known for especially strong storms, so places where you're looking at for hail, they have a later maximum. Looking at the central US, that the red there for the high rates of lightning, they linger further into the nighttime. Also in northern Argentina, you see a lot more through the night, and really there's that distinction between the strong pulsing is really over the tropical land masses. And as you get into the mid latitudes, it's not quite as strong there. As we get to hail, some similar patterns there. Of course, we have a lot less data, and you can pick out the difference looking at some of the places where we get the signal from satellite for hail offshore, like offshore of South Africa or the Mediterranean Sea. Those show up well as places where you're seeing the early morning maximum, but much lower amplitude there. I should back up and go through some caveats for this type of map. Our data here, this is coming from passive microwave satellite imagery, primarily 37 gigahertz and 19 gigahertz channels. They have footprint sizes around, say, 10 to 30 kilometers. So your hail core is going to be smaller than that. You're never really fully resolving the storm. But for a lot of the storms, we're able to get a good signal there. We have some particular types of regimes where we have more uncertainty, like we're always suspicious of over-predicting storms in the tropics. Looking at these storms in different ways, whether it's from the passive microwave or from the spaceborne radar, we have a lot of indications of very strong storms there, but there's the question of whether those storms have large hail that reaches the ground, or if they have large concentrations of smaller hail that's likely to melt before reaching the surface, or maybe some of the smaller stuff does reach the surface. We also, it looks like we probably underpredict in places where high terrain comes in, or I'll say high surface elevation, like I think we probably underpredict in the high plains But this is all trained using the SPC ground-based, spotter-based reports of 1 inch and larger hail. So all trained from the US. Okay, so next I get into some maps where I'm showing the time of the peak hail occurrence. And for this, I have very heavy smoothing just so looking at the map doesn't hurt by having I made this is 10 degree by 10 degree by 3 hour smoothing. I think the first map I made was 2 degree by 2 degree by 1 hour, and it is either ugly or pretty if you like the kind of thing where a 5-year-old colors on a page. But it shows, I think, what we would tend to expect, the late afternoon maximum in a lot of places, especially in these places in the tropics where I mentioned there are the questions of, is it really large hail? Is it really reaching the surface? But definitely strong storms there, peaking in the late afternoon. As you get to places like northern Argentina, we're seeing a very late night max towards midnight. I think I have some times, yeah, you should pop up there. So like 4 p.m., 5 p.m. in the tropical land regions. 10 p.m. is what was showing up for the maximum there in Argentina, although it turns out to be a very broad diurnal cycle. Around 10 p.m. for this northwestern South America hotspot that we have, Colombia. And we've heard from people that they do have hail reports there, but they don't necessarily match up with the particular places that we're getting our signatures, mountains versus valleys. For the US, we're seeing late in the day, so late afternoon into the early evening with some kind of complicated gradients. If I move to a higher resolution there, it's probably hard to tell, but I'm looking at the US here, the far western part of what we have any colors for, so the western high plains, it's showing up as mid-afternoon, I think like 4 o'clock for the high plains, and then it gets to later in the day, like 6, 7, 8 o'clock. And then as you go further to the east, like towards the southeast US, you're going back to a maximum more like 3, 4 o'clock in the afternoon. This map, this has gone to that 5 degree smoothing. And one of the benefits of looking at that is you can pick out things like the land ocean difference with all of these places that are offshore, whether it's offshore South Africa or offshore South America, Gulf Stream, Mediterranean, those are all showing up as the late night maximum. If I remember right, the next one is amplitude of the diurnal cycle. Here, the green shades are a large amplitude cycle. The red and purple shades are a small amplitude, close to no amplitude diurnal cycle for the purple. And we see for the offshore regions, it's very low amplitude. So don't put a lot into that late night maximum. It's close to a flat line there. But it's interesting that some of the places where we do have a lot of storms, northern Argentina and parts of the central US, it's showing up as a low amplitude cycle there. For the part in the US, it's shifted to the east a little bit of where we think up for the maximum hail, like shifted into Arkansas and Missouri. That stretch, I guess, the eastern plains and towards the Mississippi Valley, having that weaker amplitude of the diurnal cycle. I think that's because of a combination of the late night MCSs that are propagated into the region, that's giving you some of the storm count and some of the normal afternoon development. Putting those together, it makes a weak amplitude for the diurnal cycle. So here I have some plots, the line plots there on the right for looking at individual locations, plotting out the diurnal cycle for those individual ones. So the ones that are the really strong peak, those are both from Africa, Central Africa and West Africa. On the map, I have the numbers where these are, the meaning of the numbers is just ranking where the maximum ranks in our global hail climatology. But some of those are really close, so you wouldn't want to put a lot into what's number 1 versus number 2 versus number 3. But anyway, the the locations there in Africa, they have that strong peak in the Diurnal cycle in the late afternoon, like around 5 o'clock local time. As we get to central US and Bangladesh, they both are Eastern India. They both have very similar diurnal cycles from our data sets, peaking a little bit later and a fairly broad peak between about 6 and 10 local time. Argentina was really interesting to me in that its diurnal cycle is pretty flat. Depending on just where I'll put the grid box, it could be a peak at 10 o'clock or it could be a peak at 3 in the morning, but it doesn't really go away in the morning like the other places do. So that's just focusing on the 6 places that had the strongest maxima of hail. Next, let me skip past this one. Next, I did the same kind of thing at expanding it out to the top 20 hotspots. And I don't want to go through or don't want you to worry about which one is which, but this is just, the point of this is showing that for most of the places where you have a lot of indications of hailstorms around the world, you get that same kind of pattern. The very late afternoon into the evening maximum for the storms, if it's something over land. If it's along a coast or just offshore, then it tends to be a very flat diurnal cycle with a little bit of a peak in the early morning. Let me back up to the one that came before that. So this is the same kind of thing, but just going back to the lightning data and looking at thunderstorms. And it's a similar type of signal that you would see there, just basically shifted to be a broader peak in the thunderstorm data than in the hailstorm data. And they tend to start earlier in the day, which makes perfect sense. You get your storm initiation earlier, and the general thunderstorm activity lasts longer than the strongest storms or the strongest portion of the storms. Now, what actually motivated us to be looking at the diurnal cycle from this is that all that I've been showing so far comes from the TRILM and GPM satellites, which process through the diurnal cycle. But we also have a lot of satellites with the same types of measurements from sun-synchronous orbit. So with those, we're stuck just looking at particular times of day. The blue rectangles there are basically between about 12:30 and 3 o'clock local time, AM and PM, because the AMSR radiometer on the Aqua satellite, then on, I forget, the GCOM W1, I think is the next satellite with an AMSR. They have equator crossing times at 1:30 AM and PM. So the first global climatology, pseudo-climatology, I think I called it, that I had published using this type of method, it was using the AMSR data. So it was skewed towards that early morning and very early afternoon. And it turns out that that's a pretty good time for looking at Argentina. And in that climatology, I made a big deal of Argentina having the strongest storms. Probably overplayed it a little bit there. In the other data sets that we have, even from TRILM and GPM and looking at the radar or looking at the lightning data, they definitely have very strong storms. But using the sun-synchronous satellites like the AMSR, it skews the picture that you would get of the globe, because not all parts of the globe have that same diurnal cycle. Just along the same lines, this slide has the maps from 4 different satellites. So the 4 columns are the 4 different satellites. And the 3 rows, top row is 2 AM, then 2 PM in the middle, and then 6 PM on the bottom. And that's limited to just the ones that are not in sun-synchronous orbit. So for the 2 AM view of the Earth, Argentina really stands out. As we get to 2 PM, it's more of Central Africa standing out. And if we're stuck with just those sun-synchronous birds, we're not going to get as much of a depiction of some of the other places, like 6 PM being a better time for seeing where most of the strong storms are occurring in most of the world. So conclusions, I think I've probably repeated some of the same things a few times already, so don't need to focus here. But most of the places there is over land a fairly strong diurnal cycle peaking in the late afternoon or the early evening. The diurnal cycle of the hailstorms tends to show up as a sharper peak, a stronger amplitude than thunderstorms in general. Some of the interesting things that stood out as being different from those generalities were like that Argentina especially having the very flat diurnal cycle, and the late night peaks for the places that are offshore or over the ocean. So I'll wrap up there. Any questions? Ellie?
Ian, one thing I noticed looking at your data looked to me as if China didn't have very much. And I'm wondering, is that an artifact of when the satellites are moving over China, or is there some meteorological reason why China doesn't seem to get hailstorms as frequently as other places?
We show the storms there, but just not as frequently as other places. And from what I see in the literature, my impression is a lot of the hail there is on, a lot of the reported hail there is on the small side. And we're training our algorithms on reports of 1 inch and larger hail. So that's what we're trying to retrieve, whether we're successful or not. So I think that's the reason. But there are probably some other places where there's always, every time we show these maps, there's places that don't show up very strong, and people will tell us, I know there are a lot of storms in this location.
We've got like 5 minutes, so anyone has a question?
That was really interesting, thanks. It seems like Argentina is really an outlier here in terms of the diurnal cycle. Can you talk a bit about why that might be the case?
I wish I had a good answer. I don't know.
Anyone in the virtual space have a question? Feel free to raise your hand on Zoom and get to you. Anyone else here have a question? Not seeing any. Thank you very much.
Thanks.
All right, we'll move right along, and then we have Chandra is going to be talking about a hail identification algorithm for GPM.
Thank you for most of you sticking to land, and then so in fact some people left and they apologized to me before they left. Anyway, this is the hail identification algorithm for with using GPM dual frequency radar. And so, you know, historically I'm a ground radar person, and I am also the type who doesn't look at data beyond 60 kilometers because I think it's too coarse in resolution. And then somebody said, we're going to serve you right, and then we're going to make you look at hail from space. So be careful if you complain too much. This is where you end up. So I wanted to first describe the hail algorithm, and then, thanks to the predecessor, but we are sitting a little better compared to him on resolution. And we are working with radar resolution. Our swath width is narrow, but our resolution is a little higher. And then looking at most of my talk is about, because we've spent quite a bit of time developing the algorithm, and then I'm too busy showing, yes, this works, yes, this works, yes, this works, and so on. So this is the background. So there's some 101 about GPM radar. It is 2 frequencies at the KU and KA. And a long time ago, I used to work with a radar here at NCAR called CP2. And I don't know how many of you, few people will remember that radar. So in the early days before polarization, that was the way to go for detecting hail, which is using dual frequency ratio. And I spent a lot of time looking into that. And then And then some of that background came back to help, and we started developing this dual frequency ratio. And also some of the knowledge that was gained during that time was also very helpful, because don't work with attenuation corrected data, because then that's like a single point of failure. You didn't do your attenuation correction rate. You have melting hail, you have water coating. Everything is on the table, like it's been described all the time. So a lot of the algorithm was pretty much developed on the measured dual frequency ratio and looking for activities. Another good thing that happened was DPR, that is dual frequency radar, changed its scan pattern on May 21 to have full swath KU and KA. And I've been lobbying for that very hard, and finally was successful. And so these are the various products that we put out. The precipitation type, melting layer top, melting layer bottom, melting layer, it's a quality index, and then basically Dan Cecil has talked a lot about this confusion between graupel and hail. That's something a lot of us share, because low density ice versus high density ice. And even a long time ago, when I did this work with T28, also we dealt with these issues. And okay. So there are a lot of detailed papers about how this algorithm was developed. So, but I will give the basic principle. What are the indicators that really helps out? So you look at the vertical slope of dual frequency measured signal. And for simple stratiform rain, that slope is small, whereas for just snow, it's large. And graupel and hail, it's sort of medium. And then when it goes into hail, that's really small. And then you look at reflectivity max, and then some of that reflectivity being itself to work as an indicator was Matt talked about it. And then storm top height, which is actually storm top height, we had to sort of self-normalize it with respect to different latitudes, and then essentially get this precipitation type index. But, you know, like everything else, you have been in the business of developing algorithms that work on radar for a long time. When all the data is correct, when you got this one pixel, well, data is clean, you can show the algorithm works. So finally, when you make the algorithm work in real time, only probably 2 lines of code is the algorithm. Then the rest, 20,000 lines, is the algorithm doesn't blow up on your face when it goes through all sorts of data. So that's the key thing, is to make the algorithm robust, because this is going all over the world. It's seeing all sorts of things, and then it has to work, and then it doesn't blow up on your face. Okay, at the end, finally, for me, it's self-validating, because in the 80s and 90s, I worked a lot on, now people are working on getting hail size. Those days, detecting hail was a big deal. So here's hail. See, the dual pole radar can detect that. That was a big deal those days. And so I have a whole set of examples that's used by others. And then we have done our own validation. And I wanted to go really point-wise, very precise, aligned, self-aligned validation I would show. And take this case, this is Naples, Italy, and they found a massive hailstorm. So this is this is the GPM radar KA data. This is KU, and this is ground radar data. For referencing, this red line is nadir, and this is away from nadir, and then you can get an idea of distance. And then this is ground radar distance in kilometers. And then this algorithm is given into the automatic processing system, and it's not done by us, so we don't have a luxury of doing some Monday morning quarterback and change the result. It's run automatically in the NASA program. And this is hail identification. And you can see here in this area, hail was detected. Then another case, this was along Colorado-Kansas border. And this area is well known and prone to hail. And this is Morose et al. Paper with, I think Battaglia is one of the co-authors. And it is their own, so this identification of hail from ground radar was not from us, it's from their paper. And this is identification of hail from spaceborne radar. And the resolution is 5-kilometer footprint. And you can see the pattern, the red here is hail identification from their own process. And you can see it's such a beautiful, nice pattern matching you can see with the hail identification. So to the level of precision and resolution you can get. So let's keep going and let's move to Arkansas. And there is more data, and I'm showing different varieties of data to keep your interest at 4 p.m. on a Thursday afternoon. So this is ground radar data at 3 degrees elevation, and this is 4 degrees elevation from NEXRAD WSI 88D. And this is the red line is nadir. And then you can see the hail identification here and the hail identification here. So it's a nice match. So you can sort of get this standard story. I can keep going. So this is what is declared as a champion hail case by Battaglia in their paper. And this is Australian hail. And this, I was looking at it, this is one of the cases that Dan showed. And so you can see the hail detection. So then let's go to Venice. And I didn't know it rained hailed so much in Veneto region. But let's again look at the hail here. And this red line is nadir. This is the GPM footprint. And then you can see this is the GPM KU radar observations in KA. And then you can look at the vertical extents of the storms. And this is the hail identification. And people like Laviola and others have actually determined their hail algorithm using radiometric measurements. So then let's go to this multiple scattering. So there was a lot of, Matt talked about different scattering mechanisms, that one of the things that people worry about looking from space is multiple scattering due to hail. And so there is a multiple scattering index that's being put out. And sometimes, every time, multiple scattering can happen even when there's no hail. But hail most of the times does produce multiple scattering. So we have to be careful. The converse cannot be taken to be true. So we are comparing the observations here, and this is our hail product. And then wherever you see hail product, the multiple scattering group has put out multiple scattering index detection observations. So then we go and then do, we are going to do more of these cases. The bottom one is from Sarah and Dan, 2019 from GMI. The top one is, both are radiometric techniques from Rose et al. And this is a purely radar-based technique. We have to be careful. Our resolution is 2 degree by 2 degree. And then you can see global distribution. And so we also don't see much hail. We do some hail, but not as much over China as you, and this is completely different physical measurement. Okay, then we were asked to do more of a quantitative index to come up. That is, you put a footprint, and then ground radars, people do hail warning, and then how much of this footprint are we able to match in terms of probability of detection of hail. And this is the metric that is you go inside the circle, and then you do a quantitative validation, and then the match ratio that we find between ground radar based technique and then the satellite radar based technique is it's most of the time above 90%. And I saw Sarah before she left, and she asked, is it about 96%? When she was a student, I kept telling her 96%. She still remembered that. So to summarize, this is a production algorithm and that is running on GPM. So people who run access GPM data will have access to this. And then the hail flag identifier basically says whether hail exists or not. We also have a product which we wanted to put out and say it's grapple and hail possible, but we were under a lot of pressure to put out a hail only product because apparently grapple is not so famous compared to hail. I don't know why. It's so important for electrification, but it doesn't seem to get people's attention anyway. So we've been continuously validating and trying to fine tune and improve performances. And global map fairly agrees well. And then, so now we have to get into a lot of these cross validation with other techniques and explain any difference that should be happening. And I think that's my last slide. Thank you.
Plenty of time for questions. If anyone has questions, go ahead.
I tried to save time in my talk so I could ask you a question. In your algorithm, is it basically checking, one of the early slides had a few different things with the dual frequency ratio, ZH, the storm height. Is it basically checking to see if a criteria in each of those is satisfied, or does it allow for?
So what we do is, thanks for asking, because a lot of people think when you do all this and then modern days, are you doing machine learning? No, this is not machine learning. This is a physics-based technique. So these are the various indices that get into this super medicine making system. So DFRM slope is the key thing. And then storm top height. And all these go in, and then we create a precipitation type index. And I didn't have the slide that shows the whole details of the equation because I used to show that too many times, but then I said I should not have more than 15 slides. And there's like a whole bunch of papers that describe this. But you see this, this is the precipitation type index. I showed an example. If you have snow, you see where it falls. Whereas if it's grapple and hail, it peaks in a small number. So within that region, so this, it's a little hard to read. This red line is CDF, and this red is all hail. And if that precipitation type index that's generated is below 3.5, that's like a cutoff frequency, a cutoff value I put, that's hail. So it's all physics-based index computation. I am under a lot of pressure to generate some machine learning stuff. So I will do something because everybody thinks, oh, you got to do better with machine learning. And so I'm going to try and see if that would work out. Thanks for that question, because I ran through that algorithm details. But the key thing is dual frequency. And to come back to Matt's big discussion about hail size, don't ask me how, I'm following my nose here. I still think dual frequency or multi-frequency ratio will push this hail size forward. I'm starting to look into that. And but I was looking at some of your graphs and I was a little, I should say, worried, because after a certain size that things go just flat. But let's see. Okay, because but I'm looking at, of course, KU and KA band, and but we're also looking at the advantage of looking from top down is when you look this way is there is not much attenuation nonsense you have to deal with, and that's a different story also. That's much different as opposed to the whole philosophy of working with ground-based radars. So I'm pinning a lot of my hopes on looking at hail this way.
Good enough. I had a question about the physical basis for the storm top height in this. And can you go through the physical basis of the reasoning behind the storm top height?
Yeah, the physical basis of storm top height is a lot of people said when you have tall storms, then the tall space has to be okay. There's one more thing that is fundamentally important. There is hail in the column. I'm not saying there is hail on the ground, but 90% of the time when there is hail in the column, there is hail on the ground because it's hard to melt all the hail before it hits the ground. That's point A. And then second thing is there is this tall storm, and then you need to fill that space. And then what do you fill it up with? You fill it up with ice crystal, grapple, and then water-coated ice, and then water. These are the few things you can fill it up with. So it turns out that the taller the space is, the probability is very, very high that you have hail. But that's not the only thing. If it was the only thing, I don't need all the other parameters. That's why I put it in, it's easy to put it in a 4-dimensional space. If I could, I would show. It's that storm top height in addition to the dual frequency slope. It's not the dual frequency value. It's the change of dual frequency value with height. That is the killer finder for hail. So it took a lot of time and secret recipes and grinding. So it's not just the reflect storm top height. And then also we had to throw in, then we can't lose the peak value of reflectivity. So throw that in also, then it improves. You know, like everything else, you go 80% of the way with one measurement, and then you want to keep improving. Then you add one thing, it gives you another 3%, another 2%. So most of the way we go through dual frequency, the slope of the dual frequency ratio, and then rest is just to additional dressing to improve the algorithm.
We're still 5 minutes ahead, so if we have one more question. Julian?
I'm really excited about this product. So how far back in time does it go? And is it updated in near real time?
Did you say real time?
Yeah.
So this product, I think as fast as NASA puts out, it's in real time. How far back does it go? I had a date in the thing. So the scan pattern originally was not fully dual frequency. It was mixed pattern. Original pattern was this way. You can see the blue is KU footprint, and then the yellow is KA, and then there was a KA interlace footprint. And then it was all like, I mean, imagine for an algorithm developer, that's a nightmare. But we did that. But then this got simplified into a clean, full swath dual frequency footprint. So that happened May 21st, 2018. So 2019 onwards, they just go, initially there is some hiccup when the scan pattern is changed and so on. So, and then there is also all this reprocessing. That's why I put this, you see the title says version 7. That's the meaning of it, version 7. So you have to reprocess, and then, so that should like a clear answer, 2019 onwards. And then I think whenever, then do you know how fast the data comes out after this? That is, so, yeah. So that should give you the answer.
All right, thank you. All right, we're down to our last talk. You know, people were talking about how grapple doesn't get respect. I'll just tell a very quick story. I was watching a Cleveland Browns football game last year, and there's grapple falling with 30-mile-an-hour winds. And the commentator kept mentioning, this looks like hail, but I'm not quite sure what it was. And so I just randomly decided to tweet at him saying, this is called grapple. And this was in the first quarter. He came back from halftime. He read the dictionary definition of grapple on the air coming back. And they put up the weather graphic saying 38 degrees, 30-mile-an-hour winds, and grapple. And they put it in quotation marks, like they weren't quite sure exactly what this is. But so if I've done nothing else in my career, I educated about 5 million people on what grapple is. And maybe half of them were drunk and don't remember it. So anyway, we're down to our last talk now. Andy's going to be talking about hail growth regions with radar.
Okay. So the subtitle, which I didn't put in here, is to mesh or not to mesh. That is the question. And so I will be using T28 data. And Andy Detweiler did a very nice paper in 2012, basically extracting really usable T28 data. And then Paul Field did a paper using that data, but also using actual T28 windscreen photographs to see if indeed there's hail there. And then we did a paper recently where we used Paul Field's data and we used scattering methods, and we used actual 77 of the 3D scans to try to get the best indication of true backscattering. And so those data are used in the study. So I was kind of very curious where the T28 data and hail were located. So in this plot, I really looked at some aspects of where the hail was found with the T28. And top left plot is temperature. And we have 300 really high quality 10-second data points. And so the median is the vertical lines. And so almost all the T28 data, which I'll be showing, is temperatures from 0 to -10 C. The plot on the right shows the vertical velocity distribution, and kind of on average, just a little bit above 0 meters a second. But as you see, it extended up to about 40 meters a second. The lower left plot shows the liquid water content distribution. And in some cases, it was 3 grams per cubic meter, not super adiabatic. Right plot shows the ice content calculated from the particle size distributions. And the ice content is the black line, and the red line shows the total water content, liquid plus ice. So you see this quite some high total water contents. The next slide shows the hail relationship to vertical velocity. Top left shows what I was interested in is to see where the hail is located. So the total concentration and the medians are the red points, and purple is less than 3 meters a second, and yellow is greater than 10 meters a second. So you see here, on average, the total concentration does not depend much on the vertical velocity. In fact, it's almost 0 on average. The maximum diameter on the right panel shows an indication that some of the largest particles are in the peak updraft core, but on average, the largest particles are sitting near the updraft downdraft interface. The left panel, bottom left, shows the liquid water content. And as you see from the red dots, there does seem to be an dependence of the liquid water content on the vertical velocity, which is kind of what you'd expect. And the bottom right shows the ice content. And on average, the highest ice contents are right at the updraft downdraft interface. So largest particles are sitting kind of on the updraft edge. And so I fit exponential particle size distributions to the data, and the vertical bars and the purple are the median values, and the particle size distribution slope is on the x-axis. Number concentration normalized is on the right axis. And so you see here the higher concentrations with higher particle slopes. I show here some data from other authors, and the Volvogel, which is widely used, is kind of in the middle and the top, but it does not span the wide range we do. And I looked at particle size distributions just greater than a centimeter to see perhaps what melting effects would do as the particles fall below the melting layer. And indeed, the concentrations are a little bit higher on average, the N0 values, but the slopes are narrower. Okay, so next slide. Here are the calculated multi-wavelength radar reflectivities sorted according to their reflectivities. And so the point of doing this is you see at L band and S band we did these different wavelengths here, 6 of them. And as you see, L and S, L and Rayleigh, which is underneath the red line, are approximately the same. And then you see the very, very strong wavelength dependencies. And so, as we just heard from last talk, dual wavelength frequency might be a way of getting at particle size. But so I just wanted to look at a couple aspects of particle size distributions as a function of radar reflectivity. Radar reflectivity is on the x-axis, particle slope is on the y-axis. And so these are the 6 different wavelengths I just mentioned. And as you see, there are quite nice dependencies of the particle slope on radar reflectivity. So perhaps this is a way of getting more information that you can use with radar reflectivity to get aspects of the particle size distributions. The next slide shows representative Hale diameters versus the radar reflectivity. And I didn't indicate, same 6 wavelengths. And so as you see there, for all the wavelengths, there's and what I show here is the maximum diameter in red, and in black, I show the median diameter. So you see here, there is some reasonably good information, at least at temperatures below 0C, between these characteristic particle diameters and radar reflectivity. So the next slide shows the ratio of mass weighted to maximum dimension. And so basically, as a function of reflectivity on the x-axis, and these are the 6 wavelengths, and basically what it shows is you get to higher and higher reflectivities, the maximum diameter, particles in the larger end of the size distribution control the reflectivity. So that is also useful information. And so I wanted to look at the kinetic energy distribution with size. That is, I mean, I was trying to figure out, okay, what are the characteristic sizes that contribute to the total kinetic energy? And so the maximum diameter is on the x-axis, and this characteristic diameter at 25th, 50th, 75th, and 90th percentile is shown here. And so if all the particles were, all the kinetic energy was contributed by the largest particles, then you get the red line and the black line would match up. And so what you see, though, is that the 50th percentile, roughly the median, that is contributing kinetic energy, is about half the maximum diameter. And so as you get to the 75th percentiles, this goes up. And so this could be useful for getting some information on what are the important particle sizes to concern ourselves with. That is, maximum diameter might not be the most important thing. And then this, let's see here, let me see here. So this is kinetic energy flux versus radar reflectivity. And so again, the 6 wavelengths, x-axis is radar reflectivity, and then y-axis is kinetic energy flux. And the red line and the red points show Rayleigh scattering. And so, and then the yellow points and blue, I won't go into more detail, show the kind of the averages for each of these wavelengths. So the first thing you see is the kinetic energy flux is quite dependent on the radar wavelength. And so it gets further and further away from the Rayleigh. And so this might provide an opportunity to at least derive kinetic energy flux from radar reflectivity. And then this is represented, let's see, sorry. So this is the relationship between kinetic energy and maximum Hale size. And what I show here is kinetic energy and kinetic energy flux. So there seems to be reasonably good agreement between the maximum diameter and the kinetic energy and kinetic energy flux. So again, if we have a maximum diameter, perhaps we can get some idea of what the total kinetic energy flux is. And so going on to this question of to mesh or not to mesh. So I show here on the top panel, the kinetic energy flux and as a function of radar reflectivity. And I think I used S-band here. The red points show the width-mesh relationship. And what I use here is the terminal velocity and the masses from that are used in mesh. And what I use for our data points, which are the blue points, are our better estimates of mass and better estimates of terminal velocity. And so you see here, there's quite a difference at the lower reflectivities between the mesh, which is quite a bit higher, and our calculated from, but we've used here for both methods the same mass, the same size distributions. So the only difference then is terminal velocity and mass. And so the lower panel shows the ratio of Vollvogel et al. To the T28. And just using T28 size distributions with different masses, terminal velocities. And you see here, there's quite a wide difference until you get above about 55 or 60 dBz. So from that, I kind of conclude mesh needs to be revisited. Summary and conclusions. So data from the T28 Hail penetrating aircraft are used together with calculations using DD-SCAT of radar reflectivity to characterize hail and clouds. And I was interested in some of the microphysics. Largest hail is predominantly located in the weak updrafts, and the liquid water content, vertical velocity are directly related. So that is the peak updrafts, or the updraft core, is a good place to really grow the hail, but it appears to be falling out near the updraft edges. And ice water contents, which is follow on to that, are highest along the updraft edges. And the PSD median and maximum diameters both increase with increasing reflectivity, and the separation between them increases with increasing reflectivity. And the particle size distribution, kinetic energy, and flux are directly related to radar reflectivity. And our results suggest that the mesh relationship needs updating. Now, one point which is not considered here, nor is in mesh, is the melting of hail from the melting layer of the surface. And that's something I hope to look at.
Love the calculations, Andy. I had a question, actually two questions. If I recall, the reflectivity scattering calculations were for dry hailstones?
Yes, yes.
And does the T28 data set provide other information about other particles that may have been co-located with the hail in the updraft, which could also contribute?
Yes, we've only in this looked at particles larger than 0.45 centimeters, or basically this is for the hail population. We did not look in this study at Graupel. And so we were specifically looking at that, but there are lots of other small particles present. Okay.
We made it. And that will wrap us up. First, thank you all for sticking with us. What another great workshop. A couple of thank yous. First of all, Kelvin and Jesse, please stand up in the back of the room for making the hybrid stuff go. Dealing with all the glitches. Outstanding job. I've watched a lot of bad ones of that in the insurance industry, and you guys are killing it. So well done, guys. We appreciate the hard work, and I hope everybody out there in the virtual space could hear our recognition for Kelvin and Jesse back there. Also, Shelly Rayburn, she's not out front. She also handled a lot of the logistics here at NCAR to put this on. So for those of you around here, if you see Shelly, please tell her thank you. We thank her a lot. Let's just give her a round of applause too. And everybody else, thanks for sticking with it. What a great workshop. We'll go ahead and kind of advertise the next one. The European community is going to do theirs in 2024, so we'll look to do ours again in 2025. Chances are it will still be here at NCAR, but we'll evaluate things as we go. You never know how the world changes. We didn't predict global pandemic several years ago, but here we are. So it's been wonderful to see everyone, wonderful to have our virtual participants, and it's been a wonderful 3 days. So thank you again, and that will be a wrap.